and dock with the second spacecraft. So that means finding it in space, aligning with it appropriately, and then bringing the two vehicles together without smashing them into and destroying each of them, all without human intervention.
This capability is the kind of thing you need for docking with spacecraft that were not originally designed to be docked with and serviced, which happens to be a vast majority of them. That's why Raven's time on station is critical for the future of on-orbit servicing, assembly, and manufacturing, or OSAM. The OSAM-1 mission will use Raven's relative navigation capability to autonomously, meaning no humans involved, rendezvous and dock with the satellite, and then telerobotically refuel it. This will be the first time in history a spacecraft not originally designed to be serviced will be refueled as a means to extend its operational life. Raven is also important for future exploration missions.
Raven's technologies can be applied to future NASA missions because if humans want to make a footprint in the solar system beyond low Earth orbit, which is where the International Space Station is located, we're going to have to rely on some form of autonomous docking technologies in the future. Whether it be an unmanned cargo vehicle meeting up in orbit around the moon, refueling tankers located in geosynchronous Earth orbit, or a return vehicle arriving on Mars in advance of a crewed landing, all of these feats will require the technology we're developing with Raven.
Using its 3 eyes, Raven is looking to the moon, Mars, and beyond.
Relying on highly robust autonomous systems becomes more crucial the further you move away from Earth as the communications time increases drastically. Once you move past low Earth orbit, it becomes very impossible for humans on Earth to do these highly complex maneuvers in real time. It's more efficient to allow computers to perform these sequences autonomously without human intervention.
Although Raven has successfully concluded its main mission objectives, it remains on station. Meanwhile, its team on the ground is using what they've learned to develop more never-before-seen technologies that will enable future space exploration.
Before I started digging in that other bag, here you go. No problem.
If you need to fix something in space that wasn't designed to be fixed, it's going to take all the experience you can get. With that in mind, when the International Space Station's Alpha Magnetic Spectrometer, or AMS, needed repairs, NASA's Johnson Space Center and Goddard Space Flight Center used their joint expertise to make it happen. At Goddard, that expertise resides in NASA's Exploration and In-Space Services Division, or NEXUS, which evolved from the office that was responsible for the Hubble Space Telescope servicing missions. Key to these missions was the development of specialized tools. While you've probably heard of Hubble, you may not be as familiar with AMS, so let's start there. Designed for a 3-year mission of sifting through cosmic ray particles, AMS has been looking for signs of dark matter from its position on station since 2011. Hundreds of researchers have used the data collected to investigate the source of the mysterious substance to help us better understand the origins of the universe. To continue this important data collection, AMS needed an upgrade due to general wear and tear from the harsh environment of space, specifically a new cooling system. A repair could extend its life beyond what was originally planned. Sounds easy enough, right? In fact, due to the instrument's complexity and the fact that it was not designed to be repaired, even gaining access to the system to replace it was difficult. AMS's design did not incorporate the kinds of interfaces that make spacewalks easier, or have the ability to be serviced with traditional multi-purpose tools. And so, over the course of 4 years, NASA got to work designing and developing some of the most complex spacewalks since the Hubble servicing missions in the 90s and early 2000s to fix AMS.
The AMS tools themselves were unique. They were built specifically for this task, a task that was never intended to be performed on a spacewalk. And so that required a lot of thinking about how we were going to get inside so that we could access the tubes that we needed to cut into and then install the new thermal control system, but also how to put handling aids on it so that we had a place to attach our tethers, to attach our foot restraints, to have handholds, have a place to attach equipment that we needed out there.
NASA developed 20 specialized tools to make the job possible, and on November 15, 2019, astronauts Andrew Morgan and Luca Parmitano got to work. On this first spacewalk, astronauts needed to get access, By design, 5 of the tools could be seen floating off into space, attached to the debris shield that was removed to give the astronauts access to the heart of AMS.
The debris shield handling aid was one of the first tools that Luca installed on the EVA, and this gave us a handhold to install on the debris shield to work from, but also a handle for me to hold on to ultimately when we jettisoned it overboard to the aft side of the ISS, which was a lot of fun to do.
The astronauts continued with 3 more spacewalks over the next 2 months, using all of the specially designed tools. One such tool was the tube cutting guide, which was a direct result of multiple practice sessions at Johnson Space Center facilities like the Neutral Buoyancy Lab. While practicing, astronauts communicated the need for a way to identify and verify the correct tubes to cut, since they all look the same to the astronauts' eyes within the spacesuit.
After we had removed the debris shield and the VSB cover, now we have the tubes exposed, and we actually had to cut into those tubes in order to pull out the correct ones to connect with the new thermal control system, the new pump. In order to do that, we had to be very sure of the tubes that we were cutting. These ingenious tube cutting guides installed over the top of the tubes and made sure that we knew and we were communicating correctly with the ground team to make sure that we were cutting the correct tube at the right time.
In January 2020, Luca Parmitano and Drew Morgan completed the 4th and final spacewalk to repair AMS. Because of their work and the ingenuity of tool designers and engineers, the instrument is now back in commission and able to continue to collect data about the origins of our universe for years to come.
People from Goddard and JC spend a lot of time developing these tools with their knowledge and the support of astronauts like Chris Cassidy. And we are very thankful that we were privileged to use those tools and to put them to very successful use. Thank you very much.
How is the quality of the TV?
Oh, it's beautiful, Mike. It really is.
I'm in first grade and I'm watching Neil Armstrong and Buzz Aldrin dancing around like every other kid who's out there watching this. They want to go do this. This is the coolest thing ever. And I remember asking my dad, what kind of job do I need to have growing up that I can make enough money that I can go fly to the moon? And he goes, well, there's a job out there called being an astronaut. And if you are that, they will pay you to go to the moon. They're going to pay me to go to the moon. That's it. I've made my career decision. I'm going to go be an astronaut. I did not think the experience of spaceflight would change me. And I hear about these people going having this overview effect, and they come back and what am I going to go experience out there that's going to change who I am? But it made me think about a lot of things. And so for the first part, we all had that part where you're seeing the Earth, and you see yourself next to the Earth, and you feel very tiny next to the Earth. Then you turn the other way, and the Earth seems very tiny compared to the cosmos out there. And so you feel like you're 2 orders of magnitude down in terms of the size of things out there. All of life, all the history of life, all of your life, and everybody you know is in this little tiny membrane of air that sits on top of this planet. And beyond that membrane of air is this abyss of space. It's just, there's nothing life-giving about it. And that's it. That's all that separates you. And it makes you feel like we're in a very tiny spot out here. As big as the Earth seems, it seems suddenly very, very finite. One of the things that got me one day, we had some time off, and I wanted to go get some pictures of items that I'd flown up for other people out there. And so I get out there and I crank open all the different panels on the cupola window, and just by dumb luck, we were flying down the spine of New Zealand. So you've got this emerald green island with all the mountains, and you've got the ocean out there as the backdrop for all these photos. And it almost made me forget to take the pictures because I was too busy gawking at New Zealand out of the cupola as we went over it. Going on my very first spacewalk, I looked down, and that was my first mistake because this was the Amazon rainforest beneath me. It's February, I guess it's summertime in the southern hemisphere, so I could see all the way down to the river itself and all the dark green lush jungles, the brown river and all the estuaries flowing into it. I can see this muddy delta going out into the Atlantic Ocean, and I could see the gray and snow-capped peaks of the Andes Mountains all out to the west. And so despite my best intentions, Mother Nature was saying, you will not ignore me, you must pay attention. And I'm just sitting there just gobsmacked back looking at this thing and trying hard to tear myself away. Fortunately, my lead spacewalker, Steve, he just sat there and said, just take your time and take the scene, and you will never see something like this again, ever, so you might as well get the experience now. My advice for humanity is, this is a great place to start, but don't stick around here very long. We have opportunities out there. I forget who it was who said, if humankind was meant to explore the universe, God would have given us a moon. We need to take advantage of that, use that as a leaping pad to get off into other places. Someday we're going to need to be from space and not going out there, simply going into it.
imagination of a new generation. One of the great powers of the International Space Station is its duration. The ability to do an experiment, take that knowledge, design a new experiment, follow on with that knowledge, and then do the next generation after that.
NASA's been launching vehicles for decades, and each one of those vehicles has an experiment on them. But never before have we had a laboratory totally dedicated to these kind of experiments.
One of the things that's most promising is that the scientific value and the economic value that will come from the space station research is just starting to show up.
The developments that we're making now are really setting the stage for this commercial market in space. The efforts that have led up to this through the performance of all of these research investigations that we've already had on board, doing foundational research and testing out new technologies and methods, feed this market and feed the capability of doing future research in space, and also in having new commercial entities operate in that space.
We put together the ISS Benefits for Humanity book to really compile the stories that we knew of the amazing things that had been accomplished. The challenge with science is that it takes time. So even a new discovery that is clearly relevant to treating a medical condition could take decades for that treatment to actually come to market. And so we wanted to capture the state of those different new discoveries and how they were proceeding into benefits for humanity. But we also wanted to tell the stories of the people whose lives had already been changed.
We've put in specialized sections to both economic value and scientific value in order to try and demonstrate to folks what sort of value space station research has.
The scientific valuation section, we were interested in just saying, hey, we have all these publications, these scientific publications that come from ISS. What should we do with them? How should we communicate why they're important? Yeah, we've got thousands of publications, but What does it mean? And how has it advanced science as a whole for Earth and also for spaceflight? So what was shocking to me is, wow, look at all the publications that have come from space station research, and other people in non-space disciplines are finding those publications and using them in their own research. And where you can integrate space research into everyday research on Earth, you know you're having the most impact on science.
One thing we're adding is a lot more information about commercial development in low Earth orbit that is leveraging the space station.
The space economy today is still emerging, but its valuation has doubled in the last 10 years, and there are more active participants in low Earth orbit than there have ever been. The International Space Station has contributed to the commercialization in a couple of different ways. First, with commercial resupply, encouraging companies to develop their own capabilities, and then those capabilities can be used not just by the International Space Station. In terms of research, there are 12 commercial facilities that are operating right now, and they've greatly expanded the kinds of research that can be accomplished on ISS, and they're really bringing both new customers into the space market, but also they are allowing new entities to form that are learning the processes by which you conduct business in space.
Commercialization is key to the further exploration mission that NASA has. We intend to use space station to help commercial entities enter the market in low Earth orbit. And we also expect them to be able to provide goods and services that someday will help us in our exploration mission beyond low Earth orbit.
Scientists tend to ask, what's the next question? So the next question for space station is, what are we going to do next with this platform?
This is the golden age of research. We will likely never see such a strong microgravity science program in the future. We will have lots of human exploration, but to have a sustained laboratory in the way that we have now, now's the time.
This research is feeding our exploration goals beyond low Earth orbit and developing the companies that hope to make low Earth orbit part of their business plans. These two goals go hand in hand, and the International Space Station is the way to get there.
We really want to tell the stories of people and products and economic development, all of those things that are making the world a better place through our international cooperation on the space station.
Most of the children, they come here with waterborne disease.
So many children under 5 suffer from diarrhea.
They're complaining about the abdominal pain, skin rashes.
They get waterborne illness through drinking waters.
Most of the community members had little knowledge regarding the use of safe water and what safe water is.
Because most of the water we use it without knowing it is affected with disease or not.
So we need to test them so that we make sure that the water is safe or not safe.
A lot of people have the idea that water quality is too hard to do in the field and it's too complicated.
Having to transport samples, having to have reliable electricity, having to heat samples or keep samples at certain temperatures or put them in refrigerators.
But probably the biggest challenge is actually the cost.
The price was really high, up to $300 a test.
So all those things come together to make it really difficult to use a traditional laboratory approach when you're testing water. What's been missing is the really simple, cheap test kit, and that solution came from above. On the space station, we recycle almost all of the water that the astronauts drink, and that constitutes a risk because if that water became contaminated, the astronauts would have to abandon the space station in the worst case scenario. What we needed on the space station was something that was small, easy to transport, and didn't require a lot of training for the astronauts. We developed a water test kit that was really easy to use and used off-the-shelf components, and we called that the Microbial Water Analysis Kit, or MWAC. It's basically a bag that changes color in it, and the astronauts just had to hook it up to the water system, take the sample, store it overnight, and read it the next day. It worked great, and it's still in use today. This was when we realized we had a chance to make a difference in the world using the same technology that was used by NASA, but applied in a remote area of a developing country.
We started M-Water for the biggest health crisis on the planet, which is a lack of safe water. The test kit is revolutionary because of its cost. It lowers the cost of testing water points from hundreds of dollars to about $5 to $7. It can be done on site in the remote region, and it can give you a result within 24 hours.
I take a sample today, tomorrow I have results. To use a M-Water kit is very easy.
But we learned that testing water by itself wasn't enough. With the mobile app, people could map water sources and record the data.
So that way we're building sort of a global database of water information that everybody can contribute to and share with others.
So what that meant was people who before didn't have a feasible and affordable way to test water suddenly had the means to know which water sources around them were safe.
It's made people much more aware of the issues of water quality. That's a very powerful thing.
And that's all due to technology that we've borrowed from the International Space Station. So now we're able to assemble a really low-cost water quality test kit to ship all over the world.
We've been working with the local health ministry and the water utility in Mwanza, Tanzania since 2013.
Through that technology, most of the citizens in Mwanza have an increased awareness regarding the kind of water they use and whether it causes them any waterborne illnesses or not.
People are now treating their water and avoiding sources of water which could be contaminated. I've seen a growing awareness.
It is very unusual for technology that is used in international space stations to be used in developing countries like Tanzania, but it can be used, and it should be used because this technology is not limited to only developed countries, but for all humankind.
The International Space Station is the most unique laboratory that exists. There are things that you can learn, things that you can do in space that you just can't do on the Earth.
Space Station really provides an opportunity to explore, for example, say medical applications.
The aging and the osteoporosis and muscle wasting conditions are greatly accelerated in microgravity.
Understanding those phenomena allow us to look at how we can improve treatment of disease here on Earth.
What we have is the capability to affect people's quality of life.
But it's not just drug companies that can benefit from experiments or research in space, but it's a host of industries across the board.
But it wasn't always easy to get there.
Historically, access to space was limited to companies and corporations which were selected by the government, and what we lost was the true creativity of so many innovative smaller companies that really didn't understand how to get to space.
When we were doing the reauthorization of NASA, we wanted to expand the opportunities to different areas of experimentation and also different entities.
Recognizing the untapped potential for commercial access to space, in 2005, Congress declared the U.S. portion of the International Space Station a national laboratory.
Essentially, it opened up opportunities for research that could be done on the space station that would benefit us here on Earth.
Everyday companies and everyday researchers and everyday people can think about using the space station. That's a fundamental change that was never allowed before.
Today, we offer opportunities to the researcher that never existed before.
Whether it be seed funding to help support the actual project,
to access to experts to create hardware,
that rocket ride up, the on-station time with the astronaut as your lab technician, what we're doing is really making it as easy as possible for people here on Earth to do space-based research without becoming space experts.
Our part of the mission is to help guide these non-traditional, innovative users from their traditional labs here on the ground to a very unusual and important asset in space. The ISS National Lab has space versions of hardware that you can often find in laboratories here on the ground.
Everything from even animal habitats,
plant growth chambers,
freezers,
3D printers,
Earth observation windows,
incubators,
furnaces,
the centrifuges,
microscopes.
The list goes on and on. So we're working with companies that you would never imagine, and they would never have imagined using the International Space Station, and they're seeing great results from that.
And the International Space Station offers researchers like me an opportunity to find the key variables.
It's helping us to pinpoint therapeutic molecules
The space station really provides us a unique opportunity, a unique environment to do some basic and fundamental research that allows us to develop products better.
The ISS allows us to do a series of experiments in weightlessness that will have profound impacts for life on Earth.
Having a U.S. national lab in space has allowed for the formation of a wide range of companies. It's creating a new economy, a sustainable marketplace that has services, commercial products, competition. There's no limit to what we can be doing in a few years.
One of the great powers of the International Space Station is its duration. The ability to do an experiment, take that knowledge, design a new experiment, follow on with that knowledge, and then do the next generation after that.
NASA's been launching vehicles for decades, and each one of those vehicles has an experiment on them. But never before have we had a laboratory totally dedicated to these kind of experiments.
One of the things that's most promising is that the scientific value and the economic value that will come from the space station research is just starting to show up.
The developments that we're making now are really setting the stage for this commercial market in space. The efforts that have led up to this through the performance of all of these research investigations that we've already had on board, doing foundational research and testing out new technologies and methods, feed this market and feed the capability of doing future research in space and also in having new commercial entities operate in that space.
We put together the ISS Benefits for Humanity book to really compile the stories that we knew of the amazing things that had been accomplished. The challenge with science is that it takes time. So even a new discovery that is clearly relevant to treating a medical condition could take decades for that treatment to actually come to market. And so we wanted to capture the state of those different new discoveries and how they were proceeding into benefits for humanity. But we also wanted to tell the stories of the people whose lives had already been changed.
We've put in specialized sections to both economic value and scientific value in order to try and demonstrate to folks what sort of value space station research has.
The scientific valuation section, we were interested in just saying, hey, we have all these publications, these scientific publications that come from ISS. What should we do with them? How should we communicate why they're important? Yeah, we've got thousands of publications, but what does it mean? And how has it advanced science as a whole for Earth and also for spaceflight? So what was shocking to me is, wow, look at all the publications that have come from space station research, and other people in non-space disciplines are finding those publications and using them in their own research. And where you can integrate space research into everyday research on Earth, you know you're having the most impact on science.
One thing we're adding is a lot more information about commercial development in low Earth orbit that is leveraging the space station.
The space economy today is still emerging, but its valuation has doubled in the last 10 years, and there are more active participants in low Earth orbit than there have ever been. The International Space Station has contributed to the commercialization in a couple of different ways. First, with commercial resupply, encouraging companies to develop their own capabilities, and then those capabilities can be used not just by the International Space Station. In terms of research, there are 12 commercial facilities that are operating right now, and they've greatly expanded the kinds of research that can be accomplished on ISS, and they're really bringing both new customers into the space market, but also they are allowing new entities to form that are learning the processes by which you conduct business in space.
Commercialization is key to the further exploration mission that NASA has. We intend to use space station to help commercial entities enter the market in low Earth orbit. And we also expect them to be able to provide goods and services that someday will help us in our exploration mission beyond low Earth orbit.
Scientists tend to ask, what's the next question? So the next question for Space Station is, what are we going to do next with this platform?
This is the golden age of research. We will likely never see such a strong microgravity science program in the future. We will have lots of human exploration, but to have a sustained laboratory in the way that we have now, now's the time.
This research is feeding our exploration goals beyond low Earth orbit and developing the companies that hope to make low Earth orbit part of their business plans. These two goals go hand in hand, and the International Space Station is the way to get there.
We really want to tell the stories of people and products and economic development, all of those things that are making the world a better place through our international cooperation on the space station.
In 1988, Dr. James Hansen, then director of NASA's Goddard Institute for Space Studies, stood before the U.S. Senate and testified that
global warming has reached a level such that we can ascribe with a high degree of confidence a cause and effect relationship between the greenhouse effect and observed warming. It is already happening now. This last year, 2021, comes in as the 6th warmest year on record, and it continues this large, long-term warming that Jim Hansen was detecting even in 1988. And in 1988, that was also a globally warmest year, but now that ranks only 28th in the ranking. And so the warming that we've had since Jim Hansen's testimony has been dramatic and totally vindicates the concern and the warnings that he put out at that time.
the Goddard Institute for Space Studies, or GISS for short, maintains NASA's record of Earth's surface temperature, called GISS temp, that shows a clear and unequivocal increase in our planet's temperature. GISS temp stretches from 1880, long before NASA existed, until the present day. Now, when you think of NASA, you probably think of, well, space, right? And we do lots of work studying Earth from above. But the GISS temp record is actually built from the ground up. We collect measurements taken from weather stations, Antarctic research stations, and ships and ocean buoys all around the planet to understand what temperature changes look like globally. And why does the record start in 1880? That's the earliest period that we have sufficiently reliable measurements from ships and weather stations in enough places to be confident in the global record. Interestingly, it's also shortly after the time we call the Industrial Revolution, when humans started putting significant amounts of carbon dioxide in the atmosphere. But we'll get back to that later.
There are millions of measurements over the last 140 odd years. We put those together. We're using data from literally tens of thousands of different stations around the world. We use the information that's there to create a global picture of what's happening, and that gives us a very accurate estimate of how any year ranks, or what the anomaly is for any one year compared to what happened in the 19th century or what happened in the middle of the 20th century.
So we have our statistical reconstruction of Earth's recent climate, but in research science, we like to check our work. There are a couple ways we can do this. First of all, teamwork. Our colleagues at NOAA and at other agencies and universities around the world also create their own records, and we can line them up side by side and see just how closely they align. Everyone's independent climate records show the same thing. Earth is warming significantly and rapidly. And here at NASA, we have an even cooler way to check our work: space. Right now, we have more than 24 satellites dedicated just to studying our planet. Satellites can take measurements of the entire planet and line them up with our estimate of global temperature change. And sure enough, they also match. Our measurements from space match up well with what our analysis tells us. Earth's climate is warming. The next big question: why is our planet warming? Well, let's jump back to the Industrial Revolution. The release of carbon, mostly carbon dioxide, from human activities like driving cars, flying planes, and industrial burning of fossil fuels is responsible for the majority of climate change. Carbon exists in stores underground as oil, gas, and coal. When we burn it, we release it into our atmosphere, where it traps excess heat coming from the sun, raising the temperature. We've known for more than a century that carbon dioxide added to our atmosphere traps additional heat and is a major contributor to the greenhouse effect. So we can also track the concentration of carbon dioxide in our atmosphere, the primary cause of the current climate change. Both from space, using NASA satellites like the orbiting Carbon Observatories 2 and 3, and from the ground. If you've heard of the Keeling curve, you're familiar with one of these records. Researchers have been taking daily measurements of atmospheric carbon dioxide from Mauna Loa, Hawaii since the 1950s. From space and the ground, the signal is clear. There's a lot more carbon in the atmosphere than there used to be. Other things have changed too. We've chopped down tropical forests, caused the ozone hole, and filled the air with soot, smog, and other kinds of air pollution. And this is on top of natural variations caused by the dynamics of the ocean, or volcanoes, or variations in the sun's activity. And so we can ask whether it's human activities warming our planet. At NASA, we have some big and powerful computers, able to make 6.8 trillion calculations per second. We put these huge supercomputers to work to recreate Earth's climate. So we have thousands of ideas of what could naturally cause climate change. We have 4 billion years of history where nearly anything and everything you could imagine has impacted Earth's climate. But each of these events has their own distinct fingerprint, which we can identify, a pattern of behavior with natural variability. Using supercomputers, we can run simulations of natural climate drivers, solar energy changes, wobbles in Earth's orbits, ocean turnover, volcanic eruptions, and we can run simulations of human effects. And what we've seen is...
It's us. There's no way around it. Looking at the evidence, we're the force that's enacting these changes. I am so proud of our ability to understand the climate, but I'm terrified of what we've found.
But it's not just the causes of climate change. It's also the effects. Because it's not just about knowing why our planet is warming. It's also about understanding and preparing for the effects of added warmth.
Measurement of global average temperatures is so important because it's one of the most direct indicators of Earth's changing climate. But the Earth is really a system of environmental systems: land, ocean, atmosphere, and ice, and changes in one system impact the others. Our oceans are our first line of defense in climate change because they absorb so much of the extra trapped energy in the Earth system.
We are seeing the impacts of climate change now. Now we know that as our climate warms, wet areas are getting wetter and dry areas are getting drier. For example, we see more intense snowstorms. We see slower hurricanes that are causing more precipitation that inundate land. And we have more extreme precipitation in the form of atmospheric rivers that come from the Pacific and reach our west coast.
The oceans are absorbing a large amount of heat because of climate change. And once that heat is in the ocean, it actually travels all around the planet because of the ocean currents. And that has impacts on local weather and long-term climate.
As the planet warms, it's not just the ocean that's warming, it's also the ice that sits in the ocean and on land. The ice on land being warmed increases melting, which is increasing freshwater input into the polar oceans and causing sea levels to rise across the globe.
So as the climate is changing, we really are seeing a lot of changes to the environment up in the Arctic. We're seeing more permafrost thaw when it's warmer up there. The warmer air temperature can lead to warmer ground temperature, and we get that thawing of that permafrost layer.
We're finding that the fire season is being exacerbated by longer periods of drought and decreased snowfall.
Knowing that our climate is changing due to human activities means that we know how to lessen the effects of future warming. And knowing how we know what causes climate change confirms that our efforts would be meaningful. The situation is serious, but it's not hopeless. Together, we can decide to make a better choice.
Mission and liftoff. Touchdown confirmed. Hello, United States.
To explore every phase of cosmic history.
En la NASA, nuestro recurso más importante es nuestra gente.
Una fuerza laboral talentosa, diversa,
dedicada a estudiar los secretos del universo y de nuestro planeta natal.
Para el beneficio de la humanidad.
La comunidad hispana contribuye a diario a misiones esenciales de la agencia.
Trabajando para mantener seguros a nuestros astronautas y misiones en órbita.
Monitoreando los efectos de cambios climáticos.
Prediciendo eventos meteorológicos que pueden afectar a nuestras comunidades.
Ayudando a la respuesta en desastres.
Diseñando los aviones de tecnología sostenible del futuro.
Desarrollando ciencia y tecnología a bordo de la Estación Espacial Internacional.
Desentrañando los orígenes del universo.
Buscando señales de vida antigua en otros planetas.
¡Hemos llegado! Perseverance llegó. Y preparándonos para llevar a la primera mujer y a la primera persona de color a la Luna.
Nuestra diversidad de orígenes y culturas impulsa nuestra capacidad para innovar.
Y hace que nuestra agencia sea más fuerte, incluyente y diversa.
Somos hispanos.
Somos hispanos.
Somos hispanos.
Somos hispanos.
Somos hispanos.
Somos NASA.
Sigue nuestras historias en NASA en español.
Of a new generation.
NASA researchers spend weeks, even months at a time, in remote locations around the world, collecting critical data about Earth's environment. Many studies are done from the air, using NASA's fleet of research aircraft. One such mission is Operation Icebridge, a multi-year study of polar ice conducted by the NASA Airborne Science Program. Icebridge sends NASA's P-3 flying laboratory to Greenland and Alaska in the spring to study changing ice conditions in the Arctic. A second aircraft, the NASA DC-8, flies from Punta Arenas in southern Chile in the fall to measure land and sea ice over Antarctica. It takes months of planning to execute a major international mission like Icebridge. Diplomatic clearances, configuring the aircraft with scientific instruments, and finding facilities that can support the people and the airplane itself are just some of the preparations needed for Icebridge to meet its mission requirements and goals.
To deploy to someplace like Chile, we plan a good 6 months before the mission to bring everything together so that once you arrive here, we're ready to execute missions on a daily basis.
Typically a mission director, a mission manager, program manager, we get called different names. We'll do the site surveys for the location, liaisoning with the government, of the host government to the host airport. That's the real legwork that's done prior, is coming out and making sure that they can house and feed us and take care of the people in the hotels. You name it. There's a lot of little tiny details that can't be overstated.
The biggest logistical challenge for the project as a whole is to set up all of the lab space and the facilities so that the scientists can process their data and make their decisions about which project.
Logistics is huge for something like this because we have to make sure we can all support the people in the field as well as the aircraft. So we think a lot about aircraft spares and then little details about the support equipment for the airplane.
Usually on every deployment we're going somewhere, there's at least a group that goes out and scopes it out. A lot of it's done like while we're working other missions. And they will talk with the airfield, set up and tell them what we're going to be doing. And then as they're communicating back with us with what capabilities the airfield has to support us, that way we know what to ship.
For a deployment more than 6,000 miles away in the southern hemisphere, the maintenance crew needs to carry an extensive payload to maintain the DC-8 on site and keep the mission on schedule.
Yeah, we put them right on the side there.
More than 13,000 pounds of cargo are packed on the DC-8. Everything from spare tires, parts, and tools to basic comforts of home for the near daily 11-hour research flights over Antarctica.
On a deployment like this, we bring the equipment with us, and we also ship a lot of other things by sea in a big container so that we can keep the airplane moving. It'll come back from a mission. If there's anything wrong that needs to be repaired before the next flight, we have the maintenance crew to support it during the night and get it ready for a mission the following day.
The DC-8 flight operations team works around the clock to support Operation Icebridge, providing ground support for takeoffs and landings, operating the plane on research flights, and making sure sensitive science instruments stay powered up and heated overnight. The airfield is staffed 24 hours a day.
We have a makeup of about 28 people supporting the flight operations down here, and that consists of the pilots, flight engineers, navigators, mission directors, and then the maintenance crew that's split between mechanics and avionics technicians.
The maintenance team often works on tight deadlines to prepare the aircraft for its next deployment. Just 10 days after removing one set of science instruments from a previous mission, the DC-8 is reconfigured for Icebridge. In 3 weeks' time, the plane is transformed into a working science laboratory with a suite of radar and laser instruments and cameras installed throughout the cabin, cargo pit, and fuselage.
Yeah, the unique thing about the DC-8 is that it was modified to accept, at this point, we've got about 100 different instruments that have been integrated into this airframe. And so part of the modifications that were done early on was to make the airplane as versatile as possible. So if you were to look through the airframe, you'd see cutouts in both the bottom of the aircraft and the upper side of the aircraft. And a number of the windows were modified to carry structural loads of instruments being installed as well. So we can look in pretty much every direction there is outside this airplane as we're traveling through the sky.
Once the science instruments are installed, the flight operations team conducts a series of ground checks and instrument test flights over the California desert to make sure the DC-8 is mission ready.
Looks like maybe it's level now. Right, looks like it's a wings level and rock course.
So the reason why we picked these sites over the desert in California is because they have these dry lake beds there, and they are a very flat area that's ideally suited for our purpose. So we can put a GPS receiver on a car and kind of drive around on these flat lake beds, measure them, and then a few days later fly over the same area with the DC-8 and take a measurement from the air, compare the two measurements and use the data from the ground to calibrate and validate the airborne measurements.
While the aircraft is prepared for the trip to Chile, the science and flight operations teams are required to undergo specialized safety training, regardless of if they've flown on the DC-8 in the past.
Well, for the DC-8, everybody who flies has to go through basically a safety briefing. We go in a little bit more detail because we do more things on our airplanes than commercial airliners do. From our pilots, they go through survival training, water and land, and depending on where they're going, some of them have been through Arctic. All of our crew members, they all have to go to altitude chamber, water survival, land survival, and what we do here is we just build on that and then try and bring anybody else that hasn't had any formal training up to speed so they have at least a working knowledge of the kind of conditions that can happen if something was to go wrong with the aircraft.
Safety equipment tailored for Ice Bridge is also packed on the DC-8.
Overhead compartments, we've got 20-man life rafts. There's 4 of those on board the aircraft. We have 2 what we call global survival kits, which has different survival items inside of there. For this particular deployment, we also have anti-exposure suits, which if they were go into the water, we have enough for everybody on board the aircraft for that.
Once the aircraft and passengers are cleared to fly, it's time to pack up for the long transit flight from Armstrong Flight Research Center in California to the southern tip of Chile. The exhausted team gets an opportunity to rest on the overnight journey to Santiago, where a second flight crew is on standby to complete the journey to Punta Arenas.
To get to this part of the globe, it's about 14 hours of flying. We had pre-deployed a crew to Santiago to join the flight at that point so that the crew that flew all night could then step out of the cockpit and rest. And that allowed us to continue on that next day down to Punta Arenas, Chile, without having to stop overnight.
It's a cold and windy welcome at the Punta Arenas Airport, the mission base for Operation Ice Bridge. The scientists and flight crew will call this place home until the end of November.
We are setting up base stations here at the airport that record the GPS data for various instruments. We're talking to people in the weather office, at the tower, the air traffic controllers, and that typically takes about a day, getting everybody settled in here and preparing everything for the first science flight.
With 2 complete flight crews available, science flights are planned on consecutive days to collect as much data as possible over Antarctica.
On a typical Punta Arenas deployment, we have about 300 flight hours, and if we fly as much as we can, which we typically do, we kind of travel a distance in Antarctica that's equivalent to 3 or 4 times around the equator.
I think this is a glacier we're crossing.
Flight tracks are carefully designed by the Ice Bridge science team months in advance. Survey lines need to be precise, not only to make repeat measurements in exact locations, but also to ensure the plane keeps a safe distance from specially protected areas and animal habitats. A sophisticated guidance system on the DC-8 helps the flight crew keep the plane on track and navigate around more than 1,700 known wildlife locations on the Antarctic continent.
Some of the flights are hand-flown using moving map displays that have a flight track depicted on them. Others are guided by what's called the ATM instrument, where it actually puts out a signal that we feed into the aircraft navigation system, where it guides the airplane laterally.
So the ATM stands for Airborne Topographic Mapper. We designed a supplemental system to the ATM. Some people call it the ATM Navigator. What it does is it couples into the aircraft's own autopilot and helps it to steer the aircraft as accurate as we need it to be. We can generally steer the airplane well within 100 feet and often within 20 feet of where we want it to be. And that means that if you imagine a line that represents our desired track, more than half the time that line will lie within the cabin of the aircraft. We're crossing.
Antarctica's harsh and often unpredictable weather determines when and where the Ice Bridge team will fly each day.
I've got rising terrain, 12 o'clock, 7 miles.
Tally-ho.
Tally-ho, and I'm going to start climbing here.
Pilots need perfect visibility of the terrain for safety.
We'll clear it. It does get steeper as we get closer to it, so we can pitch up a little bit.
Several science instruments need a clear line of sight between the aircraft and the ground to collect proper measurements.
Meteorology is obviously a very big deal with Ice Bridge. It essentially governs everything that we do on any given day. We have to fly down low and near the terrain in order for our instruments to work as they're optimally designed to work. So it means we need clear skies below the altitude at which we're operating in order to do this kind of work. We know from experience which parts of Antarctica are likely to have good weather and which parts are not. So we designed the missions so that each of the missions has a maximum chance of success based on the likely weather scenarios.
We come up with about twice as many mission plans as we can possibly fly in the field, and that's simply so that we have enough target areas to choose from that have good weather while we are here in the field, and then we prioritize these plans.
We have to spend a very large amount of our time while we're in the field trying to sort of ascertain what the weather is going to do. It's a bit like reading tea leaves. It's a very inexact science. We depend entirely on what the meteorologists tell us through computer models. We talk a lot to the meteorologists here at the airport. They're terrific. They give us a lot of help.
The Chilean hosts provide everything from weather expertise to daily flight lunches for the Icebridge team. Airport firefighters and emergency responders are also prepared to help in case anything goes wrong with the aircraft.
So we don't use retread tires.
The DC-8 is not your typical airplane. Structural enhancements, new engines, and cutting-edge data systems make the aircraft a versatile, long-endurance platform for earth science research.
The DC-8 is uniquely capable for this kind of operation, mainly because of its long legs. It can fly for about 14 hours on a full fuel load.
We have to pretty much commute every day to Antarctica and commute back. And then we need also the capability of collect several hours of data. Typically on every flight we collect several terabytes of data all together. So we have 8 different science instruments on the aircraft. And in total it's a very complex set of measurements that we take over ice sheets, and doing it all at the same time in the same location from one airplane. It's really a tremendous resource.
It is amazing that a large airplane that was designed originally to be an airliner could be so diverse, but by its design it meets a lot of the requirements NASA had set for the type of science studies they wanted to execute using an airplane to support. This particular airplane was built in 1969, but many of the systems have been upgraded over the years to keep up with current technology. For instance, the airplane has a satellite communication system on it, which something like that didn't even exist when it was originally built. So what's nice about that is we can move data real time during the flights off the airplane to people anywhere in the world via the satellite system and then the internet, and they can send us information real time as well. We can X-chat, it's like texting back and forth to each other. We can send photographs, we can send technical data. You don't have to actually be on the flight to participate.
My view of this airplane is that it's the ideal airplane for the kind of mission we use it for, because it's built very strong. And in the old days when these were being designed and built, the airplanes were overbuilt to be on the safe side. We have a nickname for it. It's a DC-8, and the DC stands for Douglas Cable Car, because unlike the modern airplanes that use electronics and hydraulics to control the airplane in flight, this airplane is controlled with steel cables. So we do hurricane research, we fly through hurricanes, and we do a lot of different types of scientific research, and the airplane can take a lot of damage that would cripple other more modern airplanes, and this airplane still flies fine. It's like an old truck. It's solid and almost indestructible.
A wall of stickers at the mission director's console tells the story of the many missions the DC-8 has flown since it went into NASA's service in 1987. This aircraft and many others operated by the NASA Airborne Science Program fly thousands of hours every year all over the world to support a variety of Earth science research missions. It takes careful coordination and detailed planning behind the scenes to make these missions possible and to gain a better understanding of how our planet is changing.
In 1988, Dr. James Hansen, then director of NASA's Goddard Institute for Space Studies, stood before the US Senate and testified that
global warming has reached a level such that we can ascribe with a high degree of confidence a cause and effect relationship between the greenhouse effect and observed warming. It is already happening now. This last year, 2021, comes in as the 6th warmest year on record, and it continues this large, long-term warming that Jim Hansen was detecting even in 1988. And in 1988, that was also a globally warmest year, but now that ranks only 28th in the ranking. And so the warming that we've had since Jim Hansen's testimony has been dramatic and totally vindicates the concern and the warnings that he put out at that time.
the Goddard Institute for Space Studies, or GISS for short, maintains NASA's record of Earth's surface temperature, called GISS temp, that shows a clear and unequivocal increase in our planet's temperature. GISS temp stretches from 1880, long before NASA existed, until the present day. Now, when you think of NASA, you probably think of, well, space, right? And we do lots of work studying Earth from above. But the GISS temp record is actually built from the ground up. We collect measurements taken from weather stations, Antarctic research stations, and ships and ocean buoys all around the planet to understand what temperature changes look like globally. And why does the record start in 1880? That's the earliest period that we have sufficiently reliable measurements from ships and weather stations in enough places to be confident in the global record. Interestingly, it's also shortly after the time we call the Industrial Revolution, when humans started putting significant amounts of carbon dioxide in the atmosphere. But we'll get back to that later.
There are millions of measurements over the last 140 odd years. We put those together. We're using data from literally tens of thousands of different stations around the world. We use the information that's there to create a global picture of what's happening, and that gives us a very accurate estimate of how any year ranks, or what the anomaly is for any one year compared to what happened in the 19th century or what happened in the middle of the 20th century.
So we have our statistical reconstruction of Earth's recent climate, but in research science, we like to check our work. There are a couple ways we can do this. First of all, teamwork. Our colleagues at NOAA and at other agencies and universities around the world also create their own records, and we can line them up side by side and see just how closely they align. Everyone's independent climate records show the same thing. Earth is warming significantly and rapidly. And here at NASA, we have an even cooler way to check our work: space. Right now, we have more than 24 satellites dedicated just to studying our planet. Satellites can take measurements of the entire planet and line them up with our estimate of global temperature change. And sure enough, they also match. Our measurements from space match up well with what our analysis tells us. Earth's climate is warming. The next big question: why is our planet warming? Well, let's jump back to the Industrial Revolution. The release of carbon, mostly carbon dioxide, from human activities like driving cars, flying planes, and industrial burning of fossil fuels is responsible for the majority of climate change. Carbon exists in stores underground as oil, gas, and coal. When we burn it, we release it into our atmosphere, where it traps excess heat coming from the sun, raising the temperature. We've known for more than a century that carbon dioxide added to our atmosphere traps additional heat and is a major contributor to the greenhouse effect. So we can also track the concentration of carbon dioxide in our atmosphere, the primary cause of the current climate change. Both from space, using NASA satellites like the orbiting Carbon Observatories 2 and 3, and from the ground. If you've heard of the Keeling curve, you're familiar with one of these records. Researchers have been taking daily measurements of atmospheric carbon dioxide from Mauna Loa, Hawaii since the 1950s. From space and the ground, the signal is clear. There's a lot more carbon in the atmosphere than there used to be. Other things have changed too. We've chopped down tropical forests, caused the ozone hole, and filled the air with soot, smog, and other kinds of air pollution. And this is on top of natural variations caused by the dynamics of the ocean, or volcanoes, or variations in the sun's activity. And so we can ask whether it's human activities warming our planet. At NASA, we have some big and powerful computers, able to make 6.8 trillion calculations per second. We put these huge supercomputers to work to recreate Earth's climate. So we have thousands of ideas of what could naturally cause climate change. We have 4 billion years of history where nearly anything and everything you could imagine has impacted Earth's climate. But each of these events has their own distinct fingerprint, which we can identify, a pattern of behavior with natural variability. Using supercomputers, we can run simulations of natural climate drivers, solar energy changes, wobbles in Earth's orbits, ocean turnover, volcanic eruptions, and we can run simulations of human effects. And what we've seen is...
It's us. There's no way around it. Looking at the evidence, we're the force that's enacting these changes. I am so proud of our ability to understand the climate, but I'm terrified of what we found.
But it's not just the causes of climate change, it's also the effects. Because it's not just about knowing why our planet is warming. It's also about understanding and preparing for the effects of added warmth.
Measurement of global average temperatures is so important because it's one of the most direct indicators of Earth's changing climate. But the Earth is really a system of environmental systems: land, ocean, atmosphere, and ice. And changes in one system impact the others. Our oceans are our first line of defense in climate change because they absorb so much of the extra trapped energy in the Earth system.
We are seeing the impacts of climate change now. Now we know that as our climate warms, wet areas are getting wetter and dry areas are getting drier. For example, we see more intense snowstorms. We see slower hurricanes that are causing more precipitation that inundate land. And we have more extreme precipitation in the form of atmospheric rivers that come from the Pacific and reach our west coast.
The oceans are absorbing a large amount of heat because of climate change. And once that heat is in the ocean, it actually travels all around the planet because of the ocean currents. And that has impacts on local weather and long-term climate.
As the planet warms, it's not just the ocean that's warming, it's also the ice that sits in the ocean and on land. The ice on land being warmed increases melting, which is increasing freshwater input into the polar oceans and causing sea levels to rise across the globe.
So as the climate is changing, we really are seeing a lot of changes to the environment up in the Arctic. We're seeing more permafrost thaw when it's warmer up there. The warmer air temperature can lead to warmer ground temperature, and we get that thawing of that permafrost layer.
We're finding that the fire season is being exacerbated by longer periods of drought and decreased snowfall.
Knowing that our climate is changing due to human activities means that we know how to lessen the effects of future warming. And knowing how we know what causes climate change confirms that our efforts would be meaningful. The situation is serious, but it's not hopeless. Together, we can decide to make a better choice.
Wherever, however, whenever. We're here, there. We're everywhere. NASA Space Communications and Navigation. Exploration enabled.
Antarctica. It is the world's coldest continent. Scattered among the ice in this harsh and unforgiving environment are numerous research stations. One of these is the Neumayer 3 station. Situated on the Ekstrom ice shelf and operated by the Alfred Wegener Institute, which coordinates German polar research efforts. Nearby Neumayer 3 is a small greenhouse, the German Aerospace Center's Eden ISS, which is working on developing innovations for cultivating food using closed-loop systems. In a space about the size of an apartment bedroom, this greenhouse recently grew more than 600 pounds of fresh food, including cucumbers lettuce, and tomatoes in a 9.5-month period, even with outside temperatures well below freezing. The researchers took scientific samples from their crops, but they ate the vast majority of what they grew in a powerful demonstration of the benefits of closed-loop agriculture. This research not only benefits indoor agriculture here on Earth, it also has applications for space exploration. For more than 20 years, people have continuously occupied the International Space Station, a laboratory about the size of a 6-bedroom house that orbits the Earth every 90 minutes at an average altitude of approximately 250 miles. Astronauts working with researchers on the ground have used the space station as a proving ground for the technologies and know-how that will allow people to explore more of the moon than ever before and take the next step in space exploration, a crewed mission to Mars. Jess Bunchek is a plant scientist from Kennedy Space Center, NASA's leading center for growing plants in space. The agency is sending her to work with the German Aerospace Center on research that could one day help feed crews on long-duration missions to the Moon and Mars. Bunchek brings important experience to Eden ISS. Knowledge gained from working with astronauts growing salad crops in space. After a month-long voyage from Germany, Bunchek will spend about a year in Antarctica. There, she will work with a team of researchers connected to the Mission Control Center in Bremen, Germany, to solve challenges with closed-loop agriculture so that it can be robust and productive enough to help sustain astronauts on a 2 to 3 year long mission to Mars.
Of a new generation.
Tropical regions are among the hottest and most humid places on Earth, but also the coldest and driest. Yep, you heard right. While temperatures on the surface can range from 80 to 90 degrees Fahrenheit all year round, they can dramatically drop as you go up in altitude. In fact, as you get closer to the stratosphere, they can be as low as minus 110 degrees Fahrenheit. This extremely cold region between the troposphere and the stratosphere is called the tropical tropopause layer.
In the tropics, it's very warm and moist down here at the surface. When you get up to the tropopause layer, it's very cold and dry.
So it turns out that the tropopause is actually coldest in the western Pacific.
Right above Guam is an ideal place because it is the coldest and the driest part of the tropics.
everything is ready for the second phase of the field experiment. We are 13 degrees north of the equator in the Pacific, our new home away from home for the next several weeks. We are in Guam.
So the tropics are the part of the planet that gets the warmest from the heating from the sun because it gets the most sunlight on average.
Because the surface is so warm and there's so much water, you evaporate water, liquid water becomes a vapor, so you have this very hot, moist air down here at the surface. So this is air that's got a lot of energy. And just like a boiling pot of water, it can rise very high.
And it tends to pull other gases that come from the surface up with it. So this is the part of the world where most of the circulation getting up from the surface up into the upper part of the troposphere and into the stratosphere, this is where it occurs.
So here in the tropics, we see these thunderstorms boiling up to very, very high altitudes. And so we have a very high elevated tropopause here in the tropics.
As you get convective processes going, the air rises. As you know, if you take air and you expand it, it cools really fast.
And it turns out that, in fact, the warmest places in the world are in the tropics, but about 55,000 feet above us, about 16 kilometers, is one of the coldest places on Earth.
So what that does is, as it cools really fast, all that water vapor in the air going up gets squeezed out. It's like wringing a towel, and all the water starts to squeeze out. So you get cloud processes formed, it squeezes out the water. The air that comes out the top tends to be dry.
You still get some water making it up to the tropical tropopause, and there the atmospheric motions transport air into the stratosphere. So air is transported into the stratosphere with a small amount of water that's left behind.
And this is the area that tends to be the controlling mechanism for how much water gets into the upper troposphere and then onto the stratosphere.
So if you want to understand the composition of the stratosphere, how much water there is, how much ozone-destroying substances or trace gases there are, you need to go to the tropics and study the region around the troposphere and the tropics.
So this is the spot to be. So this is the area where the ocean gets the warmest, the convection is the strongest, and then the air that comes out the top gets the coldest.
And we've known that for many decades, and for at least 20 years we've known we really need to go to the Western Pacific to study the extreme dehydration where the tropopause is coldest and where the most extreme dehydration to low water vapor concentrations occurs.
Now, Guam is the coldest and driest part of the tropics.
It's actually a warm region at the surface and a cold region at the tropopause. And Guam is right in the center of action. Plus it has the airfields and facilities we need to operate our high altitude aircraft.
It takes a lot of work to plan a remote deployment of this size.
Yeah, preparing for a mission where we're deployed, where we have to take the entire team and the aircraft and all of our equipment is really quite an effort.
Making sure we had a hangar available to us, making sure we had office space available, making sure that we had areas that we could set up our aircraft control trailer and our instrument control trailer.
It's also difficult because you're away from where you built your instruments, where you operate your aircraft. So if you have a problem, you have to ship everything here.
Because when you're this far from home, so to speak, you know, you got to have everything here, not just the airplane and the people, but all your equipment, including spares.
Actually, All the work that's gone into this Atrix project has been one of the most difficult things I've ever done.
So when we operate out of Edwards Air Force Base, we operate from a fixed structure called the Global Hawk Operations Center. That's the main command and control center for the NASA Global Hawks.
Well, what's different from operating here in Guam versus operating back at Edwards is we have these mobile ground stations. So that's where we fly the airplane and operate our payloads from.
So the front room, the flight operations room, is replicated with a 40-foot trailer with all the communications equipment, all the computers, all the servers, everything. And then we have another trailer that replicates the 14 workstations that the payload operations room has, and that's in another trailer.
And we're basically providing the same functionality from Anderson Air Force Base in a forward location that we would have back at Edwards Air Force Base.
We can deploy anywhere in the world with these trailers as long as we have the appropriate setup.
And that's 872 BTC, show 4, ready, links now.
Okay, that sounds like a good plan. So we're ready for airplane taxi.
For the Atrix campaign, the NASA Global Hawk is basing out of Anderson Air Force Base. And from Anderson Air Force Base, we'll be flying north all the way up to the Aleutians, east towards the Philippines, south down by Australia and New Zealand, and out to the east all the way to about Tahiti, the other side of Hawaii, basically. It's roughly about a 4,000 mile radius of range that the Global Hawk has here from here at Anderson Air Force Base.
We really have daily meetings. I know certainly the forecasters, the modeling group, and our pilots meet almost every day whenever we're getting ready for a flight. We are working every day on the aircraft, working with the scientists. They've got to pre-flight their instruments. After flight, they've got to post-flight their instruments. Some want to come off, some don't want to come off. So it's a constant ballet of activity around the airplane in between flights until the day when we're ready to go. Everyone comes on. We'll have engine start at 5 o'clock, which means they've got to come in at 11 o'clock at night, work till 2 a.m., do their thing with the instruments. Then our crew comes in, buttons up the jet. It's rolling out at 4 o'clock. Engine start at 5, take off at 6. So it's an ensemble of people all doing really great work together to make this whole thing happen.
And that's 872, we have a good power transition, good engine start.
And Trapper, can I get a takeoff report?
Yes, sir. Runway's clear. You're going for takeoff.
Roger that.
So the Global Hawk has great capability with tremendous range and endurance.
So many lessons learned from this campaign that will make our Global Hawk operation a much more globally deployable package.
And as we've demonstrated, we can do a lot of science from Dryden, California, or we can deploy, as we've illustrated here, to reach out. And I think we've shown now that we can really go almost anywhere in the world.
Because this is our first deployment away, really away from the mainland. This will be our first, it won't be our last, and we will be well suited to take our show on the road anywhere in the world from now on.
We're collecting data over the tropical Western Pacific, data that will improve our understanding of our atmosphere, weather, and climate. The Atrix mission will help us better comprehend the world we live in, to learn more about this planet we call home. Throughout many field campaigns, we've come a long way in expanding our knowledge and understanding of our atmosphere. But this hasn't been a one-person effort. Collaboration and close coordination within the Atrix team have made this endeavor possible.
For any field experiments you do, you have the questions that you're trying to answer, and then you figure out which data do you need to best answer the questions. Once you've done that, then you figure out who has the capability of making those measurements.
So basically what we've done is gathered the leading experts in theory, modeling of the atmosphere, and in making these very challenging measurements.
And that's the only way that you can really do science. You have to go to the right place and measure at the right time with the right people.
And part of the reason I really like these airborne science campaigns is they're sort of these grand endeavors where everybody comes out to the field, we're all working very hard with a common goal, and very thankful to have the opportunity to get these measurements. The other thing about these NASA campaigns is the data will then be shared with everybody. So it'll be used by people from all different countries.
The more people who use the data, the more of an impact our data have.
We're all basically working together, trying to understand how the atmosphere works.
The data we have gathered will be used to benefit humanity for many years to come.
When you make an observation, that's only the beginning of the story. It's like walking into a crime scene and taking a picture and collecting some evidence. Footwork begins after that, the real work of putting everything together to produce a full picture of what's happening in our atmosphere.
And Atrix is basically part of that puzzle. We're addressing a key uncertainty in how the models predict future climate change.
We have to actually figure out how all of these things work.
So the real underlying objective of Atrix is to understand climate change. Now, it's well known that climate change will have dramatic effects on people and ecosystems across the planet.
The atmosphere is always changing. Levels of gases are changing, temperatures are changing, and you have to make very precise measurements in order to try to see those changes.
So when satellites measure, they measure basically looking through the atmosphere over a very long path length, multiple hundreds of kilometers they're averaging the data over. So if you have low water and somewhat higher water, what you're going to measure there is the average. When the airplane flies through these air masses, they're measuring over tens and 20 meters at a time, so they're getting that entire variability.
So far, we've gathered these fine structure measurements of clouds and water vapor and the interaction between water vapor and clouds, and that's being used to better understand how the clouds form and how they affect the amount of water that's getting in the stratosphere. The other thing we've done is we've gotten a lot of measurements of these ozone-destroying substances in the tropical tropopause layer, which will ultimately get into the stratosphere, so we can better predict how much of these get into the stratosphere and again improve predictions of ozone destruction and the ozone layer recovery.
All of these processes are the things that we're after with Atrix.
15 seconds, one pass. SA-72 is off. Right. SA-72 switches 6.
The Atrix mission, we've seen some very, very interesting relationships between temperature, water, and particles that we're seeing in the atmosphere. This is really wonderful information and will be incredibly useful for how we can improve our modeling of the atmosphere.
But anytime you do climate science can be contentious in many parts of the world. So having data that is out there, free and open and defendable is important. If your data aren't available for everybody, it's always going to be in question.
The way we look at it from the science community is that the data is all shared. So it'll be shared amongst different institutions and different agencies and even different countries all around the world. Because we all have the common goal of trying to understand how the atmosphere is working and how the atmosphere is changing.
The scientists' understanding of the climate system and answering the key questions that can help resolve the uncertainties that decision makers have to make. It's key.
And so we'll still need measurements, and the measurements will improve and our understanding will improve, but we'll need these measurements to further quantify how the atmosphere is changing.
The more we understand the processes, the better off society will be because of it. And some of those key processes, the only way you're going to answer them are through airborne campaigns like the one we're doing here.
Our future very much depends on the understanding of the world around us, on how this complex system we call Earth changes. That's why our mission is not only about doing research, but also about encouraging younger generations. They are the future of science and the key to continue understanding and improving the lives of all of us who call this planet home.
The students do not normally have an opportunity to see this.
To show them that there's actually stuff beyond just looking at what's in a book is very invaluable.
It gives them meaning and relevance to the work that they do in school.
I can't stress it enough just how important it is for the students to make that connection, because that's where they make their decision as to what they're going to do for the rest of their life.
It's fantastic to have real scientists, real pilots, real engineers and technicians coming in and sharing their experiences with the kids, because that brings science to life.
So we are bringing our science into their classrooms, as well as bringing the students here to see our science in action. And we're hoping that this will inspire some of the students to pursue careers in science, technology, engineering, or math, and one day maybe even work for NASA.
I saw how excited the kids were, so it's awesome.
Record the GDC line.
Motion power, go, Frank.
Roger, power.
S1C press complete, Frank.
Roger, go. Good. 30 seconds. Recorder at flight speed.
Minus 20 seconds.
Minus 20.
Nice release, are you ready?
Ready, minus 10. Mark. 9. Starting mission. Flame burned. Engine arm. 5, 4, 3, 2, 1. All engines running. Launch commit. Okay, right on it. Launch start, right. Hold down.
So on December 24th, 1968, astronaut William Anders took a picture of the Earth. He was in Apollo 8 and he was orbiting the moon, and he took a picture of the Earth, what's called the Earthrise picture.
Oh my God, look at that picture over there. There's the Earth coming up. Wow, that's great. Oh, I got it right. Oh, that's a beautiful shot.
And you look at that and the vastness of space with this gray moon, and you realize what a unique thing the Earth really is. And the Earth doesn't come with an owner's manual. It's for us to try to figure out all of the complexity that we see here.
Our campaign is coming to an end, but new ones will continue exploring, making new discoveries.
Clean release, subjects come right to north.
Our journey is not over. Keep watching. This is just the end of a new beginning.
All 50 years ago, we pioneered a path to the moon. A trail we blazed, cut through the fictions of science, and showed us all what was possible.
It's very pretty out here.
Today, our calling to explore is even greater. To go farther, we must be able to sustain missions of greater distance and duration. We must use the resources we find at our destinations. We must overcome radiation, isolation, gravity, and extreme environments like never before. These are the challenges we face to push the bounds of humanity. We're going to the moon to stay by 2024, and this is how.
This all starts with the ability to get larger, heavier payloads off-planet and beyond Earth's gravity.
For this, we designed an entirely new rocket.
The Space Launch System. SLS will be the most powerful rocket ever developed.
And with components in production
and more in testing,
this system is capable of being the catalyst for deep space missions.
We need a capsule
that can support humans from launch
through deep space and return safely back to Earth.
For this, we've built Orion.
This is NASA's next generation human space capsule.
Using data from lunar orbiters that continue to reveal the moon's hazards and resources,
we're currently developing an entirely new approach to landing and operating on the moon.
Using our commercial partners to deliver science instruments and robotics to the surface, we are paving the way for human missions in 2024.
Our charge is to go quickly and to stay, to press our collective efforts forward with a fervor that will see us return to the moon in a manner that is wholly different than 50 years ago.
We want lunar landers that are reusable,
that can land anywhere on the lunar surface.
The simplest way to do so is to give them a platform in orbit around the moon from which to transition.
An orbiting platform to host deep space experiments and be a waypoint for human capsules. We call this lunar outpost Gateway.
The beauty of the Gateway is that it can be moved between orbits.
It will balance between the Earth and Moon's gravity,
in a position that is ideal for launching even deeper space missions.
In 2009, we learned that the moon contains millions of tons of water ice.
This ice can be extracted and purified for water. It can be separated in oxygen for breathing or hydrogen for rocket fuel.
The moon is quite uniquely suited
to prepare us and propel us to Mars and beyond.
This is what we are building.
This is what we're training for.
This we can replicate throughout the solar system.
This is the next chapter of human space exploration.
Humans are the most fragile element of this entire endeavor, and yet we go for humanity. We go to the moon and on to Mars to seek knowledge and understanding and to share it with all. We go knowing our efforts will create opportunities that cannot be foreseen. We go because we are destined to explore and see it with our own eyes. We turn towards the moon now, not as a conclusion, but as preparation, as a checkpoint toward all that lies beyond. Our greatest adventures remain ahead of us. We are going.
We're going.
We are going.
We are going.
We're going.
I'm Larry Clyett, and I am the technical lead for the acoustic validation phase of the Quest mission. During the acoustic validation phase of the mission, that's where we will measure the sonic thump and make sure it's as quiet as we designed the airplane to be. We'll do that a number of ways. We'll do that on the ground with a lot of sensors scattered throughout the desert. And we'll do that in the air too with some airborne systems that have recording devices that can measure the sonic thump of the airplane. So I love to cook. It's probably my #1 hobby. I like trying new concepts, new ways to cook. I like making Asian foods, just Asian-inspired cuisines, whether it's Chinese, Japanese. I love making Thai food. I love to barbecue, and I think a big part of my love to barbecue and to smoke different foods is the method behind it. I mean, it's a process. I've loved Legos since I was a kid, and then I think only maybe 4 or 5 years ago I discovered that Legos can be for adults. And part of it is a little bit of escape. Everybody needs a hobby to get away from the demanding job, but a lot of it is just continuing on that creative mindset into our daily personal lives, I think, as well. The Quest mission is not just 4 or 5 years old. It's 5 or 6 decades where NASA has been investigating the ability to quietly perform supersonic commercial transportation, to be able to go from point A to point B faster. It's a very big collective effort across the mission and across many NASA centers to make that happen. And so that's what really excites me about all this.
The imagination of a new generation.
Have you ever considered how big breakthroughs in science, engineering, and medicine occur? The popular misconception of how a breakthrough happens is perhaps a eureka moment while working on a project, and in that instant, the next big thing is born. Although that may happen sometimes, the truth is that most big breakthroughs are not eureka moments at all, but actually take years of painstaking work, trial and error, and rigorous testing before the finished product is ever realized. Researchers in the world of engineering and science almost always move in small, incremental steps, slowly building the case for these new revelations until they are sure the research is ready to be shared with the world. Then, and only then, is when we in the general public hear about it. Although it may not be quite analogous, just think about the moon landing as an example of this phenomenon. Most of us are familiar with Neil Armstrong's famous words when he first stepped onto the moon.
That's one small step for man, one giant leap for mankind.
For those watching it, that moment may forever be viewed as perhaps the most tremendous scientific and engineering breakthrough in the history of the world. Clearly, that event was enormously important for many reasons, but that first step on the moon was actually the culmination of millions of smaller incremental steps from tens of thousands of others that allowed it to take place. This basic idea is true for all scientific study. Researchers and engineers generally take an idea and meticulously study it to make sure that all bases are covered before new technology reaches the general public. NASA's Environmentally Responsible Aviation Project team members are following that same philosophy as well. This team has been working for years to find ways to reduce aircraft drag, aircraft weight, fuel consumption, engine emissions, and aircraft noise. In order to achieve these lofty goals, the team did, in fact, take incremental steps to make sure each project was viable. Now, toward the end of the ERA project, the team is ready to take the lessons learned from the smaller tests and begin putting all the pieces together, preparing to show the world the next big thing in aeronautics. NASA X has been at the forefront of the ERA program since its inception. This 6-year endeavor has progressed from innovative ideas to multiple designs, wind tunnel tests, and actual flight hardware. And the aerospace industry has taken notice that these technologies are ready to dramatically improve aircraft efficiency. Part 1 of this episode of NASA X looks back at some of ERA's earlier tests to see how those early successes and failures paved the way to the larger, more advanced tests of today. And we will see what the future holds for many of the ideas and technologies that have been developed by some of NASA's best and brightest engineers and researchers. When the Environmentally Responsible Aviation Project was first implemented, it was clear the stated goals would be hard to reach. The team was tasked to reduce aircraft drag by 8%, reduce aircraft weight by 10%, reduce fuel consumption by 15%, reduce emissions by 75%, and reduce overall aircraft noise by 75%, all by the year 2025. Compounding the difficulty of making such dramatic improvements was the fact that many in the aviation industry believed that the modern tube and wing-shaped aircraft had reached its maximum ceiling on efficiency. When NASA first undertook this challenge, they realized they would have to bring an A-team of NASA engineers from numerous NASA field centers, along with highly skilled teams from industry and academia, in an effort to find these new efficiencies.
We've got new airframes, 8 different technologies that we've worked in Phase 2, a myriad of 60-something technologies we worked in Phase 1 and we looked at. And we will be delivering at the end of this year technologies that say we can meet all of those goals. So it is an unmitigated success, and every one of our partners in this is getting something out of it.
Some of the major areas of study for the team included looking at engine redesigns, airframe redesigns, materials testing, and even developing new aircraft that integrate the wings into the aircraft body to increase efficiency. This unique design is called the HWB, or Hybrid Wing Body Aircraft. The HWB began its life as a series of computer models and then was upgraded to sophisticated wind tunnel models. Once the team was satisfied the HWB concept showed significant promise, it was upgraded to a flying scale model aircraft. 122 times the hybrid wing body models flew over the dry lake bed in California, where so many previous X-planes had flown before. And with each flight, the engineering data helped validate this unique type of aircraft design. Researchers feel confident that the strides they have made in this aircraft design will pay huge dividends in the future. Just watching footage of early aircraft shows how far we've come in only 100 years. As an example, most early planes were made out of wood and canvas, but as planes became more powerful and efficient, materials began to change. Today, we're aware that most planes are made out of lightweight aluminum skins, but the industry is moving toward the use of composite materials now as well. In fact, the Boeing 787 was the first all-composite airplane ever produced, and it took its first commercial flight on October 6, 2011. Although this plane is state-of-the-art, NASA's ERA planners believe that they can improve the strength of composites while making them safer as well. The idea they're investigating is called Perseus, or Pultruded Rod Stitched Efficient Unitized Structure. Early testing began with small pieces called coupons. They were developed to a point where researchers believed they could be tested on a larger scale. NASA's team built larger test sections and eventually brought them to this lab for stress testing. With this test, designed to bring the article to failure mode, the team applied pressure until the piece snapped. The data was used to further validate Perseus, and now the team has decided to build and break a nearly full-scale piece of Perseus material.
NASA and Boeing have been working together for quite a few years developing lightweight structure for commercial transport aircraft. What we're seeing today is the final piece of a project called Damage Arresting Composites, where we're trying to develop a new structural concept that will be applicable to lightweight structures for commercial airplanes. And what you see here is a 30-foot-long test article that we'll be testing at the NASA Langley Research Center by applying the kinds of loading that it would feel if it were in a real airplane.
But with a piece this large, a major hurdle lay in front of them: how to get the piece from California to Virginia for testing. Traditional methods like trucking and train travel would not work due to bridges, overpasses, and some road weight restrictions. The solution was to fly it across country. But no ordinary aircraft would do. Ultimately, the team enlisted the service of NASA Johnson's Super Guppy aircraft for transport across country. This Cold War era aircraft was specially designed with a hinged front-loading system that could just barely accommodate NASA's cargo. It was not lost on team members that this old and slow beast of an aircraft was transporting a test article that will undoubtedly be used in many aircraft of the future. On a cold December night, the aircraft landed in Virginia for an early morning offload. Here is Dr. Faye Collier to explain what is next for this test.
Today we're here at Langley Field unloading the Perseus multi-bay Colts multi-bay box that will be tested in the Colts facility. So we've been working on Perseus for about 10 years now, partnered with the Air Force, partnered with Boeing, R&T, and we started off with small coupon testing to prove out the concept. We built a small box that we tested 3 years ago to prove that the concept could take pressure and would meet the design constraints. We went from there to assembling this piece of 30-foot structure that we're going to test in the Langley Combined Loads Test System down the street here. So a long effort that has gone into this with NASA and Boeing, culminating in the delivery of this 10,000-pound piece of aircraft structure. We'll stick it into the facility. We'll mount it. It'll be eventually pressurized to various pressure readings. The idea is to twist and turn the part to see if it'll sustain the design loads that would be needed if we were to build a real airplane out of this.
This facility will prove to be a valuable tool for researchers. These types of tests will help in investigating damage tolerance and any repair techniques that may be applicable. One of the key test points that will be addressed in this round of testing will see how Perseus handles routine damage that might be expected, such as a technician dropping a hammer. Researchers need to understand how this new material will react if minor damage occurs. To do this, a unique test rig has been designed by hand. Here is Andrew Lovejoy to explain.
So some of the things that could impact the plane are rocks or debris that's on the runway when it's taking off or landing. As I said, you could have mechanics that could hit it with a tool, or a vehicle driving by could hit it. And all those types of things can cause damage. And on the exterior, you're more likely to have a higher energy because a vehicle hitting it or something being thrown up by the tire is going to be a much higher velocity than, say, a tool drop. So barely visible impact, if you're doing walk-around inspection, it's a damage that you would barely be able to see. So if you're at that level, the aircraft has to be able to sustain the loads that it would normally see, even with that damage in place. So you have to be able to analyze and then test to make sure that you can hold those loads. So what you have to do is an impact test. So we're doing an impact test, and if you were going to impact at the top on something, you would just have a free-falling, you could have a free-falling weight that would come down and hit. And that's fairly straightforward because you have a mass and you have a height, so you can have a straightforward calculation of the energy. If you wanted to hit on the side, we have spring-loaded, but for the multi-bay box, one of the things we're doing is hitting on the keel, which is the bottom. So we have to have an impact that's going upwards. There's very limited space in Colts. You can have an air-driven projectile, you can have a spring-loaded, but those to me are less controllable. So instead came up with the roller coaster impactor. So it's really a controlled drop. It comes down the track and then it'll go back up, and when it hits, it's going in a vertical direction. So in order to impact on the keel, we needed the impact weight to go up, and we didn't have any device to be able to do that. So from scratch, we designed and built the roller coaster impactor. The second main part is the track itself. The track itself is to control it and make it go where we want it to go. When it's rolling down, gravity's keeping it on the track. When it starts to go vertical, it wants to flop. So there's actually two pieces of track that will encapsulate this right before impact to guarantee that we're getting that vertical impact on the bottom of the keel.
Numerous tests were performed in the Colts facility to check the box's ability to meet what engineers call the design limit load and the design ultimate load. In aerospace engineering, the term design limit load refers to the maximum load factor authorized in flight. It is extremely unlikely that an aircraft will ever reach this limit during its lifetime. The design ultimate load goes beyond that and is the amount of load applied which will make the component fail. In this case, the ultimate load factor is 1.5 times more than the limit load. With testing and data acquisition complete, researchers found the Perseus box performed beautifully under extremely stressful conditions. It actually performed above the expected design ultimate load factor, which means the box is even stronger than predicted. With that type of result, researchers feel there is an opportunity to lighten the box even more, potentially making future aircraft even more efficient. Although this stage of the testing is complete, the team has reams of data to look over and will continue working to make the aircraft of tomorrow stronger and more efficient than ever. The hinged wing design on aircraft has been around since the early 1900s. Currently, this design is state-of-the-art and almost magical in its operation, extending and retracting during takeoff and landing. But hinged flaps have drawbacks, such as high noise levels, and their design affects the flow over the wing, making them less efficient. NASA is currently working on improving specific aspects of wing design and has partnered with a small company out of Ann Arbor, Michigan called Flexus to combat these problems. Their innovative design has the potential to revolutionize flight by having the wings on aircraft act more like a bird's wing rather than the traditional flap system we have now. Here is Dr. Sridhar Kota, the inventor of the Flexus wing, to explain.
So with the current flaps, once they're tucked in, you don't want to move those flaps because the flow will separate. So the aerospace community has known for a long time that if you have a seamless wing that can be morphed in flight to maximize the performance, then you can get significant fuel efficiency. And actually, Wright brothers did that for roll control.
The idea to have aircraft wings morph is not a new idea. In fact, the Wright brothers' first designs used morphing wings to help with controlling flight. But as aircraft became heavier and began using stronger materials, aircraft designers were forced to stop using the morphing wing technique and use flaps and slats, which have been in use ever since. Designers have long known that reducing the use of flaps and going back to a morphing wing would be more efficient, but until now, no one was quite sure how to make it happen. While looking at this problem in the early 90s, Dr. Kota came up with an idea called compliant design that uses techniques that are borrowed more from nature than from traditional mechanical designs.
Everything we engineered, if you look around the objects around you, anything that is strong is also very rigid. And when you want mechanical functionality in the design, you put multiple parts, springs, cams, gears, and make intricate mechanism that works beautifully. Whereas designs in nature are different. They are strong, but they are compliant. They're flexible. So you can see the trees bending in heavy winds, so they bend rather than break. And you can see countless examples in nature where you get pretty intricate mechanical motion without conventional joints. And in fact, 80% of living creatures are invertebrates, and they do pretty well with the locomotion and other mechanical functionality without multiple joints and links. So the question is, how do we capture that, where we want a monolithic structure that can do mechanical motions without joints? So the idea is that how do we get this compliance, the flexibility distributed throughout the structure, and how do you design structures like that? So I'll give you a simple example of what I call the distributed compliance. And you can see this here. So here, this can be a monolithic design, no joints. And when I apply force at these tabs, and you can see it move, so you can get large deformation. But the way it's designed is you have very small stress in the structure, which means every section of the material shares the functionality, shares the load, so the stresses are evenly distributed. That's how we have very small stress, very small strain. It works in a linear elastic strain region, so you get large deformation, and which means you can do this multiple times. You can do this millions of cycles and still not fail.
Although the exact technique is still a trade secret, the Flexus team's design uses a proprietary algorithm in a way that minimizes the force it takes to morph the wing to a prescribed shape. This technique also has inherent mechanical advantages in that it is very stiff to external loads. Simply put, the design is incredibly strong, but does not need huge motors to morph the wing. To test this concept further, NASA's ERA team decided to place a Flexus wing on board an aircraft to test in flight. The team removed the traditional flaps from a Gulfstream aircraft and replaced them with a Flexus wing for the initial testing. Tom Rigney of NASA Armstrong explains.
The reason it's important is because one of the contributors of noise, one of the largest contributors of noise for an aircraft, when it comes down to approach for landing or for takeoff, there's a lot of noise that's generated by the spaces and gaps from existing flaps that are on an aircraft. And so what this does is it reduces that noise by eliminating those gaps. And they have a smooth, continuous surface rather than having gaps. And it can reduce sound within up to 4 to 6 decibels, which is significant. This technology is really helping aviation, the whole aviation industry. It's something similar to what we had with winglets. So winglets came on aircraft and made them much lighter and more efficient, more effective. And this is similar to winglets. We're going to be able to take an airplane and have wings act more like a bird Instead of having just these boards that come down and all locked in place, we're actually have morphing and shaping wings just like a bird would do. And that makes the aircraft more effective in terms of flying, in terms of efficiency, fuel savings, and it's going to save hundreds of millions of dollars for the public for flying. It's also going to make planes lighter weight, which allow for more luggage and other things to go on board. And it's more of a green type of technology, less carbon in the air for the world to have to deal with later. So this is going to be really helping out the environment as well as saving money. So it's really a great technology.
The first tests of this design were very successful and met all of the stringent stretch goals that engineers set out to meet. This design shows tremendous promise, and future testing should continue to further validate the time and effort that the ERA team put into this technology. NASA, in cooperation with industry partners, is truly transforming the concept of how we fly. 2025 is right around the corner, and before you know it, many of the concepts the ERA team has studied will undoubtedly be used to make flying safer for all of us.
It's extremely exciting. In my lectures, there are always young people in the audience, and they always want to know when they're bringing it back, and I always say, I don't think ever. I think NASA, they realizes that they have two marks, so to speak, but somehow they can be made to coexist. We had to analyze what had been done by NASA in the past. Finally, we realized that we had to have a unifier, something that was very strong to hold it all together. So over the process of working on it over the first month, I think we got simpler and simpler with our solutions so that it would work miles away on a T-38 or a rocket or a space shuttle. We were trying to embody in the logo innovation. The organization still had aeronautics as well as space, and so that you see a kind of nose cone design inside of the A's and propulsion, kind of upward thrust. Great simplicity, but still movement.
Roger, roll, Discovery.
The term worm came out of Florida in a newspaper down there, and it was meant to be derogatory, and I personally thought it was very derogatory. And eventually, over the years, the worm became a term of endearment, but it wasn't meant that at all in the beginning. When they started producing apparel a couple couple of years ago. They found out how young people in particular really like this program, and so they've allowed it to kind of come back to life on its own. It's validation, I think, of the sort of timeless approach that we brought to this. Space is about the future, and if we can still hang in there, and if it still represents that, then it's quite a victory, I think. You know, aesthetics aside, the goal was to do that, to hold up for decades, and apparently it's still it's got better legs today than it did then.
It's a very unique challenge to go and build something where you've never been before. My name is Jose Ortiz, and I'm helping to return humans to the moon safely. The Space Launch System is a big rocket that carries the Orion spacecraft with astronauts on board to space. So if something goes wrong during that initial phase of the launch, then the launch abort system is activated. So it carries a crew module with the astronauts to safety. It's a big challenge, and it's just fascinating to me to be able to design and build those components and then see them work. I like to repair things. So that's kind of a hobby I have, to go repair things in my garage. Neighbors find out about it and they come in, hey Jose, can you fix this for me? I have to thank NASA for that, and because NASA have enabled me to be able to learn and figure out how things work. I enjoy coming in and being part of a team and have a goal and make it happen.
Of a new generation.
Consider a busy street in a large urban city, what thoughts come to mind? Perhaps honking cabs, cars, or large crowds of people all trying to get to their destinations? Although that picture of a city may seem like a chaotic mess, the reality is that generally traffic and people move in a relatively orderly fashion. For the most part, cars stop at traffic lights, pedestrians cross when safe to do so, and everything works as it should, even if it's crowded. This system of traffic signals and rules of the road has been in place for many decades, so this type of movement is accepted as the norm for how we get around in a city. But what was city travel like before the invention of traffic signals? There are many stories of pedestrians dodging oncoming cars, horse-drawn carriages and fast-moving cars fighting for space, and just general mayhem ruling the day, due to a lack of a well-thought-out plan. There were already rudimentary manually operated signals in operation, but with only a stop-and-go signal, they were not very effective. This left drivers little time to react when the command changed. It was clear when automobiles became more prevalent in the urban environment that a viable solution was needed to lessen the unpredictable nature of traveling in a city. That solution was found in November of 1923, when an inventor named Garrett Morgan came up with the answer. After witnessing an especially bad accident one day, Morgan designed and patented a 3-position traffic signal, which used an automated signal with an interim warning position. the predecessor of today's yellow caution light. With this invention, cities around the world began to adopt this new technology, making the streets safer for cars and pedestrians alike. That fundamental change for city driving came about 100 years ago. Ironically, today, there is a situation in our modern world that is in need of a similar solution. But it will take more than adding a yellow light to solve this new problem. NASA, the FAA, and more than 100 industry partners have tackled the proliferation of unmanned aircraft and the need to regulate and manage these small drones. Just in the past few years, more than an estimated 700,000 unmanned aircraft systems, or UAS, have been purchased and are flying around our skies. With the push for these unmanned aircraft to be used in our daily lives for tasks such as delivering goods to our doorsteps, monitoring traffic on highways, recreational uses, and for medical needs, to name just a few, imagine what our world would look like in a few years if a dependable system of control was not put into place. Many have questions how such a dramatic change to the airspace will affect our lives and safety, and with that, NASA has set out to create a research platform that will help manage large numbers of drones flying at low altitude along with other airspace users. Known as UAS Traffic Management, or UTM, the goal is to create a system that can integrate drones safely and efficiently into air traffic that are already flying in low-altitude airspace. With UTM, package delivery and recreational flights won't interfere with helicopters, airplanes, nearby airports, or even safety drones being flown by first responders. On this episode of NASA X, we will examine this award-winning UTM technology and see how it works, and better comprehend this innovative system. We will also take a look at the dedicated NASA team at various field centers and its government and industry partners to understand the work accomplished developing and testing new software in real-world research. And we will see the system in action and find out when these new innovations will come online. Not too many years after the first flight at Kitty Hawk, North Carolina, NASA's predecessor agency, NACA, began developing technology and systems that have revolutionized the way we fly. NASA took over this workload from NACA in 1958 and has continued to pave a path forward for the aeronautics community ever since. As the premier science and technology agency in the federal government, it makes sense that NASA was once again tasked with understanding and developing a new system to make sure the drone technology would be world-class and safe from day one.
Well, there's a lot of reasons NASA's doing this work, right? So we can have a nice working relationship with industry as well as with the government side, the FAA, the DoD, DHS, DOI, that whole alphabet soup of folks that are interested in this space as well. We can bridge that gap between industry, the public, and them, as well as bring our experience in the airspace and in aeronautics in general to solve the problem, right? So building that coalition, coming up with unique solutions, testing them in the field, making sure that we have all the parties involved. That's really the sweet spot where NASA sits for this kind of thing.
NASA teams have been looking at unmanned aircraft technologies for quite a while, trying to better understand how large, medium, and small drones will begin to be integrated into our national airspace. Early conversations with the Department of Defense just needed NASA to help transition unmanned aircraft into the U.S. airspace. But those needs began to transform to a bigger picture almost immediately.
When we got involved in this, it was a pretty simple problem that we were trying to solve. DoD was bringing unmanned aircraft back from theater. They needed to move them from one base to another. And so the question was, how do you get these very high-performance unmanned aircraft up into Class A airspace? So take off from restricted airspace and move through Class E airspace up into Class A. And that, that's real geeky sounding and all, but for the FAA people, this is really important. So that's what we thought the problem was. After we had started working in this just for a couple of years, along came this package delivery. So a whole new mission and a whole new set of actors came out. So it took on a whole new meaning. NASA then got very interested in how you manage the traffic as well as what the characteristics of the vehicle should be. So when we first started, it was all vehicle-centric. But then as we got real interested in UTM, or UAS traffic management, took on a new meaning of how do you manage all of these vehicles around, and it has just blossomed for that into hundreds or thousands of use cases, and everybody that could possibly think about delivering some service or some product to a household or between businesses now has an interest in the work that we've been doing.
With the knowledge of building a completely new system that would fundamentally change how vehicles move in our airspace, the team needed to carefully understand the major issues. So they took a step-by-step approach to make sure they were moving in the right direction. They first had to lay out the goals, which included, but were not limited to, allowing diverse, small UAS mix and airspace use. For example, package delivery, safely enabling scalability for the future, and establishing a highly efficient, predictable, safe, and affordable airspace operations system, all by developing and validating integration requirements and providing prototype software UTM systems for the FAA to further test.
So NASA developed this concept called Unmanned Aircraft System Traffic Management because we are expecting millions of drones and their operations in a day, which is magnitude order different than what happens with current aviation, where there are 50,000 aircraft, and at a time there are about 6,000 at peak in sky. So the question is, how do we manage these millions of drones without burdening the current air traffic control system? Now, there are fundamental differences in the way the manned aviation works and the drone operations will work. First of all, there is no pilot. Second, that these drones are small. Third, we can actually take advantage of digitization and connectivity across these drones by exchanging information to each other. So the idea of UTM is taking advantage of modern technology, making sure we don't overload the current air traffic control system. Now, one of the big parts of UTM is this managed by exception paradigm. In today's operations, air traffic controller is the only one that has all the information on the radar display. With UTM, we can connect all the information, and that information can be shared across all the operators in the sky. That allows us to basically say that just tell me what not to do, and I will figure out a path that will avoid other vehicles in the sky.
As PK mentioned, the system is a bit different than the air traffic control system used by the Federal Aviation Administration for today's commercial airplanes. UTM is based on digital sharing of each user's planned flight details. Each user will have the same situational awareness of airspace, unlike what happens in today's air traffic control.
Well, with the projected number of new drones coming in the commercial markets for a very large number of drones and operations, it's obvious that the current air traffic management paradigm, a human air traffic controller communicating with one or a handful of vehicles, will not scale up to the number of operations of commercial drones that people are thinking about. And so a new way of controlling this traffic had to be established or thought up. And so NASA came up with the idea and vetted it through the FAA and industry to have this automated system that really did not rely on human air traffic controller interaction. And a key to this is that industry would be providing these services. And this would foster competition and economic growth and such for the system. And so this whole development of this traffic management system not
manually controlled by the air traffic controllers, but by automated systems provided by third-party industry commercial providers, really is a major change in the way air traffic management will be done in this country, and necessary to satisfy the vast number of new entrants in this growing drone market.
You think about the different ways that this system will impact people's lives. One simple one is ordering things online, right? In the future, you may be able to order something. It could be delivered to your house by drone in minutes to hours as opposed to days. That's one use case, right? So people can say, oh wow, that would be neat. Also, you can think about public safety, right? For example, fire departments. One thing they would like to do is to send a drone out before the truck can get there, right? It's possible for the drone to get to a site faster than a truck can, and they can survey the scene before their folks actually arrive. So again, that's a public safety feature that people can usually feel good that our system, a system like we've designed that may be implemented in the future, could help support. So let's imagine both of those things happening at the same time. Someone trying to deliver a hot dog to your house, and then actually a fire happening and the fire department wanting to get through. The system enables those kind of interactions, and it keeps the airspace safe, it keeps things from falling out of the sky, it keeps all the stuff working properly.
To begin problem solving, the team created 4 individual technical capability levels, or TCLs. TCLs are a risk-based development and test approach. TCL-1 served as the starting point of the platform, with drones flying simultaneously at 6 test sites, while each test site operated on their own schedule. TCL-1 focused on areas of remote population, low traffic density, rural applications, and work on notification-based operations. Researchers conducted field tests addressing how drones can be used in agriculture, firefighting, and infrastructure monitoring, and working to incorporate different technologies to help with flying the drones safely, such as scheduling and geofencing, which restricts the flight to an assigned area. After completing these valuable tests, the team then moved into the second stage of the testing, TCL-2. For TCL-2, NASA performed a 5-day flight test at the Nevada test site, with additional flights taking place for the national campaign at an additional 6 FAA UAS test sites. This testing was focused on monitoring drones that are flown in sparsely populated areas where an operator can't actually see the drones they're flying, known as beyond line of sight operations. Researchers tested technologies for on-the-fly flight adjustments in controlled airspace and technology to clear airspace for search and rescue missions or for loss of communications with a small aircraft. As the UTM team monitored these flights, researchers also introduced simulated aircraft into the same airspace occupied by the drones to add more complexity in the system. The drones flew profiles that simulated real-world uses, such as package deliveries, farmland surveys, infrastructure inspections, search and rescue missions, and video surveillance operations. This work was proven successful, and the team quickly moved on to the next phase, TCL-3. TCL-3 was flown at the 6 FAA designated test sites and focused on creating and testing technologies that will help keep drones safely distanced and flying in their designated volumes.
The UTM project also included the development of onboard technologies to help mitigate the risk from drones, both for those in the air and on the ground. These technologies are designed to help recognize and address potential problems while in flight and without human intervention. One of these technologies allows a drone equipped with special sensors and software to autonomously sense and avoid other aircraft.
This capability level also tested vehicle-to-vehicle communications in areas with moderate UAS traffic density. Testing also included UAS ground control interfacing to locally manage operations, communication, navigation, surveillance, human factors, data exchange, and network solutions. Drones were also flown beyond visual line of sight and in close proximity in altitude and distance. The focused technology flight tests were conducted at Langley and Ames research centers and complemented the flight testing conducted at the designated FAA test sites. Both provided valuable information of the flight performance of the drones necessary to work within the UTM system. Since UTM is a new way to manage air traffic, human factor data collection in real-world conditions is critical to understanding the human-system interactions.
We're really breaking new ground on the way human operators interact with complex systems. And so being here helps us get data on exactly their experience with this system. So for example, we are kind of monitoring the communication patterns that they use. So UTM as a system is exchanging lots and lots of data, and that data can be presented to those operators in a variety of ways. And they also have other ways that are not UTM to communicate with each other. They can communicate with each other over their radios. They can communicate each other through like texting applications, right? So we're kind of measuring all of those communication patterns to see what things are they talking about through UTM means and what things are they talking about with outside of UTM means, to really give us a sense for how well UTM as the system is supporting operators in conducting their operations.
Finally, TCL4 demonstrated how the UTM system can integrate drones into urban areas. Corpus Christi, Texas and Reno, Nevada were chosen as the test sites, offering the right mix of challenges to prove that UTM could work anywhere. The cities have large populations, many obstacles to avoid, windy weather conditions, reduced lines of sight, and fewer safe landing locations. TCL4 addressed these challenges using UTM systems and technologies on board the drones and on the ground. These include incorporating more localized weather predictions into flight planning, using cell phone networks to enhance drone traffic communications, and relying on cameras, radar, and alternate ways of seeing during flight to ensure drones can maneuver around buildings and land safely, all while communicating with other drones and users of the UTM system.
Over the progression of this project, where we are now is the most complex piece of it, right? So now we are testing in urban environments, in higher density operations, looking at kind of contingency or off-nominal situations. So that list of three things, urban environments, higher densities, off-nominal situations, those are all extremely complicated things to tackle. And so for us to be here tackling those things is the only way we could learn some of the things that are associated with those things. That would be all very difficult to learn in a laboratory setting. There are so many things that are really an opportunity that come from the geographic locations in which we are testing that give us these types of this data, everything that we learn from being here.
Although all this research took place here in the U.S., this new structure will be the framework used around the world.
UTM idea, concept, architecture is out there, and it's been endorsed by ICAO, the International Civil Aviation Organization. And if you look in Europe and in Asia, countries that are starting up their version of UTM, they're starting with this architecture that NASA developed. And so it's really out there, and we're participating in international standards groups to really kind of consolidate what the concept is and harmonize internationally.
The influence of UTM on future projects, I think, was something we're pretty proud of, right? The concept and the way of managing the airspace is really new. And people are seeing application of that to, for example, UAM and air taxis, potentially for high-E operations over 60,000 feet, space traffic management. All of these things can leverage what we've learned in UTM because it's about providing services to classes of operations where services aren't provided now and probably won't be provided. Right, so finding a solution to that really has benefited future work as well at NASA.
It's clear to see that a tremendous amount of planning, research, flying, design, and hard work went into this project, and that the UTM framework is here to stay.
I think we are really getting into a whole new era of aviation, right? Where we got completely new operations that weren't there before. We are envisioning a few years from now, maybe 10 years from now, a world where we'll be traveling through cities in small electric aircraft, for example, and we'll have our some drones delivering medicine or delivering food or things like that. All this is really only going to be able if we set like a foundation where we can use our great new automation capabilities, networking capabilities, really making use of digital ways to coordinate all these different operations and all this air traffic in a way that just wasn't possible before. But the only way that we can actually do this is by shifting the paradigm entirely from this very human-centered approach that we've been taking over so many years to safely manage all this traffic that was existing for these new operations, to take an approach that is a lot more built around safe frameworks in which the different technologies can interact with each other, and where they actually are going to be able to provide the first level of safety layers and the core components of organizing all this traffic.
UTM is enabling airspace operations and providing access to users that was never possible before. It's opened up skies in a way that we can now enable different types of operations in the airspace, and we have a way to manage the traffic because of UTM, which gives tremendous societal benefit of reaching places, cargo as well as people, that was not possible before.
Low-altitude airspace is leading a revolution in flight, and a multi-billion-dollar industry is emerging as a result. At no time in history has aviation been poised to enter the lives of so many people. From package delivery to first responders to safety inspections to video documentation, every person stands to benefit in ways we have only begun to imagine.
We're really at a once-in-a-lifetime opportunity to be part of aviation. We see new aircraft like we've never seen before. We have new types of software systems, scalable and cloud-based. We have new companies that are entering the space that we haven't traditionally seen in aviation so far, and we have really great collaboration amongst industry to work together, as well as collaboration with the FAA and aviation authorities to go ahead and make that happen. And that really sets us up for the next 100 years of aviation in a way that we haven't seen before.
The research and development completed on the UTM project has come to a close, but that doesn't mean that the final chapter of this technology has been written. NASA and its partners are planning future research and testing to mature these systems to the point that one day soon, flying drones in our neighborhood will be as common as seeing yellow caution signals on traffic lights. With the success of NASA's UTM project, that day is much closer than you may think.
It is great to be back at America's Space Coast, at this historic place with the men and women of the John F. Kennedy Space Center. And it's here today in the 21st century that the modern marvels that launched from these grounds prove that the public and private sectors are achieving far more together than we ever have apart. American businesses are developing new rockets, spaceships, satellites that are taking us further into space than ever before, and renewing our confidence that we can and will achieve the impossible once again. This truth echoes through the history of the Kennedy Space Center. Named for a president who challenged the American people to marshal the best of our, in his words, energies and skills to become the world's leading spacefaring nation. I know America will once again astonish the world with the heights we reach and the wonders we achieve. And as these feats of American enterprise and ingenuity attest, much more than the bridge to space, Kennedy Space Center is the bridge to the future.
The reason that you would do any kind of experiment in space is if there's something particular about the space environment, and most often that is microgravity. So mostly the ISS gives us the ability to either do something that we can't do in a facility on Earth or investigate some phenomenon, some property in a way that we can't on Earth. So for example, some of the tissue architecture, these really delicate tissues, as you start to build them up, they would collapse because you have gravity, or the cells would naturally settle to the bottom of the plate. And so you just can't study the answer to the question that you're looking for. So the space station lets us have that ability to either test what the effect of gravity is or remove that problem entirely from our experimental setup. Yeah, the space station's an incredible place to conduct research. It was sort of like being in the world's most amazing lab when I was up there in 2016. So when you're a scientist, you're used to working on one thing over and over and maybe really refining the details on that over the course of a PhD thesis or a lab project. On space station, you get somebody's incredibly refined project times 200 different fields. So for me, it was a chance to learn about all of these different areas of science, and they each have a team behind them. So I was usually pretty excited to open the container and do whatever experiment that day brought. I also really got a chance to talk to those PIs, the principal investigators, and those scientific teams, and understand everything that was going on behind their experiments and read their papers. So by the time I got to doing the experiment, I was pretty excited to take it out and to see what was going to change in microgravity. Yeah, science in space, it's an amazing lab and it's incredibly fun. So we are smiling all the time. I'm Kate Rubens. I'm a scientist and an astronaut.
It's a new era of pioneers, star sailors, thinkers, and adventurers.
3, 2, 1, 0. All engine running.
Let's go.
We have been given the scientific knowledge, the technical ability, and the material to pursue the exploration of the universe.
Locked and we have good to send that command. You have 31 minutes and 32 seconds for our support. Go for status buffer dump.
Since the retirement of the space shuttle, the engineering team is absolutely critical for Hubble. It always has been.
Without the shuttle going up to replace any equipment failures that we have to make do with what we have. What we really are concentrating on is just keeping the telescope working and keep the science going.
And everything looks excellent, and we have no reason not to expect that Hubble will last into the late 2020s and beyond.
My name is Mike Wins, and I'm the lead systems engineer for what's known as the Optical Telescope Assembly of the Hubble Space Telescope. I'm in charge of what's known as defined guidance sensors. These are the instruments that actually help Hubble do the exquisite and precise pointing that it does. Right now we're getting ready to perform an observation. The telescope is going to be trying to go to acquire some guide stars in just a few minutes here. The stock is the Space Telescope Operations Control Center, where we send commands to the spacecraft. On a daily basis, we have to send up what's known as command loads.
Accepted. DTMR is good. Step 3 is complete.
Because the computers on Hubble are very old and they have very little memory, in fact, most of your memory sticks today are 20, 30, 100 times bigger than Hubble, we have to send up essentially a load of all the commands Hubble's going to be doing for the next 24 hours.
On a routine basis, we always keep 24 hours of instructions on board, so it's routinely updating for the new sequence 24 hours in advance.
We'll start with doing our premise uplink.
Hubble is always working, it's always doing something, it's always doing some sort of observation or calibration or getting ready for the next task.
We'll be logging on forward at 14:33:17.
Hubble is truly a 24/7, 365-day-a-year instrument, so the Hubble can keep on going. It never stops.
And we are configured. It's been verified.
Now we do have to, because of this low Earth orbit we're in, the actual observations, when we're taking a picture of something, we're doing a science observation, we actually have to wait because sometimes the Earth gets in the way. So we have to pause, wait until the Earth gets out of the way as we go back around and start the observation back up.
You have constraints. You don't want the optics pointing at the sun, and you don't want the instruments to have their shutters open when you're looking at the Earth, because the Earth is bright for them. And then we have the South Atlantic Anomaly, the SAA, which is a portion of the Earth where we get proton hits that will affect the electronics in Hubble and can also affect the instruments in Hubble. And so we have to plan out very carefully our targets and observations. We have a timeline that's laid out to maximize the efficiency of it.
Hubble can actually take observations during day and night passes. Every 95 minutes, we go around the Earth. The batteries will charge from the solar rays during the day pass, and then at night, batteries power the observatory so we can continue observing. The scheduling with Hubble, we're trying to put it together as efficiently as possible, minimize our gaps. The goal is to constantly keep it busy.
We're constrained to a certain extent, but whenever we have visibility, we are observing.
The demand for use of the Hubble Space Telescope from scientists around the world is very high.
Hubble, it's at its most productive. It's got some of the best instruments that have ever been on board it. There's a very high demand. Hubble's performing exceptionally well.
2, 1, and liftoff of Space Shuttle Atlantis. The final visit to enhance the vision of Hubble into the deepest grandeur of our universe.
Since the final Space Shuttle servicing mission, we're using Hubble to get the best kind of science return we can from the suite of instruments that we have. So our focus now is on making sure we get the best science while it's still operating so well.
Luckily, at the end of the last servicing mission, we were actually left with a telescope in great condition, but Hubble is getting older and older. It's a very old telescope.
Now, 10 years after the last servicing mission, we can't rely upon servicing missions to fix things, so we have to rely upon our own ingenuity to be able to figure out if something does fail, what are the alternative paths that we have.
For the telescope to keep giving us this peak science, we need lots of things to be working together very well on the telescope. We need a pointing accuracy system that is outstanding and keeping that whole system healthy and functioning so that we can point Hubble very accurately even while it's whizzing around Earth in its orbit.
For the telescope to be able to do the science it needs to do, we have to hold it very, very steady. There is actually a little bit of motion. I mean, it's hard. We're zooming around the Earth at 17,000 miles an hour, so it's hard to hold the telescope perfectly like that. The gyros are working really good.
The gyroscopes can sense motion in each direction. And so because of the gyroscopes that we have on board and how sensitive they are in terms of sensing motion, that we can keep our cameras steady.
Gyros are very good at measuring these very small rates. The fine guidance sensors are actually sort of used, I always like to describe it as backseat drivers. And they constantly tap on the gyro's shoulders. It's about once a second. And they keep saying, turn left, a little bit more right, a little bit left, a little bit right. I mean, it must be driving the gyros nuts. So the fine guidance sensors allow you that really fine control, but actually it's the gyroscopes driving the telescope. And they're doing a perfectly good job here. Everything looks good, our stars the right brightness. The reason that is because we need to make sure we have the correct guide stars. One of the things we look at is the brightnesses, and that's what we're measuring here. Those are about right for what the stars were. But also we wanted to make sure they were exactly as far apart as we thought they were going to be. And it did. It did a check and it passed a very, very tight tolerance check to make sure that those were the right stars. So we know we're locked up on the stars. We got a good lock here. The gyroscopes are very critical because to be able to move from one position to another position, the gyroscopes are the only thing that can tell us how we can do that. We have 6 gyroscopes on board Hubble. Currently, 3 of them are still working. And 3 is sort of what people used to think of as the minimum number, but we have developed a science mode where we only need 1 gyro.
A big part of our job is to make sure that we can extend the life of Hubble and continue doing the high performance science that we're doing for many more years.
And what we've done is we've gone through all the critical components of Hubble and said, how can we potentially make them last longer, as you might do with your own car, as it's getting more miles on it. The gyroscopes have been our most problematic piece of hardware. So I helped lead an effort to develop a 2-gyro science mode. And we were able to use that mode on orbit and be able to perform science. And then learning from that, we actually developed a 1-gyro science mode that we've been able to test on orbit, but we haven't been called on to use. But in the end, possibly 5 to 10 to 15 years from now, when we're down to potentially our last gyroscope, that is the mode we will be in. Before we do anything on orbit for the first time, we have to test it out on the ground. And we're very lucky to have what we call the VEST, the Vehicle Electrical System Test Facility. And the key with the Vehicle Electrical System Test Facility is it's an exact copy of the main part of the telescope where all the electronics are. And it has the mechanical bays, it has the computers, the electronic boxes installed in there, and it has the cables and harnesses in there. And in fact, when we were building the VEST, we had the quality engineers came to us and said, you're not doing these cables exactly the way you should be doing them. You know, we've got better standards now. And our thing was, we're trying to build a copy of what we have on orbit. And so what you have in the VEST is an exact electrical copy of the Hubble Space Telescope. Every orbit as we come around the Earth, to be able to get our attitude correct, to get ourselves steady and locked on, the fine guidance sensors and the gyroscopes are key to that. And that's why those are the 2 of the subsystems that are on the top of our list as far as having contingency plans for and monitoring the health and safety of those and making sure we have them in peak performance. When something fails on Hubble, or we have an anomaly, something we don't understand, one of my jobs is to bring together the experts, which may be a thermal engineer, a mechanical engineer, an electrical engineer, a software engineer, all these different people. And we'll say, you know, how do we deal with this issue? And how can we work around it and return back to peak science? What you do is you come up with a list of what is available to you on the telescope in terms of potential. I could close this relay or open that relay or turn on this box. And I am continually amazed. You have a telescope on orbit that you can't even see. I mean, all you're doing is looking at the data coming down to you from the ground. These experts are able to use their ingenuity and come up with ways to continue to operate Hubble. And everything looks excellent, and we have no reason not to expect that Hubble will last until the late 2020s and beyond.
I personally am extremely grateful to the Hubble operations team, these people who work day and night to keep Hubble operating, providing exquisite science return, giving us the information that we need to know how Hubble's doing. Is it doing the kind of accurate pointing that we need? Is it getting the sensitivity in the various wavelengths of light in the various instruments that we need to have to do the science? Are we able to calibrate those observations in an accurate way? We couldn't do any of those scientific analyses if we didn't have this team of operations experts behind the scenes making sure that the details of Hubble's technical operations are being monitored, being handled, being managed, being planned in a near perfect way. Because the Hubble Space Telescope is so scientifically effective right now, scientists are using Hubble to investigate some of the deepest mysteries of the universe.
One of the primary things Hubble has been doing is looking at the atmospheres around exoplanets.
If you had asked the guys who built Hubble and designed Hubble, they would have sworn Hubble could never, ever do this.
That's one of the things I love about Hubble, is that it ends up giving us new questions, new mysteries to explore.
My name is Larry Dunham. I'm the Chief Systems Engineer for Flight Systems here on the Hubble Space Telescope. I started on the Hubble program back in the summer of 1982 when Hubble was being built out in California. First telescope in space to be designed so that we've got what we call orbital replacement units. They're modular boxes with handrails on them so the astronauts can go up and just pick and play. They've got nice connectors on them that make it easy for the astronauts with their big gloves to be able to put them in and out.
We've had 5 servicing missions. We have replaced some equipment multiple times, especially the instruments. We're always going with the advanced technology.
The telescope we have today on orbit is not the telescope that we launched originally. We've been able to replace all 5 of our science instruments with instruments that have the technology that didn't even exist when Hubble was being built originally.
The Hubble Space Telescope is really an observatory because it has several science instruments, several modes of operation. We have multiple cameras, multiple spectrographs. They each have different capabilities in terms of their sensitivities or the kinds of frequencies they can receive the electromagnetic spectrum. We can also use Hubble in different kinds of intriguing modes depending on what we're trying to observe.
There are different types of observing scenarios, and one of the things the scientists have been able to do is they've been able to come up with very interesting and unique observing scenarios that allowed them to do science that they never thought they could do before.
Because the Hubble Space Telescope has been operating for a long time, it's giving us what we need to explore the universe in deep ways that would never have been possible when Hubble was first launched. For example, scientists wondered whether we could use Hubble in an innovative mode in recent years, basically scanning objects slowly instead of just staring at them. In some cases, that gives us a higher sensitivity to what we're trying to observe. And we're using that special mode on Hubble now to get better information about many types of things in space, including to be able to study planets around other stars, what we call exoplanets, planets outside of our own solar system.
What Hubble's been able to do is as the planets go in front of the stars that they're going around, the spectrographs can detect changes, very small changes in the spectrum. This has allowed them to do exoplanet atmospheric studies. This is something that Hubble has sort of really stepped up to the plate and has been just phenomenally good at. Spectrographs have really sort of been leading that. If you ever see things about, oh, a new exoplanet was discovered that has this in the atmosphere or that in the atmosphere, or we think it's made of this, it's the spectrographs which have shown you that kind of information. For doing a lot of the exoplanet observations, you have to catch what's known as a transit. One, the orbit of the exoplanet has to be such that it's going to go between you and the star it's going around. We can't just do an exoplanet observation whenever we want or whenever it's convenient. We have to do an exoplanet observation when it's first starting to go into the star. And so they have to know very accurately the timing of that. We have to schedule it ahead of time. This is not something that Hubble can get around to when it wants to. We have to say, no, at this point in time, on this date, you have to be pointed here and you have to be looking here. We had to really think about how to schedule this. A lot of thought goes into it. A lot of thought goes into the planning and of the execution.
The Hubble operations team are quite willing and capable of using the telescope in new modes and new innovative ways that enable us to accomplish science that we wouldn't otherwise be able to accomplish. We asked them, would it be possible to use Hubble to track something moving quickly across the sky? And they figured out a way to use Hubble in a vast tracking mode that enable us to do explorations and discoveries that astronomers didn't envision using Hubble for when it was first designed.
Now, when we're observing our planets, when we're observing Jupiter or Saturn or Uranus or Neptune, they move also. We have to move the telescope because they're just going around the sun. They're actually moving because they're really moving. And so we have to move with them. We're observing asteroids or comets. We have to chase after them.
Oumuamua, we know came from outside of our solar system, is like a big asteroid that was detected whizzing through our solar system. We wanted to use Hubble to observe this as well, and we were able to track it. This is not a simple operation. It's moving at more than 100,000 miles an hour, so being able to observe this and track it is a wonderful capability that the operations team has enabled Hubble to have.
The telescope is big, it's massive, it moves about the same speed as the minute hand on a clock. So to move from pointing one thing to go completely around the other one takes us a half an hour. It is not a very fast motion. We actually use a very interesting technique. It's using Newton's third law. We have these very large reaction wheels on it. They're about 2 feet across, very, very heavy, very, very massive wheels. You start spinning those wheels one way, the telescope will spin a little bit in the opposite direction. This is how we can move the telescope from one part of the sky to another part of the sky.
Once we've moved the reaction wheels and we've moved the telescope to we're in the right spot, now we have to get in the exact location to put the target in the science instrument aperture.
What's going to happen now is the FGSs are going to start talking to the telescope, talking to the flight software computer and saying, I want you to move the telescope over here a little bit to be able to position the science for the science aperture.
Most of the time we use the Hubble Space Telescope to do observations that have been planned quite a bit in advance. Observers around the world, astronomers will write proposals. We will then take those accepted proposals and observe whatever it is that the astronomer has proposed. But sometimes there are things that happen that are unexpected or rapid events that we need a more rapid response.
We have a capability of what we call a target of opportunity. And that's when something unexpected happens in the universe that astronomers, they want to immediately jump on that as fast as possible with Hubble. Case in point was the gravitational wave detection to neutron stars colliding. A target of opportunity was submitted for Hubble to actually go look at the remnant and see if we could find it.
We had the engineers run through it. We got new commanding sequences from the Space Telescope Science Institute. We were able to run all that through, and then we executed on orbit.
We have to respond very fast. We produce a new schedule and set of command loads.
We can modify a lot of the flight software, modify how the instruments are commanded. It allows us to change. We can react very quickly. What Hubble has done compared to what we were thinking Hubble could do is just amazing. Hubble's had its fingers in almost everything, a neutron star collision, looking for all the supernova, all this stuff going on with dark matter, dark energy, exoplanets. Hubble has just been constantly finding new things. Now we're looking at these interstellar comets and these interstellar asteroids visiting us. It's really been spectacular to watch.
There really are two key aspects to Hubble's design that have enabled us to last the 30 years that we have, and that is really the redundancy that we have on board, and then it's the servicing, putting in new and improved instruments and being able to improve the hardware with lessons learned over the 30 years of Hubble operations. We are now at our peak performance.
The Hubble Space Telescope has had a profound impact, not only on astronomy. It showed that humans in space and science can go hand in hand to enable us to explore space in richer ways than we could ever do with either just astronauts alone or just with instrumentation alone. By using these skills together, new vistas of exploration are open to us, and that lesson is something we're still benefiting from as we envision future space exploration.
Go ahead. Okay, we have a go for release. Okay, Charlie.
It's amazing with a program that's lasted the duration that Hubble has lasted, that the astronomers up at the Space Telescope Science Institute continue to come up with new things that they want to try to do with Hubble, and we certainly hope that we'll be able to continue to provide that kind of capability to them into the late 2020s and beyond. What you're looking at with a telescope, of course, is the light from billions of light years away. So the further you look, the more you're going back towards the Big Bang and understanding how the universe was formed.
The Webb telescope will be groundbreaking because it has capabilities that are different than the Hubble Space Telescope.
We have equipment that is so much more powerful than anything we've ever had before that it's almost impossible to tell what we will discover.
Hubble's accomplishments include something called the deep fields, looking out into space and collecting light, sometimes for many days, These deep fields have revealed visually to us a universe absolutely teeming with galaxies, hundreds of billions of galaxies.
One of the neat things about the ultra deep field, and one of the things that made it so unique was how long it took us to take that image. There's an exposure time that's expressed, I think it's 11.2 days. There's a very, very long exposure time. But probably what's more important is how many orbits it took us to do that. 400 orbits of Hubble data to take that image. You only get 15 orbits a day. To take 400 orbits and say, we're going to observe this one spot in the sky for 400 orbits. And the really unique thing about that was they picked a spot where there wasn't anything. They looked and they said, there's absolutely nothing here. And they said, you want to spend 400 Hubble orbits looking at nothing? And they said, yes, because we want to see what it can see. And I think the results from the science, I mean, it was amazing. What they saw was spectacular.
Hubble had spent 2 weeks taking pictures of empty places in the sky, and they saw they weren't empty at all. They were thousands and thousands of galaxies.
We were amazed how many galaxies we've found, and we continue to go back to that portion of the sky to increase that visibility.
The Hubble Space Telescope is an outstanding time machine. It's incredibly important for our studies with the Hubble Space Telescope to realize that when we're looking at a galaxy, we're seeing it as it was millions of years ago, sometimes billions of years ago. It's taken that long for the light to get to us.
What you're looking at with a telescope, of course, is the light from billions of light years away. So the further you look, the more you're going back towards the Big Bang and understanding how the universe was formed.
What Hubble has revealed is that the universe has in fact changed over these billions of years of time. The early galaxies, the very distant ones as we see them, are simple. Sometimes they're messy looking, they're small, they haven't had time yet to form that grand spiral structure. Over time, we see galaxies actually merging with other galaxies and growing bigger and bigger, and those mergers can look like train wrecks in our Hubble images.
These very, very deep exposures that Hubble has been able to take, we have seen right to the edge of the universe, 13.5 billion years. When Hubble was first designed and envisioned, it was never thought it could actually see that far out. But because of the advances in the instruments that we've been able to put up on the telescope, and also the cleverness of the scientists, they've come up with very interesting observing scenarios, doing these really deep exposures where we just sit there for orbit after orbit after orbit, gathering the photons. We've been able to push Hubble out very, very far.
As Hubble looks out into these fields of galaxies, we sometimes see clusters of galaxies. These are galaxies that are held nearby each other by their mutual gravity. These clusters are massive conglomerations. There's so much mass that they have an actual observable impact on space-time itself. Einstein predicted that mass distorts space, but we didn't realize we could actually see the effects of that. But with Hubble, we have been able to see distortions in space around clusters of galaxies. The way we see that is when light from a background galaxy travels through that cluster of galaxies or around it due to this gravitational lensing effect. The lensing also magnifies that background galaxy, so if we look in some of these distorted arcs, we can see more detail than we would ever have been able to see without gravitational lensing, nature's boost.
There are observations where we're explicitly looking for the lensing, and they're getting science out of that just otherwise would just not be doable. Hubble has really taken that to the next level. It's doing large amounts of astrophysics that it's just never been able to do before.
Some of what we're doing with Hubble is to prepare for the new James Webb Telescope, which we anticipate launching in 2021, which will be able to see farther into the infrared part of the electromagnetic spectrum. That enables us to see some galaxies that are difficult for Hubble to see because they're so far away that their light is traveling through us through expanding space and gets stretched out into redder wavelengths, often far into the infrared part of the spectrum, even sometimes beyond what Hubble is able to detect well. The Webb telescope will give us more information about some of those very distant galaxies.
The James Webb Space Telescope is the follow-on telescope after the Great Hubble Telescope. It extends the discoveries of Hubble into the infrared spectrum region. We think that the first objects that grew out of the Big Bang material probably happened in about 100 million years after that start. And we think the Webb telescope can pick them up. They're rare, they're hard to find, but they should be there. The farthest we've been able to see with the Hubble telescope goes back about 800 million years after the expansion began. So we think we get much closer to the first objects with the Webb telescope.
Hubble gives information that the Webb telescope cannot give about visible and ultraviolet emission from things in the universe. And when we have all that information coming in at the same time, it's like a banquet of scientific return.
Now when we get the complete picture of every wavelength you can possibly see from ultraviolet to infrared, we hope to have the story of the growth of the first galaxies from the primordial material. So that will be a huge accomplishment that depends on both pieces of equipment, the Hubble telescope and the James Webb telescope working together.
So astronomers are very excited about this probability that we'll have both the Hubble Space Telescope and the Webb telescope operating at the same time for quite a few years. That will give us an abundance of new understanding about the universe. And already right now with Hubble, we're doing preparatory observations for the Webb telescope. We're using Hubble to do things, for example, like surveying distant galaxies to find out which ones would be prime targets for the Webb telescope. In fact, scientists around the world are proposing observations with Hubble right now specifically to help us learn information that will be useful for making the best use of the Webb telescope as soon as it's launched and gets going in its science observations.
I think the Hubble telescope has been the most productive science instrument ever built. In astronomy, there's what we knew before Hubble, and now there's what we know after Hubble. They're so different. Of course, Hubble has now had a life of 30 years, so it's had a long time to make this revolution happen. So it's not all at once. It's a gradual revolution, but it's still a huge revolution. Technology has changed dramatically over the 30 years of life of the Hubble telescope. So you couldn't even have imagined when the Hubble was launched that we would have the wonderful cameras and spectrometers that we fly today. We figured out how to send astronauts, we trained the astronauts, we figured out what instruments could be put in, we figured out how to repair everything that went wrong on the Hubble, and it's still alive. It's today, 30 years after launch. And I am so thrilled to say that our people were able to do that. That's the operations team that makes this possible. It's a miracle as far as I'm concerned, because it didn't have to be that way, but they made it happen.
Exploring the universe is a daunting task. There are often immense challenges that must be overcome before even setting out on a mission. The Ionospheric Connection Explorer, or ICON, has faced multiple barriers that have delayed its journey to study the frontier of space, the dynamic zone high in our atmosphere, where Earth's weather meets space weather. But before we can reap the benefits of its scientific research, ICON must launch successfully. The ICON team's can-do spirit will be repeatedly pushed to its limits while striving for a long-awaited and hard-earned T0.
A successful space launch requires flawless execution of a highly complex machine, and Pegasus ICON is no different. During previous attempts, we observed some anomalous readings. We worked through that with NASA and implemented corrective actions. This will ensure a highly successful mission.
Perseverance is doing something despite difficulty or delay in achieving success. It's a required virtue when the subject is spaceflight and the focus is a successful mission.
Just like any rocket, you have your share of problems that you run into, because this is rocket science after all.
Issues arose, but dedication never wavered. The entire ICON team knew this was about more than just rocket science. It was about the payload, science that would benefit all of humanity. As with every NASA program, giving up is never an option.
It has taken us months, hours, days to really resolve a lot of these issues with this integrated team. And thankfully, we were able to get through them, and here we are getting ready to launch.
The ionosphere is not only the area through which radio communications and GPS signals travel, it's also the space where many critical satellites and spacecraft orbit, including the space station that houses our astronauts. But despite the importance of this region, it is not well known. That's why NASA and the University of California, Berkeley built ICON.
The ionosphere itself, where ICON will be doing most of its work, is where the GPS signals travel through, it's where astronauts travel, and so it's very, very key for us to understand this region because it has profound effects on us here on Earth because of what space weather is doing to us, but it also gets profound effects of what our Earth weather is doing to the ionosphere.
By studying how the ionosphere reacts to Earth's atmosphere, it will help scientists and meteorologists forecast the conditions in our space environment, reducing its negative effects on our technology. From 360 miles above Earth at a 27-degree inclination, ICON will sample ionospheric variations in the lower boundaries of space over the course of hours, days, seasons, and decades. Traveling at more than 4 miles per second, or about 30 times faster than a commercial airliner, this satellite will examine how the ionosphere reacts to our planet's weather.
The ionosphere is highly variable, more variable than we ever expected. Now we think that the answer to understanding the conditions in the ionosphere and being able to predict those conditions relies on our ability to understand how weather below is forcing space weather above. So ICON's built to capture all the information that we think we need to understand the mechanisms and the process by which our lower atmosphere affects our upper atmosphere.
ICON will be sent into orbit by a Northrop Grumman Pegasus XL air-launched rocket. The rocket has 3 solid propellant stages and can deploy satellites weighing up to 1,000 pounds into low Earth orbit.
We selected the Pegasus XL launch vehicle. It provided an excellent combination of mission performance and flexibility for the mission design for a spacecraft of the mass of ICON.
The launch of ICON will be anything but ordinary. It will be carried on the underbelly of Northrop Grumman's L-1011 Stargazer aircraft, a launch pad far above the clouds in the sky.
The one unique thing about Pegasus is that it's air-launched. So the L-1011, which is the last flying plane of its kind, it is essentially our launch pad in the air. It's a mobile launch pad that flies up to about 40,000 feet, and that's where we launch the Pegasus from.
With the tireless effort by the team to reach mission success, it is time for ICON to prepare for another launch attempt.
There are no constraints on the
For all involved, this is familiar territory, yet something feels different this time.
It's taking a little extra time and extra care with the launch vehicle, but we're about there.
What I'm excited right now is that we're getting so close to launch, and it has taken a huge effort to get there.
Vandenberg Air Force Base in California is bustling with activity. The excitement is palpable as ICON literally comes together. Pegasus stages 1, 2, and 3 are assembled. The aft, skirt, and fin installation are now complete. ICON's solar array illumination is tested. And finally, the spacecraft is mated to Pegasus.
Once it's mated to the rocket, there'll be a compatibility test between the rocket
and the observatory. So the rocket will be the interface to communicate to ICON so we can command it. Once we certify that, we will encapsulate it. We'll put it on a transport platform, roll it out to the hot pad, and then integrate it to the L-1011.
Now that processing and mating are complete, the ICON mission takes off from Vandenberg. Hours later, it arrives at Cape Canaveral Air Force Station skid strip in Florida. Important logistics must be coordinated with the 45th Space Wing prior to launch. Once in Florida, there is a week of processing and testing prior to launch day. Lieutenant Samantha Parr is in charge of making sure ICON launches into a safe environment.
So I keep track of the weather, I keep track of our instrumentation, and I keep track of our surveillance. And I provide a recommendation to our Launch Decision Authority, and he or she can make a determination on whether or not we're clear to launch.
We are now at launch day. The team has been here before, and optimism is guarded.
It's been a lot of work to get here. At this point, we kind of see the end, and we're looking forward to a mission and putting the satellite into orbit and seeing what that science does in the future.
Anticipation builds to a fever pitch. All systems are now go for launch.
The actual time parameters for a launch of a Pegasus mission is much different than your standard ground-based missile launch. That's tied to the fact that the Pegasus literally has a first stage by being on an airplane. The airplane's at 40,000 feet, it's moving close to 500 miles an hour. It's moving, you can't stop it, you can't slow it down, it is going and it's dynamic.
The Stargazer jet takes off from the skid strip at the Cape Canaveral Air Force Station.
L-1011 is airborne at this time.
The L-1011 has now reached a cruising altitude of 40,000 feet and has begun flying in a racetrack pattern.
We fly a pattern called the racetrack. It's an oval in the sky, and so the airplane takes off, flies through the launch point at a lower altitude as it's climbing to the point we're going to launch at, which is roughly 40,000 feet.
We verify that all of our GPS are synchronized and ensure that we are going to put the launch vehicle in the correct heading so that we get the spacecraft into the correct orbit.
LC Peg, go for fin pin retract. LPO, go for fin pin retract and fin sweep.
LC, Senior MEVCO countdown, L-1011 is in the box.
About 50 miles offshore of Daytona Beach, the Pegasus XL is released from the L-1011.
With the countdown, we hear drop on my mark, 3, 2, 1, drop. And we push a button in the cockpit. The hydraulic releases actually release the rocket.
Pegasus away.
The rocket drops for 5 seconds, the airplane climbs for 5 seconds, and at the end we have a fairly good safety margin.
5 seconds later, the Pegasus rocket ignites.
Stage 1 ignition has been confirmed.
That's the minute that I consider T0 for me.
Soon after Pegasus ignites, first stage booster burnout and separation occurs.
Stage 1 separation confirmed. Stage 2 ignition has been confirmed and attitude is nominal.
Followed by fairing separation and second stage separation.
Fairing deployment has been confirmed.
After third stage separation, the ICON satellite is deployed into its lower Earth orbit.
Spacecraft separation from the Pegasus launch vehicle. So thank you, old friend, for doing that, and good luck, ICON.
It is a monumental moment for the entire ICON team, who banded together to overcome hurdle after hurdle. Powered by teamwork and unwavering dedication to its mission, ICON has overcome all obstacles in its path on the way to a successful T0.
Well, it's been quite a ride. It's been an incredible journey to get to this point and required the sacrifice of a very large team. We couldn't be more excited and honored to have launched the ICON spacecraft in orbit.
Great job for the team. Congratulations, ICON. status check to proceed with terminal count.
There is a moment at the start of every mission when everything comes together. A moment when years of preparation and planning are put to the test.
Clear to proceed.
There are no second chances.
You have permission to launch.
Success or failure is just a heartbeat away.
Rock report range status. Range green.
A spacecraft and its rocket on the pad, fully fueled and ready to launch.
Status check. Go Delta.
In that moment, a controlled explosion is released with such intense power, it can propel a spacecraft off the Earth and into space for the benefit of all. We call this moment T0. This is its story.
To shed light on the mysteries of our closest star, the Sun.
The Sun, the heart of our solar system. It's as familiar as anything we know. Although the Sun has been studied for millennia, it still holds unsolved mysteries about its effects on our daily lives. To better understand the Sun, NASA is preparing to launch a spacecraft called the Parker Solar Probe. It will lift off from Cape Canaveral Air Force Station near the agency's Kennedy Space Center, located in Florida. It's a mission of unprecedented opportunities that could revolutionize our understanding of our star and the Sun's atmosphere, the corona, a long-time destination goal for scientists such as Dr. Nikki Fox.
Going into the Sun's corona for the first time, going up close and personal with our star, to be able to answer some of the mysteries that live in this coronal region. Why is the Sun's corona hotter than the surface of the Sun? Why is there a solar wind? Why does this atmosphere, this corona, become so energized that it can move away from the Sun at supersonic speeds and bathe all of the planets?
And now that Parker has finally arrived on the Space Coast, we're one step closer to solving those mysteries. Delivered on an Air Force C-17, it's not every day this crew hauls a payload destined for the history books.
Overall, the mission itself is relatively simple. I'd say the biggest challenge is probably the load portion.
A little extra to it too, because normally we're just hauling generic things, but not a $1.5 billion solar probe.
And there's only one world-class program that specializes in missions of this caliber, NASA's Launch Services Program, a team that matches the industry's top-performing rockets with the cutting-edge spacecraft NASA is committed to launching.
LSP is NASA's bridge to space. And basically what we do is we link a spacecraft customer such as the Parker Solar Probe up with a launch vehicle provider such as United Launch Alliance. And we provide them with a custom-built ride to space on a carefully selected launch vehicle.
Engineers and scientists with Astrotech and the Applied Physics Lab teams will spend its last few months checking and testing every element and completing final assembly to be sure it is ready to leave Earth for its epic trip to the Sun. Parker must be perfect before T0 arrives.
Before we start integration with the launch vehicle, we have to do final integration of the spacecraft. That includes attaching the magnetometer boom and magnetometers. We'll then also integrate the solar arrays. And then finally, right before integration with the launch vehicle, we'll add the thermal protection system or thermal shield.
The Parker Solar Probe will be the first mission to kiss the Sun, flying through the searing heat of the Sun's corona, traveling closer to the surface than any other spacecraft before. And to do that, it will need to go faster than any other spacecraft in history. That's why, for the first time ever, NASA's Launch Services Program selected the United Launch Alliance Delta IV Heavy rocket.
Parker Solar Probe will be the fastest human-made object ever. We are traveling at an unbelievable 430,000 miles per hour.
NASA selected Delta IV Heavy for the Parker Solar Probe mission because of the combined energy of the booster, Delta cryogenic second stage, and the third stage, which means that we have enough energy to go to the Sun.
I mean, if you look at the vehicle, it's huge. It's approximately 50 feet wide, 170 feet long, and about 190,000 pounds.
Going out and seeing the Delta IV Heavy on the pad is a truly awe-inspiring experience. Just seeing that amount of raw power right in front of you is just incredible. 3 boosters, our second stage, and then we have a third stage. We're a tiny little spacecraft. We look like a little hood ornament on the top of the Delta IV.
Throughout its 7-year mission, NASA's Parker Solar Probe will swoop through the sun's atmosphere, carrying more than scientific instruments on this historic journey to the center of our solar system. It will also hold a piece of humanity itself. Back in March 2018, the public was invited to submit their names. Over 1 million were loaded into a memory card and mounted on a plaque bearing a dedication to the mission's namesake. Dr. Eugene Parker was a heliophysicist ahead of his time. He proposed this mission back in 1958 after discovering the existence of the dangerous and unpredictable solar wind.
The reason it has taken us 60 years to be able to fly this mission is not because we weren't interested. It really is because it has taken that long for technology to be developed to allow us to do this incredible mission.
During the Parker Solar Probe's perilous dive into the sun's corona, the atmosphere, it will navigate dangers never before experienced by a NASA deep space mission. 3 million degree plasma, sporadic solar flares, and delayed communication with Earth. Traveling this close is only possible because of the spacecraft's protective heat shield, the single largest piece of hardware and the most critical to mission success. One slight error in its performance could cause the probe to melt and the mission would be lost.
Parker Solar Probe is actually going and touching the sun. When we actually get to our closest approach, the heat shield on Parker Solar Probe will be at about 2,500 degrees Fahrenheit on the front surface. The back surface is going to be at about 600 degrees Fahrenheit, but then the spacecraft bus will just be operating at a normal room temperature almost. It's a little bit higher, about 85 degrees. The previous missions have been really important for solar science as we study from afar, and we can learn a lot from studying from afar. But the Parker Solar Probe is actually going and touching, almost kissing the sun, so we can learn so much more.
The spacecraft is now ready for flight, but it can't get millions of miles to the sun unless it gets a boost from a specially made third stage by Northrop Grumman.
The Northrop Grumman third stage team specifically designed and built this third stage for the Parker Solar Probe mission. The Parker Solar Probe needs a third stage because even though the Delta IV Heavy is an incredibly powerful rocket, the third stage is what gets it the extra boost to get into its final orbit around Venus and to the sun.
Parker Solar Probe is the hardest trajectory that I've ever worked on for a couple of different reasons. One, we're flying on the Delta IV Heavy, which is the largest and most complex rocket that Launch Services Program has ever been involved with. And in addition to that, we're flying a third stage that has its own guidance, navigation, and control system on board. So from a trajectory, GNC standpoint, it's like flying 2 missions at once. Parker Solar Probe it's called a heliocentric orbit, which means it's orbiting around the sun. And using a gravity assist, usually we use that to add energy to the spacecraft's orbit when we go out to places like Jupiter or Saturn or Pluto. In this case, we're going in the opposite direction. We're heading inside the orbit of Mercury. The folks at Applied Physics Lab have come up with a very unique trajectory where the spacecraft is going to use the mass of Venus to slow themselves down. And not only are they doing that one time, they're actually going to do that 7 times in a row over a space of 6 years in order to get the spacecraft perihelion, because we're orbiting the sun, down below 10 solar radii. So when we're in orbit around an object, whether it's the Earth or the sun, we go fastest when we're closest to that object and slowest when we get to the top of this orbit. And therefore, when we pass very close to the sun, which is the most massive object in our solar system, we are going approximately 430,000 miles per hour relative to the sun. This really is rocket science.
During the early stages of launch, the Parker Solar Probe will be encapsulated in a large payload fairing. The Delta IV Heavy is a massive rocket designed to launch a school bus-sized spacecraft. The last step at Astrotech is safely securing the 1,510-pound spacecraft in a fairing that, by comparison, makes the probe look small.
To get to the sun, we actually need a lot of energy. Because of that, we need a very large launch vehicle. And in fact, we have the biggest launch vehicle we can get. And because of that, this fairing that is associated with this launch vehicle is very large. But because we're a small spacecraft, we take up a very small amount of space in that fairing. And that's the reason why it looks like we're a very small spacecraft on a very large vehicle. But once the spacecraft is encapsulated, that's it. We no longer get to touch it.
The encapsulated probe is now ready for a slow, steady ride to the launch pad at Cape Canaveral. It will be transported atop a K-Mag made for transporting special payloads. It can hold thousands of pounds, spin 360 degrees, and keep its payload level when traveling up inclines.
One of the nice parts about the K-Mag that we have is it has very precise steering capabilities, and it also has a lot of different steering capabilities. So it gives us a lot of capability to get into a precise location, both for hoisting operations down in the hoistway, as well as different mating operations in our horizontal integration facility.
Now, the ULA team will carefully lift the Parker Solar Probe safely nestled inside its payload fairing to mate it atop the massive Delta IV rocket. To keep the payload safe during the entire lifting operation, there's a special channel constructed in the tower itself known as the hoistway that allows the payload to be lifted without any influence from adverse weather or environmental conditions.
The exciting part about today is it's when we finally get the customer out here, we get the spacecraft hoisted, and that's what it's all been about. A heavy mission by itself is always exciting, but then you add in the factor of having a NASA exploration mission, the mission to touch the sun. That accompanied with the heavy, it's just an exciting launch for the public, a great exciting launch for ULA. It'll be a lot of fun to see, and it'll be a lot of fun to track over the next several years as it gets into its final orbit around the sun.
NASA's Launch Services Program has now brought together the payload and its ride to space. After taking different roads to the launch pad, finally the spacecraft and the vehicle are together.
Goddard runs all of the Living with a Star missions, and this is what's called a flagship mission. It's one of the most important things that our science does. So the anticipation of launch is just tremendous. I've been working on this project for 10 years, and now to see it actually ready to go is just a tremendous feeling. It's really hard to describe.
Now, as T0 is just days away, it's up to ULA and LSP to make sure they're operating as one. In the hours before liftoff, the mobile service tower gantry rolls back, leaving the mighty Delta IV standing on its own, ready for launch. The final countdown to T0 is underway.
As the NASA launch director, ultimately what I do is give the go or the no-go. That's a very simple statement, but there's a lot that goes behind that. It's a culmination of a bunch of professionals that know their jobs, they know it well, and all I have to do is make sure all those pieces are in place. Then it's easy for me to make the decision to launch.
Thousands of rockets have launched from Florida's Space Coast, but this is the first designed to fly to the sun. Big Delta IV Heavy rocket is ready to roar to life with more than 2 million pounds of thrust to power the Parker Solar Probe on a trajectory of millions of miles to its destination.
Proceed with terminal count. First stage systems. Propulsion. Go. Hydraulics. Go. Locks. Go. Launch director. You have permission to launch. Status check. Go Delta. Go PSP.
3, 2, 1, 0. Liftoff of the mighty Delta IV Heavy rocket with NASA's Parker Solar Probe, a daring mission to shed light on the mysteries of our closest star, the Sun.
All 3 RH-68s look good in the full thrust mode. Response looks good. Vehicle trajectory looking good, right down the middle of the range track.
And as we leave the moon, we leave as we came, and God willing, as we shall return.
You probably dreamed of this.
Liftoff on Apollo 11.
You probably replayed this moment 1,000 times. You probably imagined the awe-inspiring, indescribable rush of the ride. You probably celebrated the miraculous, cheered the momentous, and mourned the shocking. You probably still dream of what could be. We did. We do. And while many thought we were through, no. We've been learning, we've been building, we've been training. And now, it's time. Because the next frontier is not just for the next generation. It's for this generation. It's for me, and it's for you. For everything we still dream about. We go as Artemis.
It's a new era of pioneers, star sailors, thinkers, and adventurers.
3, 2, 1, 0. All engine running.
Let's go.
We have been given the scientific knowledge, the technical ability, and the material to pursue the exploration of the universe.
Welcome to NASA Edge.
An inside and outside look at all things NASA. And today we're going to be talking about the Artemis 1 launch, a very important mission for NASA. We're going to be talking in specific about imaging the Artemis 1 on launch. Later on the show, we're going to be joined by Jennifer Inman and Franklin Fitzgerald to talk even more about this important process.
Blair, we're not talking about our imaging like with the cameras that we have around here. We're talking about professional imaging.
And that brings us to Tom. Tom, we've worked with you for years, but you've been imaging the shuttle for a long time, back in the later aughts, but then you've moved on and grown this technology to image now Artemis. So tell us, what exactly is SciFly?
Well, so SciFly, we're actually going to be implementing a special imaging system on the nose of a high-altitude WB-57 aircraft. It's a special imaging system we call SAMI. This particular instrument is designed to measure the temperatures of the core stage of the rocket during ascent. We won't be able to recover our core stage. It has instrumentation, but it's limited instrumentation. So this is a very unique opportunity for the engineers at Marshall to better understand the environments of the base region of this rocket. This is where all the critical avionics hardware is housed and that control the rocket nozzles during its initial stages of flight. So it's very important we understand how well that avionics are protected.
Now, as I think about SciFly, I'm thinking SciFly, scientifically
calibrated in-flight imaging.
Right, so it is clearly, Chris, all about this important imagery.
But the cool thing about it is you have developed this technology or this capability since, what, 2003, 2004?
Goes back to 2003, Chris. I was involved with the Columbia accident investigation, the return to flight. I was part of a group of engineers that had to use tools that we developed on wind tunnel data generated here at Langley to disposition damage on the shuttle that occurred during launch. So the aerothermodynamic community that I'm involved with, we kind of rallied and advocated for an experiment to be flown on the shuttle. We simulated damage by placing a bump on the underside of the wing. Protuberance in a safe location to better understand the temperature environments during reentry from that localized heating created laminar turbulent flow. But you don't see it with your eyes, but an infrared camera, you can see. Now, we do these kind of things in the wind tunnel all the time. We have, scale models like this, infrared camera, looking at it optically, 3 feet away. So I asked myself, the challenge here was, could we do the same kind of thing in flight? It represented a paradigm shift. We traditionally collected data with instruments on the vehicle, thermocouples. But could we look, with the orbiter flying, 50 miles away, track it and get a global snapshot.
At high speeds, too.
At high speeds.
Don't blink.
I mean, we're talking anywhere from 18 to 24,000 miles an hour?
24,000 miles an hour, yes, sir. So it's very tricky. It's a very tricky process to, track that vehicle, acquire it, track it, and maintain it in the narrow field of view and get that temperature image that the engineers were seeking. So we did that successfully, for 7 shuttle flights.
And now you've expanded this capability to not only you can observe vehicles coming in, re-entering the atmosphere, land-based, air-based, and ship-based,
So,
right?
yeah, so the photons, they tell us a very unique story. I mean, what we've been talking about here with the shuttle was, infrared imaging for temperature retrieval. But the photons also tell us in the visible spectrum, like with the work we're doing with the Commercial Crew Program, the commercial partners returning their capsules, back from space. The SciFly team was an integral part of that development and validation process associated with those parachute recovery systems. In that case, aircraft and ground systems were used simultaneously to obtain the critical data, the health monitoring of these parachutes to make sure that those last phases of entry, descent, and landing, the descent and landing occur as we were expecting.
It's one of the most critical parts of the mission is EDL, right?
Yeah, I mean, you would think in my discipline, I've always had the perception that, the high temperature aspects of reentry were, the critical parts, but actually my understanding now is that, the parachute architecture, that's one of the leading risks. And hence the agency put a lot of effort to ensure that we had a safe design for those commercial systems.
I think what's interesting is that what you did back with the shuttle program, with the imaging on the protuberance, that whole process, you learned a lot. And then now, because of the good data, because of what you discovered, has now found a place in almost all aspects of launch and landing.
We support multiple mission directors, actually, and we've been talking a lot here about the human exploration side. Right. But we've also supported a lot of planetary science missions, so things coming back from, asteroids, the heliophysics, launches from Wallops that we've supported with optical imaging. So it's really, the team has really broadened its base in terms of, going from just initially supporting thermal imaging, and now it's pretty extreme range of capability that we've developed for the agency.
Tom, you've built quite a team. In fact, we're going to be talking to Jennifer later on in the show.
Thanks for being here. We did have a chance, however, to travel to Houston, Texas to talk to the team developing the SAMI instrument for SciFly and getting it ready for the Artemis launch.
So Matthew, we're here at one of the labs at Ellington Field, and the star of our show, SAMI, is directly behind you. Can you tell us what does SAMI stand for?
So SAMI stands for the SciFly Airborne Multispectral Imager.
And what will this instrument do?
So this is an imaging payload that measures different wavebands of light, some bands that we can see, some bands that we can't, in order to try to obtain scientific imagery for launches and reentry missions, in addition to other support that we may provide for NASA commercial crew program.
So SAMI is being used with the WB-57. Why is it being used with that airborne platform?
So the WB-57 is an airborne asset that we actually use quite often for both launches and re-entry imaging missions. The reason that we do that is because it is a high elevation asset, meaning that we can get higher above more clouds than most of the other aircraft that we have access to. In addition to that, we have a breadth of knowledge of conducting these airborne missions with the WB-57. We have a lot of support through both NASA and some contracting companies that were able to help us develop the system. And really, it was the most difficult environment that we could have developed this in. So moving on from here, we'll be able to apply it to, different aircraft, even put it on the ground or even on a boat in the ocean to collect imagery.
So how will SAMI be operated during the Artemis launch?
So for the Artemis launch, the SAMI payload, which is what we call the whole system with all the imagers inside, will be placed inside of a ball turret on the nose of the WB-57, which has 2 rotational degrees of freedom, which will allow us to point it at the Artemis as it launches, and it will be operated from the rear seat of the jet. The person in that seat we call the Special Equipment Operator, the SEO.
Prior to SAMI, you had a similar instrument called Dynamite. How different is SAMI from that instrument?
So the Dynamite payload consists of 2 imagers, one visible and one mid-wave infrared. Both of them are capable of zooming in from very close to very far away. And the difference between that and SAMI is SAMI actually has 6 different cameras on board, 4 of which are a constant field of view, constant zoom. And the other 2 are wide to narrow zoom cameras that allow the SEO to accurately and quickly acquire and track any object that we wish to view through the camera.
Now, acquiring and tracking the rocket or capsule for a launch or reentry is totally different. Can you tell us about that procedure?
Yeah, so for launches, obviously the rocket is sitting on the ground right before it takes off. So as the WB actually approaches its planned flight path, the WB can acquire the rocket on the pad and continuously track it as it launches off of the ground. So the initial acquisition of the target is actually is much more simple than a reentry mission, because in a reentry mission, you actually have to find a much smaller vehicle in the sky as it's coming toward you, or as it were traveling across the sky at a much greater rate of speed. It's much smaller, much further away than for launch missions. So what we tend to do is we actually give them what's called a horizon break, which gives the first point in time when the WB should actually be able to see the capsule as it comes across the horizon. And that way they can point in that direction with a wide field of view, acquire that, and then zoom in with that to punch in the narrow field of view sensors.
So SAMI will be used to image the Artemis launch and re-entry. But beyond that, what are the plans for SAMI?
So SAMI was designed to be a very flexible imaging asset. Because of its unique capability for multispectral imagery, we've actually designed it in such a way that we can install it on a wide variety of NASA assets. Ideally, what we would like to do is develop the interface to install the SAMI system onto one of the Gulfstream aircraft and take it with us to image the OSIRIS-REx mission that's upcoming in our schedule. This is a very unique opportunity due to the high heating rates that we'll have, and we'll actually be adding some future capability to SAMI to do that.
Very interesting information on SAMI, but right now we'll learn a little bit more about SAMI and SciFly from our next guest, who is Dr. Jennifer Inman. Jennifer, can you tell us about your role as a project manager and the other assets you have in SciFly?
Absolutely. It's nice to be here with you guys today. We're really excited for Artemis launch, and we're going to be there with all of our bells and whistles. We've got 2 ground-based imaging systems that will be on the Cape at Kennedy Space Center, imaging the launch, and we'll have an aircraft, the WB-57 that you've heard about, flying during launch, and we'll also have Sammy on the WB-57 when Orion returns at the end of the mission.
Pretty complex stuff you guys have going on here. But one of the things I'm wondering is, when we talk about data, because we often talk about collecting data and gathering lots of data on any given event or during a launch or something like that, what exactly is the data that you guys will be getting that's so important during Artemis 1?
Oh, I like questions like this. On our team, we like to talk about how it's important to actually get information rather than data. If you get data but no information, then you've just filled up hard drives. So the type of information that we're trying to get here directly addresses some of the requirements and the science requirements for launch and some of the engineering requirements to certify the SLS system and the Orion capsule for human spaceflight. So some of the questions that we'd like to answer are whether the separation dynamics with the solid rocket boosters are as we expect them to be. We'll get that from our high-resolution airborne imagery. We also are looking to answer questions about the thermal protection system and to see what types of temperatures are achieved on the vehicle. So one of the temperatures we'll be looking at is the temperature of the outside of the core stage of the rocket. There's a phenomenon called plume-induced flow separation where you get a shock wave ahead of the rocket plumes that can cause hot exhaust gases to be entrained in the boundary layer flow and creep up along the sides of the vehicle. So we'll be looking at what temperatures are achieved there on the outside of the vehicle. We'll also be looking at the core stage, at the base of the core stage. So SLS has 4 rocket motors, and we'll be looking at the region between those 4 rocket motors to see what types of temperatures you get when the hot exhaust gases are entrained into the flow at high altitudes where the pressure is lower. And so we want to see whether the thermal protection material that we have in that region is adequate, or even if it's more than adequate and we can shave some weight off for follow-on flights.
Well, it's interesting because obviously SLS will have some kind of internal sensors itself collecting some of this data. Are you guys targeting gaps, or are you working together with them on maybe where they could use some more data? How does that work?
Oh, really good question. We definitely see our off-body measurements as complementary to the onboard instrumentation. So onboard instrumentation on the surface of the vehicle gives you discrete measurements over the full flight profile. We'll be getting global measurements over a more reduced set of the flight profile. Every pixel of our thermal imaging basically acts like a thermocouple in that location where we can measure what the surface temperature is. We're also subject to very different failure modes from onboard instrumentation. So, we might fail to acquire data, as an example, if something happens mechanically with the aircraft that causes it to return to base or not be able to take off in the first place, or if clouds block our view of the rocket at some point during the trajectory. On the other hand, onboard instrumentation can have different failure modes due to electronic failures or things like that. So they definitely go hand in hand, and we can independently measure the same variable that we're interested in and see what answer we get from the onboard instrumentation and what answer we get from the offboard instrumentation and make sure that they agree.
That helps you kind of calibrate either way, right?
Absolutely, yeah.
Now, you talk about the onboard instrumentation. Is there any redundancy between the WB-57 and your ground-based assets?
For this particular mission, we are not getting calibrated thermal imagery from our ground-based assets. That's something that requires additional funding that we weren't able to secure this time around. But we are able to get really high-resolution imagery from our ground-based assets because you can use larger optics. And so the types of quantitative information we can get are related to subsystem performance. We can look at the timing of events, and we can see details of things that happen. We can also, if anything anomalous happens, we'll have high-resolution, high-speed imagery to see what happened there. And we have different views. We have 2 ground-based imaging systems, and we have the airborne system, and they'll all be looking at the rocket from different perspectives. So that way we'll be able to see what happens to components like the solid rocket boosters from 3 different perspectives.
It's funny, everybody's excited about seeing the Artemis launch. Even your assets are like competing for space to image the launch. It's very exciting. Yeah. In fact, we had a chance to actually talk with the crew of the WB-57 as they prepare to image the Artemis on launch. Let's check it out. DJ, as pilot for the WB-57, you fly a couple of different kinds of missions for SciFly. You cover rocket launches and reentries. Can you tell us a little bit about the challenges for a rocket launch?
Yeah, both have their own unique challenges, but I'll tell you, from the pilot perspective, it really comes down to putting the aircraft in the right spot at the right time, because they both have very specific timing requirements for the sensor equipment operator.
Now, I've seen a few launches, and I've noticed that they don't always happen at the exact time. So what do you do when you find yourself in one of those situations where there's a hold or there's a delay or something, and yet you still want to be in position to get the imagery?
Yeah, that can definitely present a challenge for us. And what we do is we have a bunch of different ways that we can solve that timing problem by extending our holding pattern, shortening up our holding pattern, working airspeed. So we use all of those tools in order to try and, like I said, get that aircraft back in the right spot at the right time.
Tony, DJ told us about the challenges he has of putting the WB-57 in the right spot. What are your challenges as operator for SAMI?
Well, my challenges start from the time it was being developed and getting to know the system. But then in the flight environment, I've got to worry about the focus, the framing of the image, and then tracking the actual object itself. So you've got to handle all of those things at the same time while maintaining situational awareness, and if anything comes up that you have to then adjust to.
And of course, in a rocket launch in particular, you start knowing exactly where it is, but then it moves pretty rapidly. What's that process like tracking a moving object at that speed?
Well, one of the good tools that we do have for this is we've got a trajectory that's the nominal path of the rocket, and that helps guide us. So if we do lose it in the clouds for a little bit before it gets up above those, then they can keep us in the right vicinity. I know where to be looking, and it goes from there.
So I imagine that you're in communication with the ground quite a bit ahead of the launches and reentries, but also throughout the whole mission. Can you tell us about that?
Yeah, absolutely. Throughout the entire process, we have our own designated Capcom, and those folks will go ahead and let us know how the countdown is progressing. If they're anticipating a hold, we can start to work the timing problem early, because as a jet aircraft, we can't just hover, and we have to keep moving and, again, get the aircraft back there when it's time to push.
Now, there are also challenges on reentry. We had someone describe it as if you were looking through a straw trying to track an object in the distance. Tell us a little bit about how you acquire these objects as they're coming in at very high rates of speed.
Well, we start out with a wide straw, and then we use a more narrow straw later. The greatest thing we have for the reentries is the mid-wave infrared, which is just all about the heat and the signature there. It stands out against the cool night sky very well. And so we use that, we use a wider field of view, and then we zoom our cameras in to get the scientific grade imagery. By the time it gets closer to us, it winds up being about 5.5, 6 miles away when the key stuff happens, as opposed to 1,000 miles away when it comes over the horizon.
And of course, that's a little bit more challenging because it's coming from outer space. And it's a little, I know you have some information, but are you all nervous trying to make sure you get it right when it's visible to the human eye, or to Sammy's eye in particular?
Only every time.
Yeah.
Yes.
Safety is also a big priority, and you're flying during very dangerous activities. And so tell us a little bit about what's required for you guys in terms of safety.
Yeah, the big thing with the safety is that all is part of our mission planning process. We work with the experts to make sure that we stay out of the hazard zone if something were to go wrong during the launch, or a reentry also. We make sure we keep the aircraft out of that hazard zone. And again, we're also in communication with the ground, and if they see something going wrong, then we can make sure we turn the aircraft out of the way to keep ourselves safe.
How do you test something like SAMI? Because the opportunities for launch and reentry are so rare, you got to be on your A game. So how do you prepare to nail it each time?
Well, for launches, we are looking at some targets of opportunity, some other launches happening in the area or on the Cape that we can go and image as part of the training process. For reentries, that's pretty much a one and done. Nobody wants you to go and practice against their reentry, especially if it's an operational mission with a developmental payload. So we've really got to develop the tools that we've learned in other payloads, like the dynamite payload, and we're going to use those same tools and techniques against SAMI, and we know which benchmarks to expect before we say, all right, SAMI's ready for that job.
Now, Artemis 1, pretty special. And I know you fly a lot of missions, but how does it feel to be part of NASA's return to the moon?
Yeah, it feels awesome to be a part of that. And the biggest thing is we never take a rocket launch for granted, and we always know we have the best seat in the house. And again, it's an awesome experience. Yeah.
It seems like one of the big challenges for SciFly and anybody studying these kinds of operations is the fact that you don't really get practice. This is a one-time opportunity, but it seems like each opportunity is very unique. How much data do you have to compare with on something like an Orion reentry?
Well, you certainly hit a nail on the head there. We like to say there are no do-overs in spaceflight. Or one of our providers says, every day is Super Bowl Sunday. And so the real key is planning. We do a lot of planning ahead of time. We do a lot of simulations where we walk through timelines and we practice the call-outs that we're going to make. And we practice adjusting our trajectories, if the deorbit burn happens a little bit differently than expected. So a lot of this is planning ahead of time, knowing where the aircraft needs to be, knowing what to do if the trajectory of the capsule changes in real time. We do a lot of simulations as well on what we expect to see. So we take a model of the vehicle and we put it into a 3D rendering environment, and we model our sensor system as well. And we model things like the temperature of the vehicle and the number of photons you expect to be emitted based on the emissivity and the material properties of the surface. And all of this tells us what sensor settings we should have ahead of time, because you don't get to adjust your exposure time in real time. So if you have the exposure time too long, it could be saturated or underexposed, you're just not getting enough light. So we simulate an end-to-end mission in order to maximize our potential for success.
Do you feel any pressure?
Absolutely. There's definitely a game day feeling that's energizing and requires a great deal of focus. It's kind of a different level of consciousness that you operate in when you've got your astronaut socks on. That's my game day tradition, is to wear my astronaut socks. And you get your game face on and get focused on the mission at hand.
Well, we want to wish your team the best during launch and recovery, and just thanks so much for being on the show today.
Oh, it's been great. Thank you so much, Blair, Lincoln.
You're watching NASA Edge.
An inside and outside look at all things NASA.
Humanity has always been interested in exploration. If we really want to go to the moon, we have got to figure out a way to keep our propellants cold long enough. My name is Monica Guzik, and I have the coolest job at NASA because I work with cryogenics. Cryogenics is the study of things at very low temperatures. We've got electrical connectors we can plug into. So we want to store things like oxygen or hydrogen, but if you store them as a gas, the only way to get a whole bunch of molecules in there is to raise the pressure really high. So instead, if we make them really, really cold, they turn into a liquid, so they're way more efficient to store. So this is gonna be a liquid oxygen test. I always knew I wanted to be an engineer since I was a little girl. My dad was an engineer, and I just thought engineering was so cool. We were gonna put insulation over this. Ended up getting a summer internship here at NASA Glenn Research Center in Cleveland, and just really sort of fell in love with NASA. Cleveland is the rock and roll capital of the world. I really enjoy rock and roll music, so I try to go to a lot of concerts. When we improve cryogenic technologies for space applications, it always has a trickle-down effect to the Earth. Now we're rolling into the Artemis generation, and we're still doing that.
Hello everyone, I'm astronaut Randy Bresnik, living and working aboard the International Space Station. Now, on the space station, we live in a microgravity environment. Do you think the laws of physics will hold up? Come on, let's go find out.
The acceleration of an object depends on the net force acting on the object and the mass of the object, or F equals ma.
Surely good show, Sir Isaac.
Here we see that once the force of the thrust is greater than the weight of the vehicle, the rocket begins to accelerate.
All right, we're going to start with something small. Something you might have at home. A little stick of chapstick. We'll go ahead and use our force being our bungee cord here. We'll put it on our bungee, and we'll pull it back. And let it go. And you can see how fast it accelerates because there's very little mass. Next, we'll try a little spaceship. little more massive, and you can feel that because as you move it, you can feel that the kind of the force, the extra force you have to push with your hand. So we'll put our spaceship on our launcher here, same spot. Notice it's flying a lot slower than that chapstick did. What we've seen is the same amount of force on a smaller, less massive object means the acceleration is faster. Well, this is the biggest and most massive thing we have. So let's see how the acceleration is affected. Pull back the same amount on the force, and here we go. And there you have it, Newton's second law of motion in action. Thanks everybody for exploring a little physics with me today. Now I'm going to send it back to Earth so you can start your experiments. See you again real soon.
Mars is orbited by two moons, Phobos and Deimos. Phobos has a diameter of approximately 23 kilometers, while Deimos is just 13 kilometers across. The two moons were discovered in 1877, but their origin remains unknown. Observations of the moons suggest the pair resemble asteroids. With gravity too weak to create a spherical shape, the moons have an asymmetric, lumpy structure. The moon's surfaces mainly reflect long-wavelength near-infrared radiation. This is similar to D-type asteroids, which sit in the outer part of the asteroid belt that orbits the Sun between Mars and Jupiter. This has led to the idea that the moons might actually be asteroids that were scattered towards Mars and captured by the planet's gravity. But not everyone agrees. Captured moons normally orbit a planet on inclined or elliptical orbits, but Phobos and Deimos have near circular orbits around Mars's equator. A second possibility is that Mars's moons were formed during a giant impact with the planet. Debris from the collision would be thrown into orbit and coalesce into the two moons, both orbiting in the same plane. JAXA's Martian Moon Exploration Mission will be seeking the answer as to how Phobos and Deimos were formed. The spacecraft is carrying instruments that can examine the composition of the two moons, including those developed by the French and US space agencies. If the composition of Phobos and Deimos is similar to that of Mars, the two moons were probably carved from the Martian surface during a giant impact. But if the moon's composition is different from the planet, then they likely formed in a different part of the solar system and are captured asteroids. You can follow the Martian Moon's Exploration Mission on our Twitter feed and website.
We're excited to see what kind of data that we collect from this first project. Any sort of data we get is going to be brand new information for us and for
Three, 2, 1, and 0. And a liftoff of the Falcon 9 rocket and the Dragon spacecraft, packed with science and supplies for the International Space Station, humanity's home in low Earth orbit.
So we were originally scheduled to be on SpaceX 14, but about a week before launch, our project got canceled from that launch because of some issues with the controlled environment.
Science in space can be complex, and no matter how meticulously things are planned and executed, sometimes those complexities get in the way of launching on time. When equipment used to house the experiment didn't look perfect for a final pre-flight test, there was no choice but to push it to a later flight to ensure mission success.
As a first-time investigator, that was, it wasn't devastating. It was just sad that we weren't going to be able to launch because up to that point, it had taken us about 2 years to get there. Ultimately, it gave us about 6 months more time to reevaluate that controlled system and do some more groundwork to prepare for the launch in December of 2018 on SpaceX 16.
After the setback of being moved to a later launch, our team of scientists now has only days left before their experiment will be loaded into a SpaceX Dragon capsule that will carry it to the International Space Station. Elaine and Parastu, the co-founders of a biomedical startup, are at NASA's Kennedy Space Center, readying their research for microgravity.
Since this is our first project that's launching to station, this is also our first time working at the Kennedy Space Center. So it's been an exciting moment to not just see the visitor center, go look at the touristy things, but also get past the security gate and into the actual laboratories.
While some experiments are loaded into Dragon in the weeks leading up to launch, others have more time-sensitive components. These require precise preparation and loading in the days before liftoff. For those scientists, laboratories at the Kennedy Space Center that are a part of the Space Station Processing Facility, or SSPF, become a home away from home. Here, they can carry out the critical last steps of preparing their experiments for delivery to the space station.
So we got here on a Thursday, and it's currently Sunday. Put in a big day yesterday filling up these wells with gel solution and getting ready for handover at 7:30 a.m. on Monday, ahead of launch on Tuesday afternoon.
Once you arrive here, you kind of get into this other time. It's this weird little time bubble where everything is now L-based, and L being launch, and it's L minus 72, L minus 48, L minus 24, and it's just building up to the actual launch time.
With those precious remaining hours, the team is prepping their microplates for microgravity. Microplates are also used in labs on Earth, but these were specially designed to be self-contained.
My role on the project was to design the actual microplate themselves. The challenge on orbit, though, is that generally fluid experiments have to be conducted in the glove box, and the glove box is very time limited. It's very crew intensive. So we've designed this self-contained microplate that can be operated outside of the glove box. It has all of the containment to keep the fluids inside.
So we have loaded these wells with hydrogels that they were carrying drugs, and we want to actually look at the effect of microgravity and how the release of the drug is affected when we send it to the space station. So the concern that we have is that if we have bubbles that are in the wells, it may be difficult for the plate reader to be able to read the amount correctly. So we are being very careful with how we are loading the waters.
So what's left to do today, once Parastu here finishes filling the microplates, I'm going to take over and seal them up completely. Once that's done, we'll add all of the labels onto the microplates and put them in a self-contained box that is what they'll actually travel to the space station on.
3 years in the making just to get here.
Once we do that, we'll turn it over to Cold Stow. Cold Stow will take it from there, and the next time we'll see them, we'll be on orbit, and the crew's opening them up.
Cold Stow, short for cold stowage, is the team responsible for making sure that the research stays at the right temperature on its journey from the lab on Earth to the lab in space. This handoff is one of the last steps before being loaded onto the rocket. The cold stowage team will take Elaine and Parastu's experiment and keep it safe and sound before it's loaded for launch.
Does it feel like a relief?
Well, it'll feel like a relief when we actually see it take off. And then it'll be finally...
It's a huge step though.
Yeah.
It's done. It's out of our hands at this point.
Yeah. That'll be officially out of our hands when it leaves the Earth's surface. So that'll be the moment that we're finally done. Until we get data, and then we get to process it.
That's just the beginning, actually.
So what'll happen now is, now that we've handed them over to NASA, NASA will deliver, they're on their way right now out to Dragon to be loaded. And the launch hopefully will happen tomorrow at 1338. I've been involved since the very beginning, which is approximately about 3 years ago. It's been a long road, but like everything, it's a lot of work. It's worth it. And we're excited to help Timpanogen and get some data for this project.
Overall, we're going to get a lot of data from just this one project and those 2 experiments that are going to inform a lot of different things for us. All right.
It's a little windy out here today. It's a beautiful day. It's a little windy. It's got me concerned. My launch intuition is tingling a bit. It's always an awesome and amazing and special thing to see. It's the launch day. It's a little windy out here today. It's a beautiful day. It's a little windy. It's got me concerned. My launch intuition is tingling a bit. I grew up here in Florida. I came to this very spot out here in the Causeway as a kid. My dad would take us to launches all the time. So personally, it's like the kid in me comes out when I come here. It's really cool. I've been on both sides of it. I've been a researcher, and then I've been now helping researchers. And I got to say, it's nervous on both sides. You have a lot of worry, I guess, as a scientist. You have a lot of work involved. As a payload provider, you hope you've checked all the boxes and you've done all that you can do to make everything work for the researchers so that they get good data. It's not easy to put even the most simplest payloads on the space station, but it's worth it. It's worth all the work. I think some of the biggest discoveries we've made and are going to find are up on the space station. It's incredibly important.
Well, we've been really nervous all the way up until right this moment. Nervous that our dreams aren't actually going to happen. But now that the larger countdown is happening and the rocket's all fueled up and everything looks like it's going to happen on time, it's getting really exciting. The last 15-minute window before it takes off. Thanks to Cases for funding this, thanks to Nanorax for helping us coordinate and making the hardware and coordinating all the data collection too. And thank you for the astronauts who are going to be working on this project on station. So a lot of people worked on this. It's not just the 2 of us. It's been a lot of people. So we really appreciate all their support.
7, 6, 5, 4, 3, 2, 1, 0. And liftoff.
As Falcon 9 and Cargo Dragon take flight, bound for the International Space Station with fresh supplies and research, helping to maintain our human presence in space as the station celebrates its 20th anniversary.
It'd be incredible just to watch it no matter what, but knowing that we have a personal investment in it makes a big difference.
Yeah, so it's just knowing that something that we've been working on is on it, and then watching the whole experience makes it just different. It really, I can't find the right words to explain it. Really,
definitely feel like the work leading up to it was worthwhile.
Yeah, absolutely. And watching it with your best friend.
Yeah.
And like someone that you've been working with for such a long time, and it's just, I think it couldn't get better. That's what I can say. Yeah. I didn't want to do it with anyone else.
Yeah, that is the exact same sentiment that I have too. So it was really special that we could both be here.
Yeah.
And watch it together.
Our scientist experiment is officially on its way to the International Space Station. The SpaceX Dragon capsule that gives the research its ride to low Earth orbit now must make the last leg of its journey to the hands of the astronauts in microgravity.
What's neat for us is we've got cargo vehicles coming and going to the ISS all the time. It is really like a busy parking lot. Vehicles come in, they stay for a few months, we do a whole bunch of science, and then they leave again. And before you know it, the next one's coming up. Now, what's important to remember is that these vehicles cannot dock themselves to the space station. We have to bring them into the space station utilizing robotics. And what I like to tell people is performing robotics, going out and capturing that vehicle is like a really difficult video game. And so we practice over and over and over again using computer simulations on how to actually capture that cargo vehicle to bring it into station. Once that cargo vehicle docks to station, we do a series of pressure checks and equalize that pressure with the International Space Station, and finally we get to open the hatch. Very quickly the crew starts to move because we've got some experiments that are actually kept at certain temperatures, and we have to transfer them quickly out and keep them at the same temperature there on board the space station.
Elaine and Parastu's research is one of the experiments that requires quick unloading. Stored at a constant temperature to ensure the hydrogels stay intact, it's one of the first items that astronauts must remove from Dragon. Then, with the experiment finally aboard the space station, it's time to conduct science in microgravity.
This was fantastic for me. This is what I do. This means a lot to me as a clinician. And so it was really neat to be able to perform that sort of science on station.
So station 1002 is loaded.
Choose your lettuce leaf. Cheers. Cheers. We get balsamic? Oh, that's pretty good.
Wow.
It's a salad. It's a salad. JC, that was delicious.
Feel, Serena, that sounds great.
Well, when you haven't had a salad in 6 months, it's delicious.
I'm still station on 2 for Nanorax.
With you on 2 for Nanorax.
Right, how's your view? Do you want anything different?
View looks great.
No, the view looks great, thank you.
Now that the experiment is aboard the space station, it's time for the astronauts to get to work. Elaine and Parastu are back in Virginia, and the Nanorax team is back in Texas, where they will perform a ground control version of the experiment being conducted by the crew in space.
The crew members are using the Nanorax plate reader to read the plates. They're analyzing what's in the plate and the migration of fluids between the 2 chambers that are on the plates. And so we have our ground samples here. These are identical to the ones that are on the space station. And what we're going to do is, as the crew members insert the plates into the plate reader on the space station, we're also going to insert the plates onto the ground unit we have behind me. And that's just to confirm that what we're seeing, any effects that we do end up seeing, is effective the space environment compared to the ground unit. In summary, what the plate reader does is, it's called, the big fancy word is a spectrophotometer, and it's got a big lamp in it that shines white light, and then it's got a prism or a grating. And the white light shines on the grating, and then it moves to orientate to kind of separate the light into a wavelength. And you get to select which wavelength you want to shine through your samples. We have 6 plates. Each plate takes about 4 minutes, so it's about 30 minutes each. And every time in between, we'll be listening for the crew member to say that they inserted the plate. Then we'll hit the command here. Once the run is done, the crew member will come over and take the plate out, put the new plate in, and it'll repeat for 5 more times.
Still station on 3, plate 1003 is in the tray.
Oh yeah, it's reading the plate. It's got a little, the plate sits in there, moves the plate this way, and then the read head moves this way. And a little here, that's kind of the lamp that's in there that turns the lamp on. Sounds like bad techno music.
My crewmate actually was the first one to start this experiment, and I took over for him and said, hey, what experiment is this? What are we doing? And he looks at me and he says, I'm not sure. So we called down to the ground to mission control.
And I know that part of this is we're looking at a gel that can release antibiotics, kind of slow release to a wound site. But I don't know what happened to that plate in the NanoRax reader this morning, and then kind of what's going on this afternoon.
What we're looking for is how the drug migrates through the gel over time, which is why we're scanning the plates 2 times a day for this 2-week run.
I like that answer. That's very cool. Thank you for finding that out.
No problem.
So this is 15 days. It's twice a day, and they're typically in the middle of the night, which is the morning for the crew on space station, and then usually sometime in the late morning, early afternoon here. But Kyle's been running the show. He's been getting up every 6 hours, 8 hours, 7 hours to do this. It's kind of fun in a way. I get to play astronaut on the ground, so that's always fun.
After 15 days of running the experiment, the researchers have a lot of valuable data about how hydrogels behave in microgravity. To learn even more, the samples will come back to Earth for further analysis. For the last leg of their journey, the samples will return to Earth in the same Dragon capsule that gave them a ride to microgravity. After Dragon splashes down in the Pacific Ocean, it's taken to the port of Long Beach, where NASA will be ready to retrieve the precious cargo.
Splashdown for Dragon was on the Sunday, I believe. And so NASA has a group called Cold Stowage and Cargo Manifest, and they go out and pick up the payloads from Dragon. And then they distribute it to people at LA or whoever needs them there, and then they bring them also here to Johnson Space Center. And so now I'm out front at the Cold Stow office, and I just picked up Module 74, which is our Tympanogen project. And they hand it to me, and I put it in my cooler, and then I drive it over to our office, where it's going to sit until we fly up to the Tympanogen office in Richmond, Virginia, to do the final phase of the experiment, which is removing the samples out of the reactor microplates. We're really proud to take part in this really interesting experiment.
When we first got our gels back, it was already exciting because space never loses its cool, and so we had these places where, oh my god, these are what the astronauts touched. And so we opened up and they've been to space and back, and now they're in our lab.
My younger son, we actually came into this room years ago, and he was probably 4, and I put on my helmet on him and put my harness, and it's dragging on the floor, and he looks at me and goes, "Look, Daddy, I'm a test pilot."
Put this side in first.
I'm Nils Larson. I'm the chief test pilot here at NASA Armstrong. It really came when I was probably a junior in high school, maybe a sophomore, and one of my teachers handed me a book, and the book was The Right Stuff. I knew I kind of wanted to be an engineer or a scientist, and I read that and I went, wow, this would be cool. You could be both an engineer / scientist, and you could be a pilot. Best of both worlds. How cool would this be?
Roll 3, 2. Copy, Mark.
The test pilot answer is my favorite is whatever I'm flying today. So I just got out of the F-18, so that's my favorite right now.
Well, the role of the test pilot is to pull it all together in the air. Our mission here, our objectives are testing science and technology through flight, in flight.
Let's see, flight objectives, basically the biggest thing is to try and get this instrumentation worked out, you know, be able to compare it to the airplane and to what's being recorded on my chest. Mission security, mission rules, go, no go. We talked about the 40,000 foot, probably the biggest one. So we'll go to 39,999 feet. Let's see.
Keep me on my toes.
Yeah, exactly.
Okay. You got your helmet? Okay, I'll give you the rundown real quick, and then we can go out there and do what we gotta do.
Well, what we do is our initial concern is to give the pilot a safe and reliable aircraft for his mission. Once we've achieved that, then our next concern becomes the science and the research folks that are going to be associated with the airplane. So if they've attached an experiment or they're looking for specific data, we work with them to make sure that their equipment is working the way it should be and that it gets them the data that they're looking for.
You know, for us here, we work a lot more with a project. We're doing, you know, sometimes we call it weird things with airplanes. So rarely are we going to point A to point B, or if we are going point A to point B, we're going up and down and up and down and up and down the whole time when we're going there. And our job is to try and get the people the data.
Fan of the speed brake. see its effect on pitch. That was a good one.
You look and, you know, you still, even though you're sitting in the same desk, you know, Neil Armstrong worked here. We named the place after him. You know, my desk used to be right where he sat. You know, Joe Walker, you know, I sit where his desk used to be. That's where I sit now. And you still don't feel like you're worthy to be sitting where they were.
Air Pro 2.
I'll say one thing. These pilots are about the best test pilots probably in the world. They're very busy. They're either flying all across the world in sims, meetings, tech briefs. They make things happen at NASA and for the United States and the world. They're the first people flying maybe a wing that was modified or some modification to an aircraft.
We're not done with flight. There's a lot of research yet to be done in flight. There's a lot of gains yet to be accomplished in flight. And to get our job done, we need test pilots like Nils Larson, like the people he works with and trains.
Still a little bit of side-to-side motion on the stick, a little bit of pumping forward.
It's early morning and I'm watching the sunrise over the lake bed, and it's a beautiful sunrise, and it suddenly occurs to me, oh my God, I made it. You know, I'm doing what it was that I decided when I was 16 that I wanted to go do. I always tell people that it's worth it, because it wasn't like I was just nosing the book, you know, for 17 years. I had a lot of fun in those 17 years getting up to that flight. And then I've had a lot more flights like that since. So, you know, it's totally been worth it.
Hi, I'm Jim Green, better known as Lunac, and this is Ask NASA. Are we ready for the first question? Let's see. I'm getting a sense of it. Yes, we're going to the moon, and we're doing it for many important reasons. It's because we want to practice on going to Mars. Things that we want to do is to learn to live and work on a planetary surface. Of course, it's got to be about the water. How are we going to use it? We're going to drink it. That's the first thing. The second thing is we can take those two elements apart and use them for rocket fuel. Or we can just simply use the oxygen to breathe. We want to be able to look at this water, tease it out through cores, and understand the water history of the moon. Just that will be fantastic. Ah, yes, the South Pole. It's fascinating. Let's see what it looks like. Here's some LRO data, and it shows us all the areas that have sunlight and all those areas that never receive any sunlight. These are the areas that have the water. What equipment are we going to take to the moon? Well, this is going to be done with the commercial groups that are planning to have landers and rovers, and we're going to ride along. We're going to take scientific instruments with us and tease out the impact history of the moon. That will tell us how the Earth and the moon evolved together. Let's find out what else is going on at Mars. Ah, yes, Marnak knows the answer to that, and it's right here. This is one of our fantastic rovers. It's called Curiosity, and it's currently roving on Mars today. We need to know what that is because it will tell us if Mars is like Earth. All right, sock it to me.
Why is Mars red?
Mars is red because it's been oxidized. That means it has material on the surface that grabs that oxygen and turns it red.
How are the moon and Mars similar?
Well, that's our plan. We're going to go to both.
How are the moon and Mars different?
Well, one's bigger than the other.
Do you know Bruno Mars?
Plays real well. He's the one that wants to go to Mars too. We ought to take him.
Do sound waves travel on Mars?
Sound waves do travel on Mars, but not on the moon.
Oh, cool. What's your favorite planet?
I love all my children equally.
Have you ever named a NASA science mission?
Well, a couple. I was involved in the Image mission, so I helped name that. The Curiosity was the one I helped name. I didn't put in the essay, but I knew it when I saw it. That was the name it needed to be.
Can you describe the solar system in one word?
Massive.
Do you have a question for NASA? Send your questions to our experts on Twitter using hashtag AskNASA.
Today we're going to talk about nutrition and the role it plays to keep astronauts healthy on the International Space Station. Hi, I'm NASA astronaut Tracy Dyson. Welcome to Station Life.
Houston on 2 for velocity confirmation. Steps 45 and 46. We're moving on to step 5.
You want to go right now for that activity?
Copy. Thank you.
Okay, Tracy, we copy, and that's good information. We'll pass it along.
Good nutrition is a part of good health, whether you're on Earth or off. Today's show will focus on nutrition research aboard the International Space Station. That's one small bite for man, one giant leaf for mankind. Astronauts Scott Kelly, Kjell Lindgren, and Kimya Yui of Japan recently sampled the fruits of their labor after growing and harvesting a crop of outrageous red romaine lettuce from the Veggie Plant Growth Facility. This was the first crop of vegetables grown in space, specifically for the purpose of providing fresh vegetables for the astronauts. Later this month, the crew will harvest zinnia flowers, a precursor for the next crop. We're going to try tomatoes. You know, living in space changes our bodies in a number of ways. We lose bone mineral density, our muscles atrophy, our cardiovascular system gets weaker, and we experience immune system dysfunction. One of the ways of understanding the changes in our bodies during long-duration spaceflight is to study our nutritional status at specific time points during our mission. Samples that we collect while we're in space provide scientists with information on bone metabolism, oxidative damage, body chemistry, and hormonal changes. These insights give scientists a more complete picture about what's happening in our bodies. That increased understanding of the role of nutrition in adaptation to spaceflight has a broader application on Earth, One example is understanding the relationship of nutrition to bone loss. This is potentially valuable for people suffering from osteoporosis right here on Earth.
The bones in our bodies are alive, growing, and changing all the time. Our bones are composed of different layers. The outer surface of bone is called cortical bone. This is the smooth, hard part of the bone that we can see when we look at a skeleton. Inside the cortical bone is the trabecular bone. This type of bone looks like a sponge and helps to protect the bone marrow. The constant process of bones growing and changing is known as bone remodeling. This process is carried out by specific cells in our bones. Cells called osteoclasts have the role of breaking down our bone and removing any parts that need replacing. At the same time, cells called osteoblasts have the job of making new bone and helping to repair any parts of the bone that have been damaged. On Earth, in healthy individuals, this process is normally balanced so that the same amount of bone is made and broken down. In space, astronauts are exposed to lower levels of gravity than on Earth. This means that they have less mechanical stress put on their bones as they move around. Scientists believe that the bones naturally try to adapt to this new environment by increasing the rate that the bone is broken down by the osteoclasts. Meanwhile, bone formation continues to occur at the same rate as it does on Earth. The result is an imbalance in bone remodeling, which leads to an overall decrease in bone mineral density. While in space, astronauts can manage with lower bone density, but when they return, their bones are less able to cope with Earth's gravity. This increases the risk of fracture and injury. Scientists use many different tests to measure the density of the astronauts' bones. Results show that the astronauts, while in space, lose bone in a similar pattern to people on Earth who suffer from osteoporosis, but the astronauts lose it at a much faster rate. Scientists have found that exercise, when combined with good nutrition and increased vitamin D intake, is able to preserve some of the bone that was previously being lost. Since 2008, astronauts have been able to use a new exercise machine called the Advanced Resistive Exercise Device, or ARED. It is thought that this increase in force triggers the formation of new bone, bringing more balance to the bone remodeling process and allowing the bone density to stay at roughly the same level as it was before the spaceflight. It is a significant achievement to be able to maintain bone density in space, but more experiments need to be carried out to see whether the new bone which is formed in space has the same structure and strength as new bone which is formed on Earth. Understanding bone loss associated with microgravity may lead to better preventive care or therapeutic treatments for people on Earth suffering bone loss as a result of bone diseases like osteopenia and osteoporosis, or for patients on prolonged bed rest.
One of the things I love about the field of nutrition, one of the things that really drew me into the field of nutrition as a graduate student, was the fact that nutrition really is a cross-cutting science, and the fact that we get to look at all the systems and nutrition in and of itself. So doing bone studies and muscle studies and vision studies and cardiovascular studies really helps to branch out and to work with other groups and see the integration within the human being and not just focused on a specific enzyme in a specific tissue in a petri dish in a lab somewhere in a basement. One of the great things about nutrition research on Space Station is that Space Station is a great platform and that it allows us to study very healthy individuals in a very strange environment, in a very unique environment that the body is trying to adapt to. And what that does, that allows us to understand how the body responds to these changes, and in many ways that reflects disease patterns or altered physiology, if you will, on Earth. So bone is a great example where when an astronaut is put into spaceflight, the body starts to break down bone because the body realizes it doesn't need the same skeleton in weightlessness as it did on Earth. And by looking at that adaptation and how to counteract that adaptation, that tells us about how the body responds to these different changes. So we see roughly the same change in bone in about 6 months on a space station mission as you would see in a much longer period, 4 or 5 years. So it's almost like time-lapse photography where we can see a much faster glimpse of what's going on. We can study countermeasures much more quickly. And again, the implications of those studies for people studying those same phenomena on Earth really helps to leapfrog some of the technology ahead. Hi, my name is Scott Smith. I'm the lead for the Nutritional Biochemistry Lab at the Johnson Space Center, and we're studying nutrition off the Earth for the Earth.
In space and on Earth, our bodies require proper nutrition. Defining the nutrient requirements for spaceflight and ensuring provision and intake of those nutrients are primary issues for astronaut health and mission success. After all, you are what you eat. One challenge is providing appetizing food for astronauts that doesn't require refrigeration and has a long shelf life. While the food is generally much better than you might imagine, and we have come a long way since the early days of spaceflight, we do have limited access to fresh foods. In our next segment, we'll go inside NASA's Space Food Systems Laboratory, as seen in the National Geographic Space Station Live program.
Eating in space is its own kind of fun. But keeping astronauts fit and healthy is a serious business. Michelle Clinch is responsible for what they eat.
We're making spaghetti with meat sauce.
Space meals begin just like ours do, with a trip to the supermarket.
Thank you.
But the similarities stop there. Spaghetti and meat sauce is just one of the 250 things on the space station menu. Each portion is meticulously calibrated.
We have a database where we maintain the nutritional content of all our products. Calories, fat, protein, carbohydrate, things like that.
But the most important calculation is what things weigh. That's because it costs $10,000 for every pound blasted off to the astronauts. So NASA adopted a reduction technique, also used by the military.
Freeze drying removes a high percentage of the moisture, so typically when we freeze dry our products, we take them down to about 3%.
Each portion now weighs just 1 ounce. Cost to transport, $660. 1,300 miles away, and the orbital Cygnus resupply module is being loaded with the freeze-dried food. And it's time for a few last-minute food luxuries.
These are the tortillas. They're very popular on orbit.
After a daily routine of freeze-dried meals, a fresh piece of fruit is a welcome relief, well worth its weight in gold.
As you can see, we're only sending 3 apples, so you may think that's unfair because we have 6 people on orbit. They may have to share.
This very precious cargo is one of the last things to be loaded onto the rocket.
It's on its way.
3, 2, 1.
Less than a kilometer away from us now.
2 days later, Cygnus docks with the space station.
We're getting ready to berth the Cygnus 1 vehicle. All right. Looks really good. Perfect. Perfect. All right. Bonus food.
Including some surprise treats from their families.
Wow. Look at that. Tortillas. The real tortillas. Look at that. Real tortillas. Pours it. Wow. Oh my goodness gracious. The greatest hot dog relish in the history of man. Oh my gosh, my wife didn't tell me about this.
Hello, and welcome to Node 1. In the boxes you see here, we keep our food on the International Space Station, and specifically the food that we are currently eating. And in our logistics module, Leonardo, where I was just now, we keep our supplies. We keep them in soft containers like this one, which we call bobs. And this one is a very special bob for me because it contains my bonus food, the food that I chose myself based on my preference and my taste. This one, for example, is one of my absolute favorites. It's quinoa salad with mackerel. Mackerel is a great source of healthy proteins, but also of healthy fats. Those fats that our body absolutely needs to stay healthy and in good shape. On board we have different kinds of fish, which are great sources of healthy fat. For example, thanks to our Russian colleagues, we have sturgeon. In my bonus food, I also took sources of healthy fats that I can eat for a snack. I love avocado, for example, so I took it in form of guacamole that I can spread on my bread. Or I also love dry fruit, so I have almonds and nuts. And I didn't forget to take olive oil. And I can tell you, our rehydrated veggies not only taste a lot better with olive oil, but they're also a lot healthier. So I hope you will put the right rocket fuel into your body, starting with the right types of fat. And remember, eating healthy is not rocket science.
You know, I don't know the reason behind it, but your taste buds change when you get to space. So the things that you like on Earth and you just can't get enough of, you've got enough of when you get to space. So there's something about your taste buds. Don't know what it is. However, aromas, you don't get enough of it, partly because of the way things are packaged. And coffee, for instance, has this smell that you kind of consume while you're eating the food, but it's in a package that has a straw and you can't smell anything. So it still didn't stop me from drinking it, but you just couldn't smell it. And same with all the other foods. They come in a little package, and so you don't really smell it very well. And you'd miss that. When you come back to Earth, you find out just how important smell is when you're eating food. So, how does the space station smell? You know, this is a good question because in general, the space station smells like nothing. It's clean, except if you're in node 3 and you're working out on the A-Red machine and all of a sudden you smell something that you think is coming from the WHC, but it's actually, which is our space potty, but it's actually our Russian colleagues back in the service module open up a can of beef, and it gets into the air circulation system, and it makes its first stop in node 3. And so at first you're like, oh, what is that? And you're like, oh wait, it's lunchtime. And then it's a much better smell into your brain. You know, mealtime in space can be a lot of fun. It's especially dinner time. At the end of this long day where 6 people, 6 little pink bodies in space, working all day long, and we're rarely together working unless it's something very unique. We're all off doing our own thing. And to come together at the end of the day when you know that you've signed off with mission control and you're in that evening period of time, that you can sit around a table with your crewmates and share food. And when you're an international crew and you have food from your Russian crewmates, your Japanese roommates, well, that's what we are, crewmates. When you have everybody coming together at the table to share their food, that's one of the best parts about eating in space.
So I just finished eating and I have to enter in what I ate because the ground folks like to keep track of it, keep track of our calories, how much salt we're getting, how much protein, things like that. They track us closely on everything. When we lift weights, we have to keep track of how much weight we lift, how many reps we do. When we run on the treadmill or when computers are recording our heart rate, when we turn on lights, when we turn on the toilet. I learned on my first mission there are no secrets in space. We got video cameras in just about all the modules. So it's basically like being in a big fishbowl. The ground knows everything about us up here, which is not that big a deal, but it's something to keep in mind when you need a little privacy.
We'll just get my safety cutter on the other side of my IDA back here.
Copy, Terry.
A lot easier without the pool stanchion.
Absolutely, yeah. And it's just like in the pool instead of that, with the exception of that big blue planet down there.
Exactly.
As the International Space Station flies 257 statute miles over the coast of Chile, Terry Virts in the initial moments of his first spacewalk.
Welcome back, and thanks for watching this episode of Station Life. As you can see, space station nutrition research is vital towards improving the quality of human health and well-being in space and here on Earth. NASA is constantly searching for ways to benefit humanity, as together we take the next steps towards exploring our universe, searching for the answers that matter to us the most. Thank you for joining us on Station Life and our behind-the-scenes look at nutrition research aboard the International Space Station. Be sure to stay in touch and follow us on Facebook and Twitter for the latest research news. And don't forget to download our fabulous app on your mobile device. Until next time, stay with us, off the Earth, for the Earth. I think it's time to eat.
The reason that you would do any kind of experiment in space
is if there's something particular about the space environment, and most often that is microgravity. So mostly the ISS gives us the ability to either do something that we can't do in a facility on Earth or investigate some phenomenon, some property in a way that we can't on Earth. So for example, some of the tissue architecture, these really delicate tissues, as you start to build them up, they would collapse because you have gravity, or the cells would naturally settle to the bottom of the plate. And so you just can't study the answer to the question that you're looking for. So the space station lets us have that ability to either test what the effect of gravity is or remove that problem entirely from our experimental setup. Yeah, the space station's an incredible place to conduct research. It was sort of like being in the world's most amazing lab when I was up there in 2016. So when you're a scientist, you're used to working on one thing over and over and maybe really refining the details on that over the course of a PhD thesis or a lab project. On space station, you get somebody's incredibly refined project times 200 different fields. So for me, it was a chance to learn about all of these different areas of science, and they each have a team behind them. So I was usually pretty excited to open the container and do whatever experiment that day brought. I also really got a chance to talk to those PIs, the principal investigators, and those scientific teams, and understand everything that was going on behind their experiments and read their papers. So by the time I got to doing the experiment, I was pretty excited to take it out and to see what was going to change in microgravity. Yeah, science in space, it's an amazing lab and it's incredibly fun. So we are smiling all the time. I'm Kate Rubens. I'm a scientist and an astronaut.
It's a new era of pioneers, star sailors, thinkers, and adventurers.
3, 2, 1, 0. All engine running.
Let's go.
We have been given the scientific knowledge, the technical ability, and the material to pursue the exploration of the universe.
Being an educator today is not easy. We here at Heights Elementary School are not here simply to educate our students in the academic realm. It's so important for our students to be lifelong learners, and we have to think about ways that we motivate them to do so.
There are so many distractions that we have to compete with.
iPads, Xbox, video games,
the internet.
Far too many channels of cable television.
What we need is something that kids will be highly motivated about, something to keep them physically fit as well as making nutritionally sound choices.
What we needed was a new tool to help these kids think about diet and exercise in order to make the healthy choices they need to.
I knew what that tool was. It was something that inspired me as a kid and continues to inspire me today. The space program.
The importance of an astronaut's physical exercise and proper diet cannot be understated, not just for the fitness of the astronaut, but also to ensure that they stay mentally focused and productive during their stay on the International Space Station and for future missions, whether it be to asteroids, the moon, or Mars.
In response to the rising childhood obesity rate, NASA has developed a series of activities based on astronaut training, and we call that Train Like an Astronaut.
Examples of the Train Like an Astronaut activities include things that we do exactly as we do on the ISS: cycling, resistance training, and cardiovascular. And then onto dexterity, putting puzzles together, making healthy food choices, and working as a team. All activities as they truly do on the ISS.
Train Like an Astronaut activities are flexible enough to be used in conjunction with other programs like NFL Play 60. What makes this program unique is that we're using the human challenges of spaceflight to inspire as well as motivate our children to make healthy choices throughout their life.
We're currently in 24 countries with over 24,000 participants and growing every year.
This has expanded to such an incredible opportunity for both myself and for educators around the world to make such an impact on the lives of children, both with fitness as well as nutrition.
It was excitement for the whole thing that the students, they weren't just doing exercises anymore. They were training like an astronaut.
The true success of this program is the educators. An example of a teacher that has worked and motivated his children is an outstanding educator by the name of Tim Vigorito. This gentleman excited them and inspired them in ways that we never could do it. And with that, he's helping us grow the 21st century leadership that we so desperately need.
Mr. Vigorito is extremely passionate about the Train Like an Astronaut program.
I think he himself would like to be an astronaut.
He comes to life when he's teaching the kids and talking about the program. The kids feel that enthusiasm.
We're just so fortunate to have him. Oh, it's truly the case.
They say your astronaut training doesn't begin when NASA hires you.
Cool.
It begins when you're young, by learning about space and the world around us, and by making healthy choices in life. Today, I'd like to recognize an outstanding physical education teacher, Tim Vigorito, for being a champion for the Train Like an Astronaut program and influencing thousands of students to date.
Wow.
It is educators like you that truly make a difference in this world, and who will inspire the next generation to propel humankind on future missions to Mars and beyond.
This is too much. For me, it's become a way of life, and I'm just so thankful to everyone for what it's done for me. I just want to share that with my students. Maybe it'll inspire them to reach a little deeper or to go a little further or maybe to try a little harder, whatever it is in life.
The International Space Station is the most fantastic vehicle ever built.
It's a one-of-a-kind laboratory orbiting about 250 miles above the Earth.
And we perform experiments on the International Space Station.
We can do science, we can do experiments, we can learn how to do things out of this world.
And the result will help benefit the people on the ground.
Space Station really provides an opportunity to explore, for example, say medical applications.
The aging and the osteoporosis and muscle wasting conditions are greatly accelerated in microgravity.
The weightless environment will give us insights into things like diabetes and maybe even cancer.
Understanding those phenomena allow us to look at how we can improve treatment of disease here on Earth.
If we wouldn't have conducted experiments on the ISS, we wouldn't have known that you could use cold atmospheric plasma in such broad application areas we're now exploring.
One of the most promising results has been gained by studying a protein associated with Duchenne muscular dystrophy.
We may be able to slow the disease by half, potentially doubling the lifespan of many of these DMD patients.
We provided eyes-serve imagery for many natural disasters, including floods and fires, for deforestations, for volcanic eruptions, and for earthquakes. So it was really a fantastic example showing how imagery from the International Space Station could be used in these times of dire need.
This was when we realized we had a chance to make a difference in the world using the same technology that was used by NASA, but applied in a remote area of a developing country.
I think it's made people much more aware of the issues of water quality. That's a very powerful thing.
Having the HYCO on the International Space Station has been the ideal test bed for our research.
We can monitor these water bodies from space, and if we can reduce exposures both to humans and even animals, then we've achieved our goal.
And now today, we're able to operate the largest fleet of Earth imaging satellites in human history.
And none of that would have been possible without the International Space Station.
The space station has done so many things for life on planet Earth. It shows us what human beings can do working together. It shows the science that we can discover.
Over 2,000 experiments have flown on board ISS. 170 countries around the world have participated in some fashion, either in the ISS itself or in one of the experiments. Our rate of research is actually increasing. We're doing more today on board the space station for research than we have ever done before, and that's only going to continue in the future.
And so what we're seeing today is a proliferation of new ideas and new concepts. It's almost like it's a renaissance of what's happening in space. Buckle up and strap down, because this is going to be a rocket for all of us in the global community to be part of.
Carroll Township's a very rural area in northern Ohio, right on Lake Erie. Lake Erie has always been very important to Carroll Township and its residents. We use it for drinking water, we treat it, and it's really our livelihood.
In Lake Erie, for what unknown reason, suddenly the toxin level spiked, and that got through the treatment system.
It was indicated to me that it is pretty dangerous.
Cyanotoxins can cause skin rashes,
Headaches,
nausea,
vomiting, stomach problems,
nervous system problems,
liver damage,
to death.
We sampled, and we had about 2.5 times the limit from the World Health Organization. The second sample was approximately 3.5 times. Our plant wasn't set up to handle what was coming in from Lake Erie. One of my biggest worries was actually hurting someone or even worse. So we shut it off right away, shut everything off. We had a very close call that day. The last thing you want to do is produce an unsafe water and allow your people to drink it. What we need is a better way to track and predict these cyanobacteria entries from our source water so that we can make sure that this never happens again.
A lot of times we'll find out after the fact that there's a problem with cyanobacteria in the water because the blooms already occurred. We either get results of sick animals or sick people. We need a paradigm shift. We need to go from being constantly reactive to these blooms to having a capability that allows us to become proactive. And the U.S. Environmental Protection Agency has been very encouraging of allowing for some high-risk, high-reward projects. And that allowed us to think outside the box, way outside the box. We've been fortunate enough to make use of a sensor on the International Space Station called HYCO, which stands for the Hyperspectral Imager for the Coastal Ocean.
HYCO consists of 2 instruments. One is a camera, and the second instrument is a spectrophotometer, which actually gives us the spectrum of light leaving that water.
The camera on a cell phone, for example, contains about 3 bands of data in a red channel, a green channel, and a blue channel.
HYCO gathers light from the red, orange, yellow, green, blue, indigo, and violet parts of the spectrum. So using this technology, we're able to now detect those water quality parameters such as water clarity, what the phytoplankton concentration is in your water, how much light is being absorbed in your water, as well as what's the distribution of cyanobacteria in those waters, and does that concentration pose a health hazard?
So what this means is instead of waiting for someone to report that there's a problem with cyanobacteria bloom, we can monitor these water bodies from space
and get information that we can rapidly get out to the water quality managers through a smartphone application that we've developed.
So the app allows you to drop a pinpoint, and that pin can be placed in an area where a drinking water treatment plant may have an intake, and see what the current water quality conditions were. Each user gets that information near real time, so they can make judgment calls on whether they have to respond or take action.
Having the HYCO on the International Space Station has been the ideal test bed for our research.
This is an amazing partnership. The Naval Research Laboratory had HYCO on NASA's International Space Station. As HYCO acquired a scene, it was transferred to the Naval Research Laboratory. And then the Environmental Protection Agency was able to do the analysis and the validation to send this information out through a prototype mobile application. Yes, this technology will reduce costs and provide near real-time information. But the big goal here is protecting humans. And if we can reduce exposures both to humans and even animals, then we've achieved our goal.
As farmers and winemakers, we work very hard to grow the best quality fruit possible to make the best wines possible. The real polished part of winemaking is letting that wine age gracefully so those flavors can be preserved and brought to your home and to enjoy in the glass. The greatest issues we face as winemakers is that our optimal storage conditions for our wines are also optimal growth conditions for mold and bacteria.
Mold is really bad in a barrel room or in a cellar because it has an odor to it. And the wines are a living, breathing thing. And actually, they pick up the characters of where they're living.
The wines can absorb that aroma, and it's just not a healthy environment to work in. My father and I built this barrel room underground. The challenge is we've got some stagnant air which can cause mold growth. Who knew that our solution would be not underground, but up in the sky?
In order to carry astronauts to Mars for deep space exploration, you have to be able to grow your food stores. You don't have enough space and capacity to carry them with you. So NASA began experimenting with growing crops in space. What they found is that in the growing chambers on the International Space Station, the crops they were growing were emitting a naturally occurring hormone called ethylene. It's a gas, and ethylene is the reason that fruits and vegetables ripen.
But the problem was in space we're going to have a very confined environment, so the ethylene concentration can build up, especially in a plant growth chamber. It basically destroys the plant. And so there was a need to grow plants in space, and we were good at growing plants here at the University of Wisconsin. And so NASA came to us and said, we've got a problem. I think you've got a solution. Can you help us?
Through the University of Wisconsin Advanced Astroculture Program, they developed an ethylene removal system that was successfully tested on a number of missions on the International Space Station. So the ethylene removal system that was developed draws air through a reaction chamber. The air is passed across a catalyst bed, and that catalyst has the effect of removing anything organic from the air. That includes mycotoxins, bacteria, viruses, and even mold.
It showed us that with the right technology, we can overcome the challenges of growing plants in space and enable future space explorers to grow their own food as they continue to explore the solar system.
The International Space Station program not only supports the technology that allowed us to get rid of ethylene in the Space Station astroculture program, but it also provides a great variety of technologies to exist that otherwise wouldn't have been possible.
Realizing that this technology could have tremendous benefits here on Earth, we developed the Aeroside air purification systems. Initially used in the perishables world for prolonging the shelf life of fruits and vegetables, not long after that, we realized because of the effects the technology has on mold, that the wine industry was a perfect complement for the technology.
This technology has been a real boon to us. It helps me sleep better at night.
But as you can see around the cellar, there's not a lot of mold.
Within 24 hours, the amount of airborne mold spores were dramatically reduced.
Within 2 weeks, about 99.9% of the mold had vanished on the walls.
It solves problems before they occur.
The room smelled fresher. It actually enhances your storage conditions for you to even make better wine.
It's really amazing when you think about all the innovations that are going on up in space, how they can come into a place as unexpected as a winery, which translates into benefits on your dinner table.
Servir is a joint NASA and USAID program where we're working with developing countries around the world and strengthening their ability to use satellites to address the many problems that they have, including floods, fires, harmful algal blooms, and other types of events that they have where they can use satellites to really make better decisions.
We're using space information to help decisions that affect people in the village where they live.
When there's a major disaster, governments around the world come together and they provide all of the satellite data basically that the world has to offer. But there's smaller disasters that occur in the countries that we work in that may not make the front page of the New York Times, but in that country it's a really big deal. We asked ourselves, could we make a difference if we had a dedicated imager for acquiring imagery quickly after natural disasters and to be able to provide that imagery back to the countries that need them, that have real decisions that need to be made with a very quick turnaround. As NASA, we looked in our own backyard and started thinking, could we use the International Space Station? The International Space Station was really a fantastic asset to take advantage of because it passes over 90% of the Earth's populated area every 24 hours. We developed an imaging system and we called it iServe, which basically is a camera and a telescope system that sits inside the International Space Station and can collect imagery when it passes over natural disasters or other events that we need to collect imagery.
Initially, we were planning to take a few pictures per day.
So we contacted all the USAID missions around the world, and in total we had more than 2,000 requests coming, for people who need images from iServe.
And we moved to like 1,000 images per day.
We provided iServe imagery for many, many natural disasters, including floods and fires, for deforestation, for volcanic eruptions, for earthquakes. So it was really a fantastic example showing how imagery from the International Space Station could be used in these times of dire need.
And now we have a huge archives of images of areas around the world. So this is something that was not really there before.
iServe is an example of, in essence, making the International Space Station even more international and connecting space to village to better understand and protect our home planet.
From the solar winds to the mystical auroras, science is a way of knowing, a way to help us understand the world around us. But how do we learn about the things we see, and how do we make sense of the things we don't understand? Find out next on Real World. As humans, we're all really curious about the world around us. Science is a way of knowing, but what does science really look like? Let's drop in on some NASA researchers who are currently working from home. Dr. Nicolene Weil studies the sun and solar winds by analyzing data from spacecraft, like NASA's Solar Dynamics Observatory. Dr. Marilia Samara studies charged particles in space by sending rockets into the auroras. And Amber Versteinen is an undergraduate student majoring in atmospheric science. Amber's internship at NASA helped put her on the path to a career in science. Dr. Weil, can you help us learn more about the nature of science?
Science is about understanding the natural world around us. Science is about finding new information, which inherently comes with being wrong a lot of the time. By definition, you're exploring space and questions that nobody has really thought through before.
Dr. Samara, how do these questions drive the study of science?
We'll ask questions. We try and figure out what experiment might help us answer those questions. We go for it. Usually we don't figure out enough. We try again. We had no idea how the aurora was created, but people would notice that when they had a compass and there was aurora going on, funny things would happen. So they knew it had something to do with the magnetic field.
Scientists use different methods and tools to gather a variety of mathematical data. Data may include images, numbers, patterns, shapes, and calculations that help model and describe the world around us.
So think of images just with like a camera. That's a remote data set. You can do it in optical light, the light that we can see with our eye, just like with a regular camera. But we can also look at the sun in other wavelengths, other types of light, like X-ray light, ultraviolet light, infrared light. And so those are give you other types of information about the sun. The other type of information that we can get is called in situ, and that means measuring directly where you are.
In the case of aurora, we're trying to launch and go over the aurora in what we call the apogee, which is the highest point from the ground, and make measurements there. By concentrating on the apogee is we effectively get a snapshot of how the environment, that space plasma environment, looks at that particular time, at that particular altitude. It's surprising how much science is in just a couple of minutes of these measurements.
When we look at data for a long enough period of time, we can understand patterns in those data and really make sure we're not just answering one little question about the sun, but that we're really pulling all of the information together and making sure the big picture still makes sense of how we think the sun works. When good science is being done, it leaves room for us to change our mind, to realize we were wrong about how something was working as we get new information, and we have to refine our ideas about how the natural world is working.
Scientists do their best to understand observations with the knowledge and tools they have, but sometimes scientific explanations change.
So I think of science as basically a puzzle. We have tiny pieces of a big puzzle. Every time we have a new piece that actually connects, our image changes.
We do our best to describe what we see and what we're observing, and then we figure out which parts still aren't making sense. Sometimes a model will make sense and explain all of the observations that we have today, and then tomorrow the sun will do something totally different and we'll have new observations. And it's not even necessarily that the model was wrong, it's just that the model was incomplete.
It's important for all of us to understand the nature of science because we can all be scientists, asking questions and gathering data. Amber, you've had a chance to collect data during your internship at NASA. What were you studying?
While I was in high school, my first project was studying ozone and how it affected plants by working on an ozone garden that was at the Virginia Living Museum. An ozone garden is a garden that consists of different types of plants, some that react to ozone and some that don't. So some of the tools we used was a meter stick to measure the heights of the plants. We used a rain gauge to measure how much rain all of the plants were getting. We used a thermometer to measure the air temperature that the plants were growing in, and we used a psychrometer to measure the relative humidity of the garden each day. The ozone garden research was really important because it shows how different plants grow more efficiently in different climates and how ozone has such a big effect on plant growth. This is really important to understand with our changing climate.
A new fact is really like a new piece in a science puzzle. As more pieces are added, the big picture becomes clearer and clearer. But it's important not to try to force any pieces that don't fit.
It's important when we do science to do our best to overcome our biases. Everybody has biases. It's important to be ready to be proved wrong.
Science is a human endeavor, and our understanding of science is constantly changing. Men and women from all cultures and backgrounds choose careers as scientists and work in teams to answer the questions we have about the world around us. So, how can you get involved?
So don't just sit there. Ask a question. Make an observation. Use all the tools you have to collect evidence. Even do a citizen science project. You could even do an internship, maybe even at NASA.
So what are you waiting for? Science is an amazing way to use math to help uncover grand mysteries in the natural and material world. Special thanks to Dr. Nicolene Weil and Dr. Marilia Samra for helping us understand more about the nature of science. And thank you, Amber, for helping us see ourselves as scientists. I'm Sarah, and see you next time on Real World.
NASA Marshall Space Flight Center is Science Central for the International Space Station. Our teams help astronauts conduct groundbreaking research in microgravity. We have supported more than 3,400 investigations from around the globe. Our operators work with researchers, commercial companies, and even students to expand scientific discoveries on the orbiting laboratory. Now let's hear how each flight controller position is critical towards making science happen in space.
Welcome to the Payload Operations Integration Center. As a Payload Operations Director, I manage the day-to-day operations of science experiments performed on board the International Space Station.
The science experiments on the International Space Station range from studying human physiology to dark matter and even growing plants in space. As a Payload Rack Officer, our job is to monitor and ensure the safe operational use of these experiments.
It's very important that tools and parts are safely organized on the International Space Station. Every day, stowage engineers track the location of these items so astronauts can easily find them to conduct science experiments.
The PACOM team talks directly with the ISS astronauts, guiding them through science experiments and technology demonstrations. The crew are our system, and we advocate for them from the ground.
Analyzing, integrating, and communicating. These are the responsibilities of an operations controller. We ensure that the astronauts have the resources they need to complete their science experiments safely.
Sometimes even the best plans need to change. Timeline change officers work with NASA centers and scientists from around the world, developing the best plans for each science experiment.
It is important that science data is transmitted down to Earth. As a data management controller, I help to ensure that data from Space Station is sent to scientists around the world.
The Marshall Ground Control Team ensures that all ground equipment is fully operational, such as computers, servers, hardware, and software. We also make sure that all data is successfully sent to and received from the satellites.
Thank you for visiting. We hope you've enjoyed this behind-the-scenes look at how Marshall enables scientific discovery.
Send that command. You have 31 minutes and 32 seconds for our support. Go for status buffer dump.
Since the retirement of the space shuttle, the engineering team is absolutely critical for Hubble. It always has been.
Without the shuttle going up to replace any equipment failures that we have to make do with what we have. What we really are concentrating on is just keeping the telescope working and keep the science going.
And everything looks excellent.
and we have no reason not to expect that Hubble will last until the late 2020s and beyond.
My name is Mike Wins, and I'm the lead systems engineer for what's known as the Optical Telescope Assembly of the Hubble Space Telescope. I'm in charge of what's known as defined guidance sensors. These are the instruments that actually help Hubble do the exquisite and precise pointing that it does. Right now we're getting ready to perform an observation. The telescope is going to be trying to go to acquire some guide stars in just a few minutes here. The stock is the Space Telescope Operations Control Center, where we send commands to the spacecraft. On a daily basis, we have to send up what's known as command loads.
Accepted. DTMR is good. Step 3 is complete.
Because the computers on Hubble are very old and they have very little memory, in fact, most of your memory sticks today are 20, 30, 100 times bigger than Hubble, we have to send up essentially a load of all the commands Hubble's going to be doing for the next 24 hours.
On a routine basis, we always keep 24 hours of instructions on board, so it's routinely updating for the new sequence 24 hours in advance.
We'll start with doing our premise uplink.
Hubble is always working, it's always doing something, it's always doing some sort of observation or calibration or getting ready for the next task.
We'll be logging on board at 14:33:17.
Hubble is truly a 24/7, 365-day-a-year instrument, so Hubble can keep on going. It never stops.
And we are configured. It's been verified.
Now we do have to, because of this low Earth orbit we're in, the actual observations, when we're taking a picture of something, we're doing a science observation, we actually have to wait because sometimes the Earth gets in the way. So we have to pause, wait until the Earth gets out of the way as we go back around and start the observation back up.
You have constraints. You don't want the optics pointing at the sun, and you don't want the instruments to have their shutters open when you're looking at the Earth, because the Earth is bright for them. And then we have the South Atlantic Anomaly, the SAA, which is a portion of the Earth where we get proton hits that will affect the electronics in Hubble and can also affect the instruments in Hubble. And so we have to plan out very carefully our targets and observations. We have a timeline that's laid out to maximize the efficiency of it.
Hubble can actually take observations during day and night passes. Every 95 minutes, we go around the Earth. The batteries will charge from the solar rays during the day pass, and then at night, batteries power the observatory so we can continue observing. The scheduling with Hubble, we're trying to put it together as efficiently as possible, minimize our gaps. The goal is to constantly keep it busy.
We're constrained to a certain extent, but whenever we have visibility, we are observing.
The demand for use of the Hubble Space Telescope from scientists around the world is very high.
Hubble is at its most productive. It's got some of the best instruments that have ever been on board it. There's a very high demand. Hubble's performing exceptionally well.
2, 1, and liftoff of Space Shuttle Atlantis. A final visit to enhance the vision of Hubble into the deepest grandeur of our universe.
Since the final Space Shuttle servicing mission, we're using Hubble to get the best kind of science return we can from the suite of instruments that we have. So our focus now is on making sure we get the best science while it's still operating so well.
Luckily, at the end of the last servicing mission, we were actually left with a telescope in great condition, but Hubble is getting older and older. It's a very old telescope.
Now, 10 years after the last servicing mission, we can't rely upon servicing missions to fix things, so we have to rely upon our own ingenuity to be able to figure out if something does fail, what are the alternative paths that we have.
For the telescope to keep giving us this peak science, we need lots of things to be working together very well on the telescope. We need a pointing accuracy system that is outstanding and keeping that whole system healthy and functioning so that we can point Hubble very accurately even while it's whizzing around Earth in its orbit.
For the telescope to be able to do the science it needs to do, we have to hold it very, very steady. There is actually a little bit of motion. I mean, it's hard. We're zooming around the Earth at 17,000 miles an hour, so it's hard to hold the telescope perfectly like that. The gyros are working really good.
The gyroscopes can sense motion in each direction. And so because of the gyroscopes that we have on board and how sensitive they are in terms of sensing motion, that we can keep our cameras steady.
Gyros are very good at measuring these very small rates. The fine guidance sensors are actually sort of used, I always like to describe it as backseat drivers. And they constantly tap on the gyro's shoulders, it's about once a second. And they keep saying, turn left, a little bit more right, a little bit left, a little bit right. I mean, it must be driving the gyros nuts. So the fine guidance sensors allow you that really fine control, but actually it's the gyroscopes driving the telescope. And they're doing a perfectly good job here. Everything looks good, our stars the right brightness. The reason that is because we need to make sure we have the correct guide stars. One of the things we look at is the brightnesses, and that's what we're measuring here. Those are about right for what the stars were. But also we wanted to make sure they were exactly as far apart as we thought they were going to be. And it did. It did a check, and it passed a very, very tight tolerance check to make sure that those were the right stars. So we know we're locked up on the stars. We got a good lock here. The gyroscopes are very critical because to be able to move from one position to another position, the gyroscopes are the only thing that can tell us how we can do that. We have 6 gyroscopes on board Hubble. Currently, 3 of them are still working. And 3 is sort of what people used to think of as the minimum number, but we have developed a science mode where we only need 1 gyro.
A big part of our job is to make sure that we can extend the life of Hubble and continue doing the high performance science that we're doing for many more years.
And what we've done is we've gone through all the critical components of Hubble and said, how can we potentially make them last longer? As you might do with your own car, as it's getting more miles on it. The gyroscopes have been our most problematic piece of hardware. So I helped lead an effort to develop a 2-gyro science mode. And we were able to use that mode on orbit. And electrical system test facility is it's an exact copy of the main part of the telescope where all the electronics are. And it has the mechanical bays, it has the computers, the electronic boxes installed in there, and it has the cables and harnesses in there. And in fact, when we were building the vest, we had the quality engineers came to us and said, you're not doing these cables exactly the way you should be doing them. You know, we've got better standards now. And our thing was, we're trying to build a copy of what we have on orbit. And so what you have in the vest is an exact electrical copy of the Hubble Space Telescope. Every orbit as we come around the Earth, to be able to get our attitude correct, to get ourselves steady and locked on, the fine guidance sensors and the gyroscopes are key to that. And that's why those are the 2 of the subsystems that are on the top of our list as far as having contingency plans for and monitoring the health and safety of those and making sure we have them in peak performance. When something fails on Hubble, or we have an anomaly, something we don't understand, one of my jobs is to bring together the experts, which may be a thermal engineer, a mechanical engineer, an electrical engineer, a software engineer, all these different people. And we'll say, you know, how do we deal with this issue? And how can we work around it and return back to peak science? What you do is you come up with a list of what is available to you on the telescope in terms of potential. I could close this relay or open that relay or turn on this box. And I am continually amazed. You have a telescope on orbit that you can't even see. I mean, all you're doing is looking at the data coming down to you from the ground. These experts are able to use their ingenuity and come up with ways to continue to operate Hubble. And everything looks excellent, and we have no reason not to expect that Hubble will last until the late 2020s and beyond.
I personally am extremely grateful to the Hubble operations team, these people who work day and night to keep Hubble operating, providing exquisite science return, giving us the information that we need to know how Hubble's doing. Is it doing the kind of accurate pointing that we need? Is it getting the sensitivity in the various wavelengths of light in the various instruments that we need to have to do the science? Are we able to calibrate those observations in an accurate way? We couldn't do any of those scientific analyses if we didn't have this team of operations experts behind the scenes making sure that the details of Hubble's technical operations are being monitored, being handled, being managed, being planned in a near perfect way. Because the Hubble Space Telescope is so scientifically effective right now, scientists are using Hubble to investigate some of the deepest mysteries of the universe.
One of the primary things Hubble has been doing is looking at the atmospheres around exoplanets.
If you had asked the guys who built Hubble and designed Hubble, they would have sworn Hubble could never, ever do this.
That's one of the things I love about Hubble, is that it ends up giving us new questions, new mysteries to explore.
My name is Larry Dunham. I'm the Chief Systems Engineer for Flight Systems here on the Hubble Space Telescope. I started on the Hubble program back in the summer of 1982 when Hubble was being built out in California. First telescope in space to be designed so that we've got what we call orbital replacement units. They're modular boxes with handrails on them so the astronauts can go up and just pick and play. They've got nice connectors on them that make it easy for the astronauts with their big gloves to be able to put them in and out.
We've had 5 servicing missions. We have replaced some equipment multiple times, especially the instruments. We're always going with the advanced technology.
The telescope we have today on orbit is not the telescope that we launched originally. We've been able to replace all 5 of our science instruments with instruments that have the technology that didn't even exist when Hubble was being built originally.
The Hubble Space Telescope is really an observatory because it has several science instruments, several modes of operation. We have multiple cameras, multiple spectrographs. They each have different capabilities in terms of their sensitivities or the kinds of frequencies they can receive the electromagnetic spectrum. We can also use Hubble in different kinds of intriguing modes depending on what we're trying to observe.
There are different types of observing scenarios, and one of the things the scientists have been able to do is they've been able to come up with very interesting and unique observing scenarios that allowed them to do science that they never thought they could do before.
Because the Hubble Space Telescope has been operating for a long time, it's giving us what we need to explore the universe in deep ways that would never have been possible when Hubble was first launched. For example, scientists wondered whether we could use Hubble in an innovative mode in recent years, basically scanning objects slowly instead of just staring at them. In some cases, that gives us a higher sensitivity to what we're trying to observe. And we're using that special mode on Hubble now to get better information about many types of things in space, including to be able to study planets around other stars, what we call exoplanets, planets outside of our own solar system.
What Hubble's been able to do is as the planets go in front of the stars that they're going around, the spectrographs can detect changes, very small changes in the spectrum. This has allowed them to do exoplanet atmospheric studies. This is something that Hubble has sort of really stepped up to the plate and has been just phenomenally good at. Spectrographs have really sort of been leading that. If you ever see things about, oh, a new exoplanet was discovered that has this in the atmosphere or that in the atmosphere, or we think it's made of this, it's the spectrographs which have shown you that kind of information. For doing a lot of the exoplanet observations, you have to catch what's known as a transit. One, the orbit of the exoplanet has to be such that it's going to go between you and the star it's going around. We can't just do an exoplanet observation whenever we want or whenever it's convenient. We have to do an exoplanet observation when it's first starting to go into the star. And so they have to know very accurately the timing of that. We have to schedule it ahead of time. This is not something that Hubble can get around to when it wants to. We have to say, no, at this point in time, on this date, you have to be pointed here and you have to be looking here. We had to really think about how to schedule this. A lot of thought goes into it. A lot of thought goes into the planning and of the execution.
The Hubble operations team are quite willing and capable of using the telescope in new modes and new innovative ways that enable us to accomplish science that we wouldn't otherwise be able to accomplish. We asked them, would it be possible to use Hubble to track something moving quickly across the sky? And they figured out a way to use Hubble in a vast tracking mode that enabled us to do explorations and discoveries that astronomers didn't envision using Hubble for when it was first designed.
Now, when we're observing our planets, when we're observing Jupiter or Saturn or Uranus or Neptune, they move also. We have to move the telescope because they're just going around the sun. They're actually moving because they're really moving. So we have to move with them. We're observing asteroids or comets. We have to chase after them.
Oumuamua, we know came from outside of our solar system, is like a big asteroid that was detected whizzing through our solar system. We wanted to use Hubble to observe this as well, and we were able to track it. This is not a simple operation. It's moving at more than 100,000 miles an hour, so being able to observe this and track it is a wonderful capability that the operations team has enabled Hubble to have.
The telescope is big, it's massive, it moves about the same speed as the minute hand on a clock. So to move from pointing one thing to go completely around the other one takes us a half an hour. It is not a very fast motion. We actually use a very interesting technique. It's using Newton's third law. We have these very large reaction wheels on it. They're about 2 feet across, very, very heavy, very, very massive wheels. If you start spinning those wheels one way, the telescope will spin a little bit in the opposite direction. This is how we can move the telescope from one part of the sky to another part of the sky.
Once we've moved the reaction wheels and we've moved the telescope so we're in the right spot, now we have to get in the exact location to put the target in the science instrument aperture.
What's going to happen now is the FGSs are going to start talking to the telescope, talking to the flight software computer and saying, I want you to move the telescope over here a little bit to be able to position the science for the science aperture.
Most of the time we use the Hubble Space Telescope to do observations that have been planned quite a bit in advance. Observers around the world, astronomers will write proposals. We will then take those accepted proposals and observe whatever it is that the astronomer has proposed. But sometimes there are things that happen that are unexpected or rapid events that we need a more rapid response.
We have a capability of what we call a target of opportunity. And that's when something unexpected happens in the universe that astronomers, they want to immediately jump on that as fast as possible with Hubble. Case in point was the gravitational wave detection to neutron stars colliding. A target of opportunity was submitted for Hubble to actually go look at the remnant and see if we could find it.
We had the engineers run through it. We got new commanding sequences from the Space Telescope Science Institute. We were able to run all that through, and then we executed on orbit.
We have to respond very fast. We produce a new schedule and set of command loads.
We can modify a lot of the flight software, modify how the instruments are commanded. It allows us to change. We can react very quickly. What Hubble has done compared to what we were thinking Hubble could do is just amazing. Hubble's had its fingers in almost everything, a neutron star collision, looking for all the supernova, all this stuff going on with dark matter, dark energy, exoplanets. Hubble has just been constantly finding new things. Now we're looking at these interstellar comets and these interstellar asteroids visiting us. It's really been spectacular to watch.
There really are two key aspects to Hubble's design that have enabled us to last the 30 years that we have, and that is really the redundancy that we have on board, and then it's the servicing, putting in new and improved instruments, and being able to improve the hardware with lessons learned over the 30 years of Hubble operations. We are now at our peak performance.
The Hubble Space Telescope has had a profound impact, not only on astronomy. It showed that humans in space and science can go hand in hand to enable us to explore space in richer ways than we could ever do with either just astronauts alone or just with instrumentation alone. By using these skills together, new vistas of exploration are open to us, and that lesson is something we're still benefiting from as we envision future space exploration.
Go ahead. Okay, we have a go for release. Okay, Charlie.
It's amazing with a program that's lasted the duration that Hubble has lasted, that the astronomers up at the Space Telescope Science Institute continue to come up with new things that they want to try to do with Hubble, and we certainly hope that we'll be able to continue to provide that kind of capability to them into the late 2020s and beyond. What you're looking at with a telescope, of course, is the light from billions of light years away. So the further you look, the more you're going back towards the Big Bang and understanding how the universe was formed.
The Webb telescope will be groundbreaking because it has capabilities that are different than the Hubble Space Telescope.
We have equipment that is so much more powerful than anything we've ever had before that it's almost impossible to tell what we will discover.
Hubble's accomplishments include something called the deep fields. Looking out into space and collecting light, sometimes for many days, these deep fields have revealed visually to us a universe absolutely teeming with galaxies, hundreds of billions of galaxies.
One of the neat things about the ultra deep field, and one of the things that made it so unique was how long it took us to take that image. There's an exposure time that's expressed, I think it's 11.2 days. There's a very, very long exposure time. But probably what's more important is how many orbits it took us to do that. 400 orbits of Hubble data to take that image. You only get 15 orbits a day. To take 400 orbits and say, we're going to observe this one spot in the sky for 400 orbits. And the really unique thing about that was they picked a spot where there wasn't anything. They looked and they said, there's absolutely nothing here. And they said, you want to spend 400 Hubble orbits looking at nothing? And they said, yes, because we want to see what it can see. And I think the results from the science, I mean, it was amazing. What they saw was spectacular.
Hubble had spent 2 weeks taking pictures of empty places in the sky, and they saw they weren't empty at all. They were thousands and thousands of galaxies.
We were amazed how many galaxies we've found, and we continue to go back to that portion of the sky to increase that visibility.
The Hubble Space Telescope is an outstanding time machine. It's incredibly important for our studies with the Hubble Space Telescope to realize that when we're looking at a galaxy, we're seeing it as it was millions of years ago, sometimes billions of years ago. It's taken that long for the light to get to us.
What you're looking at with a telescope, of course, is the light from billions of light years away. So the further you look, the more you're going back towards the Big Bang and understanding how the universe was formed.
What Hubble has revealed is that the universe has in fact changed over these billions of years of time. The early galaxies, the very distant ones as we see them, are simple. Sometimes they're messy looking, they're small, they haven't had time yet to form that grand spiral structure. Over time, we see galaxies actually merging with other galaxies and growing bigger and bigger, and those mergers can look like train wrecks in our Hubble images.
These very, very deep exposures that Hubble has been able to take, we have seen right to the edge of the universe. 13.5 billion years. When Hubble was first designed and envisioned, it was never thought it could actually see that far out. But because of the advances in the instruments that we've been able to put up on the telescope, and also the cleverness of the scientists, they've come up with very interesting observing scenarios, doing these really deep exposures where we just sit there for orbit after orbit after orbit, gathering the photons. We've been able to push Hubble out very, very far.
As Hubble looks out into these fields of galaxies, we sometimes see clusters of galaxies. These are galaxies that are held nearby each other by their mutual gravity. These clusters are massive conglomerations. There's so much mass that they have an actual observable impact on space-time itself. Einstein predicted that mass distorts space, but we didn't realize we could actually see the effects of that. But with Hubble, we have been able to see distortions in space around clusters of galaxies. The way we see that is when light from a background galaxy travels through that cluster of galaxies or around it due to this gravitational lensing effect. The lensing also magnifies that background galaxy, so if we look in some of these distorted arcs, we can see more detail than we would ever have been able to see without gravitational lensing, nature's boost.
There are observations where we're explicitly looking for the lensing, and they're getting science out of that just otherwise would just not be doable. Hubble has really taken that to a next level. It's doing large amounts of astrophysics that it's just never been able to do before.
Some of what we're doing with Hubble is to prepare for the new James Webb Telescope. which we anticipate launching in 2021, which will be able to see farther into the infrared part of the electromagnetic spectrum. That enables us to see some galaxies that are difficult for Hubble to see because they're so far away that their light is traveling through us through expanding space and gets stretched out into redder wavelengths, often far into the infrared part of the spectrum, even sometimes beyond what Hubble is able to detect well. The Webb telescope will give us more information about some of those very distant galaxies.
The James Webb Space Telescope is the follow-on telescope after the Great Hubble Telescope. It extends the discoveries of Hubble into the infrared spectrum region. We think that the first objects that grew out of the Big Bang material probably happened in about 100 million years after that start. And we think the Webb telescope can pick them up. They're rare, they're hard to find, but they should be there. The farthest we've been able to see with the Hubble telescope goes back about 800 million years after the expansion began. So we think we get much closer to the first objects with the Webb telescope.
Hubble gives information that the Webb telescope cannot give about visible and ultraviolet emission from things in the universe. And when we have all that information coming in at the same time, it's like a banquet of scientific return.
Now when we get the complete picture of every wavelength you can possibly see from ultraviolet to infrared, we hope to have the story of the growth of the first galaxies from the primordial material. So that will be a huge accomplishment that depends on both pieces of equipment, the Hubble telescope and the James Webb telescope working together.
So astronomers are very excited about this probability that we'll have both the Hubble Space Telescope and the Webb telescope operating at the same time for quite a few years. That will give us an abundance of new understanding about the universe. And already right now with Hubble, we're doing preparatory observations for the Webb telescope. We're using Hubble to do things, for example, like surveying distant galaxies to find out which ones would be prime targets for the Webb telescope. In fact, scientists around the world are proposing observations with Hubble right now specifically to help us learn information that will be useful for making the best use of the Webb telescope as soon as it's launched and gets going in its science observations.
I think the Hubble telescope has been the most productive science instrument ever built. In astronomy, there's what we knew before Hubble, and now there's what we know after Hubble. They're so different. Of course, Hubble has now had a life of 30 years, so it's had a long time to make this revolution happen. So it's not all at once. It's a gradual revolution, but it's still a huge revolution. Technology has changed dramatically over the 30 years of life of the Hubble telescope. So you couldn't even have imagined when the Hubble was launched that we would have the wonderful cameras and spectrometers that we fly today. We figured out how to send astronauts, we trained the astronauts, we figured out what instruments could be put in, we figured out how to repair everything that went wrong on the Hubble, and it's still alive. It's today, 30 years after launch. And I am so thrilled to say that our people were able to do that. That's the operations team that makes this possible. It's a miracle as far as I'm concerned, because it didn't have to be that way, but they made it happen.
Imagine you are on the moon. Your job for the next 8 hours will be exploring, traversing up and down lunar hills, sampling rocks, and setting up equipment. Temperatures can reach a blistering 250 degrees Fahrenheit. Luckily, you have a portable life support system, a backpack that provides oxygen, water, power, and, for the excruciating temperatures, a cooling system. Under the Artemis program, NASA and its partners are planning to return astronauts to the moon, and the agency is testing new spacesuit technologies. As a new age of exploration heats up, engineers are looking to improve how to keep astronauts cool in space. Outside the International Space Station, astronauts perform extravehicular activities, EVAs, also known as spacewalks. During the Apollo era, spacewalks took place on the lunar surface, and with the Artemis program, humankind will once again return to live and work in the harsh environment of the moon. Future plans call for spacewalks to last longer and be more demanding, not just on the astronauts, but also on the spacesuits and systems that protect them and keep them alive and healthy. NASA has been working on advanced technologies needed for next-generation spacesuits. NASA's reference design, the Exploration Extravehicular Mobility Unit, or the XEMU, features greater mobility, visibility, and flexibility. This prototype is just the beginning. To meet the needs of future exploration as part of the Artemis program, NASA will share its newest designs, research, and data with commercial industry, whom NASA will partner with to build the next-generation spacesuit. It is an effort that will benefit from NASA's most recent studies and the agency's 50-plus years of spacewalk experience. Spacesuits are essentially a spacecraft made for one. They have many important life-preserving components, but none is more complex than the system to regulate the temperature of the astronaut. Engineers call this cooling system the thermal control loop.
The thermal control loop is part of the portable life support system, or the backpack that the astronaut wears when they do an EVA. The thermal control loop is designed to keep the astronauts cool. When the astronauts are doing spacewalks, they can be exposed to extreme temperature swings, say up to 250 degrees Fahrenheit. The thermal control loop is part of a system that consists of a liquid cooling ventilation garment, or LCVG, that the astronauts wear under the spacesuit. It consists of tubes that are filled with water that circulate from water pumps in the backpack to keep the astronauts cool.
During the Gemini program, engineers realized that astronauts not only needed protection from the temperatures of space, but also from the heat generated inside the suit, from their own bodies as they worked. Originally, the suit designers thought that airflow over the astronaut's body would keep temperatures regulated. What they discovered was that air cooling in a spacesuit is insufficient to do that job. During the Apollo era, it was decided running cool water through a garment that covers the body could help keep the astronauts from overheating. The means of cooling the astronaut was now an essential life-sustaining element to the spacesuit and was here to stay. The spacesuit currently in use on the space station, developed in the 1970s, also uses a water-cooled garment. Circulating water is still the best way to cool an astronaut. However, improvements can be made on how to move that water through the system, using new technologies and materials to test how to make the essential cooling system safer and more reliable than ever before. The result of this research is SERFI, the Spacesuit Evaporation Rejection Flight Experiment, all the critical elements of a spacesuit cooling system in one box. 2 SERFI units have been built, one to work here on Earth in our gravity, and another SERFI unit meant to be tested in the absence of gravity, in space. On board the International Space Station, astronauts take advantage of the microgravity environment to perform a variety of science experiments and to test exploration technologies. When engineers developed the spacesuits for the Apollo and Space Shuttle eras, NASA did not have a space station in operation. Today, the station presents a perfect platform for engineers to use microgravity to put the SERFI cooling system to the test.
In that experiment, we will test a couple different versions of the water pump that will be used to circulate the water through the system. We'll test temperature sensors, we'll test pressure sensors, integrate all those into one little package and test them for long duration to see how they'll perform over the expected life of a spacesuit.
SERFI shows how the water will move through the system as if it were inside a spacesuit, cooling the astronaut. But a spacesuit cooling system needs to do more than just circulate water. As the astronaut works, their body generates heat, which is transferred into the liquid cooling and ventilation garment. A thermal control loop needs a way to remove the heat from the water that is circulating through the system. That's where SWIMMY comes in, the spacesuit water membrane evaporator.
SWIMMY consists of some porous hollow fiber membranes that are contained in a metal manifold. When warm water flows through the porous membranes and then is exhausted into space, the cool water continues through the porous fibers and continues to flow through the LCVG liquid ventilation garment to cool the astronaut.
With the means to run a cooling system and offload heat and gases, the SURFY unit runs for 8 hours at a time, the span of what a spacewalk might last in space or on the moon. The tests are run again and again, simulating the rigors of what a spacesuit thermal control loop might encounter during its life cycle. Astronauts take water samples from SURFY for analysis. Just as a spacesuit might sit in storage for a time between spacewalks, like during a trip to the moon or Mars, SURFY is sometimes switched off. This time of dormancy is when contaminants can grow in the system.
That's when the bugs, the microbes, grow in the water system. And those little guys grow and they reproduce and they can grow through the system. They'll clog your filters, and once your filters get clogged, the water stops flowing.
When the water stops flowing, the suit stops cooling. Contaminants in the water are such a problem for current spacesuits that astronauts set aside time for regular water maintenance chores every 90 days. The SURFY tests hope to demonstrate that new technologies and materials will be far more robust in working through water contamination issues, reducing the risk of the cooling loop failing.
We don't want to have to worry about water quality. We want to be able, we've joked among the team, we want to be able to pour chicken soup into the exploration EMU and it'll still run the way it's supposed to run. Even if there's microbes in there that the system doesn't care. So we want the filters to catch the microbes, and if the filters don't catch the microbes and they flow through the pumps don't even notice the microbes or the contamination or whatever's in the water. They keep operating the way they're supposed to operate. We want our crews to be spending their time exploring, not running maintenance procedures on our spacesuits.
All the testing for SURFY in space is duplicated on Earth, with a twin SURFY running in 1G, Earth's gravity. By testing here and simultaneously testing in the microgravity of the space station, engineers can infer how the cooling unit will run in the 1/6 gravity of the Moon, the 1/3 gravity of Mars, and all points in between. The knowledge gained from building and testing the twin SURFY units is already paying off, as work is underway building a full-size backpack for NASA's prototype exploration spacesuit.
How's it going to perform in microgravity? Well, by sending SURFY to space station, we can actually test how it's going to perform in microgravity. That in itself buys down the risk. So now there's one less unknown that we have to worry about when we send our hardware off to do what it's supposed to do.
I am so excited that SURFY, SWIMMY is on orbit, that we're working great, our ground unit is working great. SURFY has made a difference. We've had engineers, scientists, thermal analysis, water experts. It's been an exciting multi-discipline collaboration.
It's a collaboration that will inform spacesuit technologies for the Moon and beyond. A new design for a thermal control loop and its ability to help regulate temperatures for astronauts during exploration can benefit from the data gathered from SURFY, making it one cool little experiment.
This is a science mission on par with Apollo missions, Space Shuttle, International Space Station, and Hubble missions. For nearly 2 decades, thousands of people around the world, many spending their entire careers, built the James Webb Space Telescope. And it all comes down to this.
Once we launch the James Webb Space Telescope, there are no second chances. We have 300 single-point failure items, and they all have to work right. When you're 1 million miles away from the Earth, you can't send someone to fix it.
We've never put a telescope this large in space. We want to see distant parts of the universe humans have never seen before. Looking back in time almost 14 billion years to see the first galaxies that formed after the Big Bang. And we want to search for the building blocks of life in the atmospheres of planets orbiting distant stars. To unfold the history of the universe, we must first unfold this telescope.
This is the largest primary mirror, the largest sun shield, and the most powerful space telescope ever built. And yet, this large telescope needs to fit inside a 5.4 meter diameter rocket fairing. That's the largest fairing size available on any rocket, and it's the fairing size on our ride to space. The Ariane 5, provided by the European Space Agency, is one of the world's most powerful rockets. To cheat the fairing size limit, we built Webb to fold, like origami, to fit inside the rocket fairing.
And this brings us to our most challenging part of this mission, unfolding it in space.
Think of what you're doing. You're taking this extraordinarily delicate, precise, state-of-the-art scientific instrument, you're slapping it on a rocket, and for the next 8 minutes, the explosion from that rocket is following you into outer space. Vibrating you, shaking you. Everything that goes into outer space has to live through this environment and work once it gets there without having someone come to fix it.
Two weeks. That's how long it will take to fully deploy the Webb telescope. We can take longer if we need to, but those 2 weeks after launch are going to be nail biters. This is the Mission Operations Center at the Space Telescope Science Institute in Baltimore. Those 2 weeks after launch will be like our Super Bowl, World Cup, you pick the analogy. Years of training comes down to these moments.
The Webb Observatory has 50 major deployments, 50 depending on how you categorize them, and 178 release mechanisms must work to deploy those 50 parts. Every single one of them must work. Unfolding Webb is hands down the most complicated spacecraft activity we've ever done. Then again, nothing about Webb is easy. We've never done any of this before. There's nothing simple about sending anything into space. You can't do it without taking risks.
This mission is squarely in new spacecraft territory. Webb is the perfect example of science desire driving engineering capability to new frontiers. Webb's unique design was born from reasoned engineering to accomplish its science goals.
Here's the plan. Shortly after launch, we unfold Webb's solar panel for power and our high-gain antenna for communication. About 12 hours later, we have an important engine firing that sends Webb on the proper course towards its orbital destination, about 1 million miles away. That's where Webb will do its science. Webb will be moving so fast, it passes the moon's orbit in 1.5 days, half the time it took Apollo astronauts to reach lunar orbit. First, we lower the sunshield pallet, then raise Webb's primary mirror and instruments away from the sunshield. The solar wind will push us around with the sunshield open, so we'll unfold a trim tab to help keep us stable.
We got these huge, iconic, golden segmented mirrors that will help us deliver amazing new images from the cosmos. But in some ways, the sunshield is a lot more complicated, and it's just as essential. Without it, nothing works.
Here we've got 5 sunshield layers, or approximately 8,900 square feet, almost the size of 3 tennis courts, of very thin Kapton material, about 1 to 2 thousandths of an inch thick. Making them go where you want them to go in 0G is extremely challenging.
The sunshield shades the telescope from the heat of the sun, earth, and moon. The concept is simple, but there is nothing simple about the design or operation, especially when you get to space. Webb's Sunshield assembly includes 140 release mechanisms, approximately 70 hinge assemblies, 8 deployment motors, bearings, springs, gears, about 400 pulleys, and 90 cables totaling 1,312 feet. All this just to keep the Sunshield under control as it unfolds. First, we release these special restraints that protect the Sunshield during launch. They roll out of the way, but not all the way until we are ready to deploy a side. Next, we release a set of covers over the core region. Now comes the critical point. All 107 Sunshield release mechanisms need to fire on cue. 107. They free the 5 Sunshield layers, allowing them to extend as the mid-booms deploy.
Sunshield fully deployed, we start setting up the optics. First, the secondary mirror is extended and locked into place, and a special radiator behind Webb is extended, which helps further lower the temperature of the science instruments. Finally, we open the primary mirror's wings and lock them in place. With that done, Webb is in its final configuration, but we're not done yet.
After 47 deployments, and accomplishing the hardest spacecraft unfolding NASA has ever done, Webb still won't be ready for science.
While the instruments cool, we'll control motors behind each of Webb's 18 mirror segments, a secondary mirror, and the fine steering mirror located inside the center of the primary mirror. We'll precisely align the mirror segments to form a perfect mirror. Then, Webb will be ready to explore the cosmos.
Flashing across California desert skies, the airplanes you see here are writing new chapters in the story of man-made flight. There she goes.
This is my first opportunity to greet you as Deputy Administrator of the National Aeronautics and Space Administration.
Together, you and I must make our new agency
the most unusual place.
An organization that can challenge conventional wisdom.
We can engineer anything. We can write the requirements for.
We're going to make your idea work. This particular idea is quite disruptive.
A typical flight, of course, starts under the wing of the B-52 mothership.
This sleek, high-speed machine would have made Rube Goldberg proud.
The manner in which we fly re-entry from space on the space shuttle was pioneered on the X-15.
X-31 pretty much wrote the book on thrust vectoring, along with its sister program, the F-18 HAR.
And the observation of an occultation is one of the more challenging missions that Sophia can do.
Right now, we are looking at the dawn of a new era of aviation.
Flight loads is a crucial discipline. It is one of the areas that requires a good combination of both science and art. We often say that every airplane that we have ultimately goes through the loads lab.
In 1964, a new building was rising from the desert shore of Rogers Dry Lake. The tests this laboratory has conducted over the past 50 years have supported almost every type of vehicle the aerospace industry has to offer.
We do a lot of testing in the laboratories to make sure that components are going to withstand the environments that they will see.
Every time we go away from the standard configuration on a vehicle, it changes the loads, and we've got to understand how that affects the forces and stresses and things going on within the airplane.
We in the Flight Loads Lab have been interested in thermal testing for many years.
These specimens are being exposed to temperatures from 400 degrees to 1,000 degrees Fahrenheit.
In order to precisely calibrate the thermal effects on the strain gauges, ground heating tests were conducted.
Also, over the years, there's been low temperature testing using cryogenic cooling capability.
A cooling system was used to lower the glove temperature to the minus 30° Fahrenheit pre-launch condition. The heating and cooling systems work together to bring the entire glove to cold soak condition.
The type of loads that a wing will experience in flight are bending loads, torsion loads, and shear loads. They're loads that are applied to the wings as a result of the air loads that are put onto the airplane when it's flying or when it's maneuvering.
How far can we push it? Where is it going to fail and how is it going to fail? So this work here has really been key to being able to help us anchor the models that we're developing to analyze the performance of these structures and also to take that next step and optimize the design of these systems.
The second HIMAT aircraft underwent extensive ground vibration testing after its delivery to the UL Dryden Flight Research Center.
Any aircraft in flight has resonant modes which occur as its structure flexes under aerodynamic loads. These flexures can become rapid and large. Under extreme conditions, they may even result in structural failure.
In Dryden's Flight Loads Research Facility, mechanical vibrators are attached to portions of the aircraft structure. As the aircraft structure is excited at known amplitudes and frequencies, its mechanical responses are carefully measured and tabulated.
So we're trying to understand how the airplane rings, basically like a bell.
You actually want to see the structural characteristics and how it behaves. Once you go and fly it, if you experience any like flutter or dangerous vibration motions, then it's practically too late.
We can tell if the structure is sound.
With all this data, we'll be able to update our models, which will be used in our flutter analysis to validate that we are good and can give flight clearance for the vehicle.
Inertia testing, understanding basically how the mass is distributed around a vehicle, which gets important for the control laws.
The moment of inertia essentially tells us the angular momentum properties of the vehicle. We want to understand during flight, when we're trying to control it, how it pitches up and down, we'll understand how much resistance and inertia happens during those pitching maneuvers.
We need to know for certain that our sensors are behaving properly so that when we put them on our structures or put them on our vehicles, we actually believe the data that's coming off.
Not only test a large test article, but to bring in some new test techniques like the FOSS and really calibrate that against more traditional strain measurements and the finite element modeling.
The Flight Loads Lab here at NASA Armstrong performs some of the most sophisticated tests that I've seen on vehicles, flight vehicles as well as entry vehicles.
This facility is not only very unique, but it's a national treasure.
Hello everyone, I'm astronaut Randy Bresnik, living and working aboard the International Space Station. Now, on the space station, we live in a microgravity environment. Do you think the laws of physics will hold up? Come on, let's go find out.
The acceleration of an object depends on the net force acting on the object and the mass of the object, or F equals ma.
Surely good show, Sir Isaac.
Here we see that once the force of the thrust is greater than the weight of the vehicle, the rocket begins to accelerate.
All right, we're going to start with something small, something you might have at home. A little stick of chapstick. We'll go ahead and use our force being our bungee cord here. We'll put it on our bungee, and we'll pull it back. Let it go. And you can see how fast it accelerates because there's very little mass. Next, we'll try a little spaceship. A little more massive, and you can feel that because as you move it, you can feel that the kind of the force, the extra force you have to push with your hand. So we'll put our spaceship on our launcher here, same spot. Notice it's flying a lot slower than that chapstick did. What we've seen is the same amount of force on a smaller, less massive object means the acceleration is faster. Well, this is the biggest and most massive thing we have, so let's see how the acceleration is affected. Pull back the same amount on the force, and here we go. there you have it, Newton's second law of motion in action. Thanks everybody for exploring a little physics with me today. Now I'm going to send it back to Earth so you can start your experiments. See you again real soon.
It is great to be back at America's Space Coast, at this historic place with the men and women of the John F. Kennedy Space Center. And it's here today in the 21st century that the modern marvels that launched from these grounds prove that the public and private sectors are achieving far more together than we ever have apart. American businesses are developing new rockets, spaceships, satellites that are taking us further into space than ever before, and renewing our confidence that we can and will achieve the impossible once again. This truth echoes through the history of the Kennedy Space Center. Named for a president who challenged the American people to marshal the best of our, in his words, energies and skills, become the world's leading spacefaring nation. I know America will once again astonish the world with the heights we reach and the wonders we achieve. And as these feats of American enterprise and ingenuity attest, much more than the bridge to space, Kennedy Space Center is the bridge to the future.
It's a new era of pioneers, star sailors, thinkers, and adventurers.
3, 2, 1, 0. All engine running.
Let's go.
We have been given the scientific knowledge, the technical ability, and the material to pursue the exploration of the universe.
Our world is full of new and exciting inventions that continue to push the boundaries of technology forward. Every day, it seems something new is announced, developed, and implemented that changes how humans interact. Just in the past few decades, cell phones, internet speed, medical breakthroughs, and the reinvention of basic infrastructure is beginning to change the norms in our everyday lives. But have you considered how these changes in science, engineering, and medicine occur? To most of us, on the outside of these revolutionary practices, it seems like magic when innovations appear in our lives overnight. In reality, it's years of painstaking work, trial and error, and rigorous testing that occurs before a finished product is ever realized. Researchers in the world of engineering and science move in small incremental steps, slowly building a case for these new revelations until they are sure technologies are ready to be shared with the world. In fact, there is an old saying in research, quote, "An amateur works on a task until they get it right, but a professional works on a task until they can't get it wrong," end quote. Fortunately for all of us, over the past few years, NASA, the FAA, and industry have been engineering the next big idea that may completely change how we interact in our world with the implementation of unmanned aircraft. The idea for inclusion of these aircraft is not new. The basic concept for small flying vehicles has been in popular culture and in the limelight for quite some time. But until recently, these vehicles have rapidly accelerated off the drawing board and into the skies. Over the past few years, NASA has been testing and validating research associated with unmanned aircraft through a project called Unmanned Aircraft System Integration in the National Airspace System, or UAS in the NAS project. This project spanned several years and addressed many of the early concerns of how unmanned aircraft would be integrated into our national airspace. After years of study, the UAS in the NAS project has tackled many of the early concerns. But one last big hurdle remains: to successfully demonstrate how unmanned aircraft will work in harmony within the national airspace. With this in mind, the final phase of testing, called the Systems Integration and Operationalization Demonstration Activity, or SIO, has begun in earnest. Throughout our country, at various NASA field centers and other testing locations, NASA has assembled a core strategic group of researchers to analyze and test unmanned aircraft through the SIO demonstration. Some of the key flight activities will include using various sized unmanned aircraft built by 3 different companies to highlight commercial UAS missions that have the potential to provide economic and public benefit to the American people. Throughout the testing, NASA plans to document best practices and lessons learned from the SIO activity and provide it to the UAS community to prepare us for routine commercial unmanned aircraft operations in our communities. On this episode of NASA X, we will take a look back at years of testing and development that have led up to the SIO demonstration flights, and we'll meet the companies that are helping to make these flights happen. This research and engineering has the potential to influence a massive shift in how we receive products and services, and may ultimately make an impact on how people travel and interact in our world. To understand why the NASA team has set up the SIO demonstrations, we first have to look at why integrating unmanned aircraft into the NAS is such a Herculean effort. Here in the United States, we arguably have the best air traffic management system in the entire world. During normal times, around 50,000 flights take off and land daily, with nearly 3 million airline passengers traveling across the more than 29 million square miles that make up the U.S. national airspace system. In that system, close to 15,000 air traffic controllers, 4,500 aviation safety inspectors, and 5,800 technicians operate and maintain services for our National Airspace System, or NAS. It has more than 19,000 airports and 600 air traffic control facilities. In all, there are 41,000 NAS operational facilities and over 71,000 pieces of equipment, ranging from radar systems to communication relay stations. With all of this infrastructure, integrating unmanned aircraft systems into the NAS will be demanding, to say the least. But this integration is of vital importance to our country, because these new vehicles will be part of the next revolution in national security and defense, emergency management, science, and in commercial applications. For these reasons and more, NASA set out in 2009 to work on several main objectives for the project that included providing research findings that utilized simulation and flight tests, supporting the development and validation of detect and avoid and command and control technologies, and finally, the SIO demonstrations themselves. Two of the biggest challenges that needed solutions before the SIO demonstrations could take place was in the key areas of detect and avoid and command and control. For detect and avoid, one of the primary safety concerns with integrating these new systems is the inability of remote operators to see and avoid other aircraft. On all flights with pilots on board, the FAA requires the crew to be aware of all other surrounding aircraft, either visually or using onboard instrumentation. So in addition to instruments, the pilot physically looks out of the window to help safely avoid other aircraft. Because unmanned aircraft literally don't have a pilot on board, NASA and its partners worked on concepts and designs that allowed safe operation within the national airspace.
What detect and avoid is since the pilot for an unmanned aircraft is either remote off the aircraft or not there at all in the case of an autonomous aircraft, there is no human eyeball to go see other aircraft. So the technology needs to be developed to use other means such as radars or cameras to be able to detect where other aircraft are flying in the proximity of your aircraft, your unmanned aircraft, and then be able to somehow, like a pilot would, avoid those other aircraft. And the way that's done is through developing some mathematical algorithms to be able to direct the aircraft to a location that would be safe. And so that's the kind of research that NASA wanted to focus on, because that was the most critical aspect of how to safely integrate unmanned aircraft into the national airspace that industry writ large could not really understand.
The second hurdle was with command and control. Because unmanned aircraft are completely different from crewed aircraft, new techniques needed to be developed, including improving the avionics on board the UAS and on the ground. These aircraft must have reliable, safe, and secure data connections at all times while operating in the complex environment of controlled airspace.
Similarly, the command and control part of the UAS and the NAS project is based on the fact that most radio communications that are operated in the airspace now with pilots are voice communication. So it's a pilot talking to an air traffic controller or talking to other pilots, and they use voice to do that. Well, so the aviation spectrum that's been set aside for voice control doesn't work for an electronic control, because if you're going to control the aircraft through some sort of communication methodology, it's got to be done electronically, because you're sending a message to the aircraft to be able to turn or to be able to climb or descend, etc. And so the technology that NASA worked on was to develop a radio that could be used in that bandwidth, that spectrum bandwidth, to be able to send electronic messages to and from the vehicle, and thus be able to command the vehicle. So that's why the command and control work that's been done under the UAS and the NAS project is so important.
Over the years, researchers time and time again showed that they had developed the detect and avoid and command and control technology to the point where it could be reliably tested in real-world conditions. Although there were other flight demonstrations throughout this project, the last major hurdle of flying the SIO demonstrations is now at hand. NASA, in partnership with the FAA and industry partners, have begun the demonstrations of potential commercial applications using different sizes of unmanned aircraft systems for the SIO demonstrations. The goal of SIO is to work toward commercial UAS operations in the NAS. In order to accomplish this goal, NASA has partnered with 3 pioneering companies to conduct flight demonstrations in the NAS that emulate commercial missions and begin working toward Federal Aviation Administration or FAA type certification.
When NASA was selecting the partners for SIO, we went through a partnership process that included the evaluation of a number of candidate partners. And we were looking for some key aspects that these partners could bring to the table. And so the first was really great domain knowledge in unmanned aircraft and associated technologies. The second attribute was knowledge of certification and the knowledge that's really needed to kind of take these vehicles from the concept and early development stages through to becoming a commercial product. And then the third thing we were looking for are viable commercial missions that would be publicly beneficial. We really wanted to showcase how unmanned aircraft can play a role in the future of the world and have a positive impact. There's 3 different companies that are participating in the SIO activity: Bell, General Atomics, Aeronautical Systems, and AATI. Bell is bringing their AP-70 unmanned aircraft, which weighs approximately 300 pounds and is capable of vertical takeoff and landing and operations around urban areas. The primary mission that they're focused on is emergency medical supply transportation in an urban area. General Atomics is utilizing their Sky Guardian unmanned aircraft for multimodal long-endurance infrastructure inspection. That unmanned aircraft weighs approximately 12,000 pounds, so it's much bigger than the others that are participating in SIO, and is intended for an infrastructure inspection mission at altitudes above 10,000 feet. AATI is using their AI Ranger unmanned aircraft, which weighs approximately 180 pounds, for a pipeline inspection mission at lower altitudes between 1,000 and 5,000 feet. And then lastly, throughout this process, we've been collaborating with the FAA, who has provided extraordinary support and helped us to navigate the regulatory process that's in place for these demonstration activities.
The 3 partner companies are each using various sized and different types of unmanned aircraft configured for the SIO demonstrations.
Over the past several years, actually going back probably a couple decades, NASA has been working on UAS, first more in the technical side and now maybe more on the standard side. And I think the SIO activity was looking, or the objective was to address some of the gaps that still remain. And one of the ways that we were able to do that is by partnering with some companies to go after some of these things. The outcome of the demonstrations is to try to help the companies really get their arms around some of these barriers that still exist, work with the FAA to develop the processes, the solutions to be able to address some of these gaps, and then bring it to a place where the industry can learn off of those lessons. The aircraft that are participating in the SIO activity are really pretty unique, and they span quite a range. We've got airplanes that have propulsion systems that are all electric. We've got a turboprop. Another one is a piston powered. So from a propulsion side, they're pretty distinct. And then even if you look at the way that they just operate, one takes off like a conventional airplane would take off from a commercial airport. Another one can basically launch off of almost anywhere and just land on some clearing. And then another one actually can take off also from anywhere, just vertically, and again landing vertically. So quite a range, even in altitudes, the way that they operate. Some of them were designed to operate at lower altitudes. Some of them were designed to be able to go pretty high, even maybe 40,000 feet.
Each company offers a unique perspective and engineering goal in performing the SIO tests.
So Bell's participation in NASA SIO is really about making sure we get the data that the regulators need to be able to understand not just the aircraft requirements, but the system environments for being able to get advanced aerial mobility actually into commercial space, integrated with the rest of aviation in the national airspace. Bell's actually been doing unmanned aerial vehicles for quite some time. From a commercial standpoint, APT is, a sizable vehicle, a little over 300 pounds, carries 70 pounds of payload. It's critical that we get this right so that we are safe and compliant in the airspace, and that's a part of what NASA SIO is about. They're a trusted data provider for the FAA and other regulators to be able to help us understand what really is required for the aircraft, for the airspace requirements, and then for the integration of those systems together. So NASA's involvement helps drive the technology to a high enough level that we have sufficient data for the FAA to make regulations. I would say the way it's being done right now is innovative. You see, NASA leaning forward with electric and hybrid propulsion, as well as, detect and avoid, and some of the things that we need for the airspace. You see the FAA leaning forward based on their small unmanned experience and knowing that we need to get out in front of this time to make sure that we do it right as we get to larger vehicles. And so that partnership and kind of active arrangement of let's discover together and work together towards what's both safe and economically viable as an overall community is really new.
On this particular mission, the APT-70 was armed from a ground control station, then was instructed to initiate a vertical takeoff. Per its design, it then rotated to fly on its wings, where it was nearly silent to the researchers below. It flew at an altitude of 500 feet above ground level, transitioned in and out of Class B airspace, all while staying in constant communication with the ground station through a redundant data link. On board was the prototype airborne detect and avoid system that provided the remote pilot with awareness of air traffic in the vicinity and recommended flight maneuvers. Initial results were promising, with more validation and testing to continue in the future. Another partner, General Atomics Aeronautical Systems Inc., or GA, flew their Sky Guardian aircraft. It had been used for unmanned missions for many years, totaling more than 6 million flight hours. For this NASA mission, a demo aircraft piloted remotely from California flew for 9 hours from its Gray Butte Flight Operations Facility near Palmdale, California, to Yuma, Arizona. Data was collected from the Detect and Avoid system to provide situational awareness of air traffic near the Sky Guardian. This system includes a traffic alert and collision avoidance system used in manned aircraft which fly in civil airspace, and air-to-air radar to detect and track nearby aircraft that may not have active transponders. The particular aircraft in this test may provide services that include hundreds of miles of inspections of rail, power line, communication and canal infrastructure, agriculture monitoring and topological surveys, as well as wildfire and flood monitoring. According to GA CEO Lyndon Blue, quote, GA's work with NASA is opening the eyes of regulators to the safety and utility of unmanned aircraft systems and the performance of certain tasks for public and commercial good, end quote. Researchers believe these types of aircraft will also play an important role during crisis management events, such as wildfire containment. The onboard airborne sensors can see through thick smoke, enabling the craft to inform ground personnel about the location of fire lines so they can deploy resources more efficiently. The SIO demonstration also highlighted how the aircraft can be used for many other civilian and commercial missions as well. The third demonstration flight was a team from American Aerospace Technologies Incorporated, or AATI. Although AATI's craft was considerably smaller than the other test vehicles, its use case was invaluable. It can fly at medium altitudes and carry advanced sensors used to patrol our nation's more than 500,000 miles of midstream pipelines, providing a fundamentally new and unique capability that changes the way we manage health, safety and the environment, respond to disasters, optimize operations, and leverage human capital.
So the mission itself serves multiple purposes. We're proving out the capability of beyond visual line of sight UAS in the national airspace. And the specific applicability for this mission is that we are looking for ways to make critical infrastructure inspection processes safer and more efficient. And so for this specific mission, the Air Ranger took off from our launch and recovery site, and we flew downrange along a oil pipeline which is buried underground, and we performed an inspection of the right-of-way of that pipeline. And we are proving out not only the applicability for critical infrastructure itself, but we're proving out the safety case for actually operating UAS in the NAS, not only utilizing the aircraft's technology for flight, but also utilizing different technologies for safety, such as detect and avoid systems, ADSB, and flight radar notification systems for having situational awareness of not only what's in the airspace around us, but being able to tell others in the airspace that we're flying as well. In my opinion, to safely regulate and certify these types of aircraft to fly, you have to prove out three different things. You have to prove out that the aircraft itself is mission capable. You have to prove that the aircraft is dynamically capable to change for different conditions. And you also, most importantly, have to prove out the safety case. And so utilizing different types of technology, utilizing different processes and workflows, building the safety case around operating procedures, and integrating all of these different components aside from the actual flight itself, really build the roadmap and really set the stage for the rest of the industry to say, hey, look, this is what the infrastructure looks like, this is what the framework looks like to do this on an operational basis in the future.
Although the SIO demonstrations are now complete, NASA and industry will continue to move forward with exciting new technologies and hardware built on the foundation of successful data collection and testing from the SIO activity. The future of unmanned aircraft is bright. UAS will continue to advance scientific research, benefit environmental protection, assist with disaster mitigation, and move more people and goods to their desired destinations safely and efficiently for decades to come.
This was just the results of a project with a specific goal that we had within NASA Aeronautics, but it's certainly not the end. I mean, integrating UAS into the national airspace is an evolving thing. There are many more challenges, there are many more use cases that the industry is going to come up with. And so we're sensitive to that, and we're keeping an eye on that so that we can really align our research with those areas that are emerging, and hopefully so that we can enable those to really be to come into fruition for the benefit of the American public. And so as we stand up new projects, we'll leverage our experience with UAS and the NAS project, but we'll do it into new areas, whether it's autonomy or other areas of research that will really enable a lot of these use cases and bring about some pretty exciting new markets for the country.
You know, there's this big unknown. You're headed out into this alien landscape that's just completely hostile to you. And you know, if you didn't have a nice ship and extremely warm clothes, you probably wouldn't be able to survive. And so, Mosaic as a whole, it's a year-long drifting expedition. So it involves people from 20 different nations, about 600 scientists. It's a huge, massive effort meant to study the Arctic as a system, not just the ice, but things like the atmosphere, the ocean, biogeochemistry, all kinds of things in a way that allows us to look at what's happening throughout the course of the year. So we left Tromsø on September 20th. Took us 10 days or so between leaving port, sailing out, picking up some instrumentation, and then starting to sail into the ice pack and starting to search for the flow. It was really difficult to find the flow because we needed ice that was thick enough to support all our equipment. Some of it's very heavy, and to do this safely. And actually, one of the big surprises to me and a lot of people on board was just how thin the ice was. You'd get out on the ice, but it's dangerous. It's an alien landscape. It's cold, there's bears. The polar bear situation was really interesting, and kind of terrifying. When we were out on the ice and we were setting things up, taking measurements, the bears did come back 2 times when I was there. And they came to our camp and they were doing things like messing with the equipment and going through our site. So there it was different because they're more on the turf that we had set up. You know, this is our turf now, and now they're coming in, and I could see them in places that I had been. So we were very isolated on the polar stern, and we had very limited connectivity. We had an email account. We could send 50 kilobytes a message. It was a big change for me and a lot of people said, you know, after a week or so, I didn't miss it anymore. And I was one of those people. I really appreciated being a bit more isolated for a while and experiencing life in a different way. Doing field work like this brought me right there to the ice. When I do my research, I use data like this from the data that's taken up close on the ice. Sometimes that's the only way to get information on the ice. Things like how dense is the ice or how dense is the snow. You can't do this remotely. But we can use this to do calibration and validation of ICET2 over the course of the year. So this is valuable for improving the retrieval techniques that we use for ICET2. For me to be on the ground and get that different look at the ice and the surface, it just helps me as a scientist come up with new ideas and to inspire me to use the data that I have and then think about this in a totally new way, in a different way.
In the beginning, the void, the darkness, then light, then life. And from life came man, joining the caravan for the long, slow journey through a world of discovery, invention, exploration. His marks, his milestones, stretch out through the centuries. His footsteps echo down through the corridors of time. Time. July 1969 in Florida. The footsteps, the caravan quickened. The corridors shortened as man reached outside his world into another void. Today in Florida, they go about their lives, taking only a sideways glance at the reminders of that milestone. Reminders, images that vaguely jog our memory.
This is Apollo Saturn launch control is aiming toward a planned liftoff time of 32 minutes past the hour. The start of our launch window on this mission to land men on the moon. The countdown still proceeding very satisfactorily at this time.
Time, it plays tricks on us. It smudges and blurs the sharp edges of reality. But we turn the trick and summon up our own reality, images, sounds, to help us remember.
The batteries all look good. The next time we go internal will be at the 50-second mark with those batteries, and they will remain, of course, on internal power during the flight. The lunar module, which has been rather inactive during these latter phases of the count, also is going on internal power at this time on the 2 batteries in the ascent stage and the 4 batteries at the descent stage.
They came 1 million of them to this place, drawn by the magnet of history in the making.
The astronauts, the prime crew, were awakened at 4:15 a.m. Eastern Daylight and proceeded to have a physical examination in which they were declared flight ready. They sat down for the normal astronaut fare on launch day. As far as breakfast is concerned, orange juice, steak, scrambled eggs, toast, and coffee. The target for the Apollo 11 astronauts, the moon, at liftoff will be at a distance of 218,096 miles away. The astronauts departed from their crew quarters after checking out their suits. They departed from the crew quarters at 6:27 a.m. and some 27 minutes later, 8 miles away from the crew quarters at the Kennedy Space Center, atop the launch pad at Complex 39, 6:54 a.m., the commander, astronaut Neil Armstrong, was the first to board the spacecraft. He was followed about 5 minutes later by Mike Collins, and finally Buzz Aldrin, the man who's sitting in the middle seat during liftoff, was the 3rd astronaut to come aboard. The weather is certainly go. It's a beautiful morning for a launch to the moon. We expect a temperature of about 85 degrees in the Kennedy Space Center area. We're still go on Apollo 11 at this time. T-minus 25 seconds. 20 seconds and counting. T-minus 15 seconds. Guidance is internal. 12, 11, 10, 9. Ignition sequence starts. 6, 5, 4, 3, 2, 1, 0. All engine running. Liftoff. We have a liftoff. 32 minutes past the hour. Liftoff on Apollo 11. Tower cleared.
You got a bunch of guys about to turn blue. We're breathing again. Thanks a lot.
I'm going to step off the limb now.
One small step for man, one giant leap for mankind.
Apollo 11, Armstrong, Aldrin, and Collins. They and millions of others reached out and, in their own way, touched another planet. The images remind us that it happened, but not how it really was in the context of the times. George Lowe, one of the architects of the Apollo program, does remember.
If you think back at the period of the 60s, they weren't very happy years in general. We had, well, the ever-deepening involvement in Vietnam. We had riots on the campuses, riots in Watson elsewhere, 3 terrible assassinations. A great deal of strife and turmoil in the country. And yet all of this was overcome by one single event, and that was Apollo 11. The decade ended with it. It was a fantastic adventure that I believe helped overcome all of the bad things of the decade. It represented Americans to ourselves and particularly to the rest of the world as we like to see ourselves and as we hope the rest of the world likes to see us.
The equipment of Apollo, some of it is now in museums, artifacts from an age of discovery. These strange-looking objects, they're there as reminders that after all, it did happen, and it happened the way we remember. The facilities of Apollo, now silent and still. In Houston, Mission Control, the nerve center of manned flight operations. The chapters of space history, first Mercury, then Gemini, then Apollo, were written by the people who sat at these consoles. And these chapters of history came at us with breakneck speed. Christmas Eve, 1968, in the beginning, Apollo 8, the footsteps were quickening. A few months later, Apollo 9. The long years of preparation were contracting into days, hours, minutes. The first manned flight of the lunar module, the Spider. Apollo 10, the dress rehearsal for the real thing. In 5 months, 3 missions, and in the 7th month, the payoff. Then, the celebrations. The images and the sounds fade in our memories, but some things we can't forget. Names: Apollo 11, Armstrong, Aldrin, and Collins. Other names: Grissom, White, and Chaffee. They remind us that it wasn't all success and celebration. There was failure and tragedy. Early in 1967, the 3 crawled into the command module at Cape Kennedy for a test. There was a flash fire. All 3 died. After the shock came the long, painful job of picking up the pieces, learning the lessons, coming together for a common goal. The remains of the launch structure stand as a reminder that the goal was reached. These strange shapes, what do they mean? These towers of steel, what are they? Monuments or leftovers from some earlier age of discovery? In the long history of man, in the slow journey of the caravan, what point do these mark? Historian Arthur Schlesinger, I have no doubt at all that if posterity remembers the 20th century for anything, historians 500 years from now looking at the 20th century, it will be because it will be the century when man first began to break his terrestrial bonds and began the exploration of space. So that's it? As man learned, moved on, and discarded the earlier structures, he came to these. They're marked for further milestones, reserved for future missions, other reaches to other different voids. Historians 5 centuries from now will mark this century, this place, and they will further note that from the void, life, man, it took eons to reach this point. But once there, the centuries and years compressed into days, hours, split seconds of exploration. The wheel, the engine, the airplane, they came slowly at first, then with increasing velocity. And then this, so huge, so powerful, so different that no ordinary modern name would suffice. They reached backward through antiquity to Roman mythology, and they named it Saturn. Saturn. His father was heaven, his mother earth. Complex organization, the mammoth machines, the incredibly detailed technical knowledge, the dedication. It was all harnessed, sharpened to a fine edge, and focused. The program developed and matured. Apollo 17 was launched at night, and even the old hands, the hardened veterans of the space program, couldn't help but feel the awe, wonder, and excitement. In the excitement of the split second of exploration, man doesn't stop to freeze the moment in history, to look at it and ask what it means. He simply lives it out. But in the Apollo program, on their way to the moon, they found a way to live out their strange moments in those strange spacecraft. It may be the peculiar nature of Americans to make history and to have fun in the making. Fun because we, were confident of success. But the program teaches lessons. Confidence is a transitory thing. Apollo 13.
Hey, Houston, we've had a problem here. Can say again, please. Houston, we've had a problem. Stand by, 13, we're looking at it.
3 days out, barreling toward the moon, an explosion. No one would see the problem for some time, but they went to work on it. The people of Apollo coalesced into a single dedicated unit. linked themselves with their technology, and cheated tragedy. A new chapter in space history was written in Mission Control. Eugene Kranz was the flight director when the problem developed.
Throughout this entire next several days, there was one dominant thought in the minds of all of the flight controllers. We teach them that between God, country, and your own capability, that you can solve any problem that may occur in flight. Throughout the entire course of Apollo 13, there was never any doubt that we'd get the crew back. So there was a very positive approach, and with this kind of approach, you can solve just about any problem that comes up.
Solve any problem, country, capability, old-fashioned words during a time when some said the old-fashioned virtues were forgotten. Well, they weren't forgotten. They were translated into action, into programs which took man soaring above the surface of the moon, away from Earth, but always looking back on it. These divided thoughts, the moon, the Earth, run through the Apollo program a sort of theme. They went there flying in their graceful machines, but they always thought back to where they came from. Perhaps that's natural. The moon is a strange place for men to be flying to. If it's strange for men, for mankind, it's stranger still for the individual man. Harrison Schmitt, Dr. Harrison Schmitt, a geologist, he touched the moon and remembers how it was when Apollo 17 was making its descent, the last flight to the moon, the last time that man walked on its surface. Schmitt remembers how it was.
One's first feelings are a mixture, a very complex mixture of humility, excitement because of something you had planned to do was being accomplished, but of a great attention to detail, to the detail that you had thought about and learned about for so many years prior to the actual event. That detail keeps you occupied with where your hands are and where your feet are, which rung they might be. You try to remember, well, am I at the bottom of the rung? And then as one moves away and tests his way on the surface of the moon and looks around, and in my case, looked around a very magnificent valley, you see a rolling, hilly country that is interspersed with some blocky fields of rocks that you know because you've studied the photographs, and you saw them as you descended surround large craters that have been formed in that rolling countryside. These rolling dark hills merge in the distance a few kilometers away with the very smooth but very bright colored slopes of the massifs. And they rise with a majesty to rocky tops that are almost beyond description because there's nothing like it that we have seen on Earth.
The Sea of Tranquility, Hadley Rill, Taurus Littoral. They were once strange names on the map of the moon, but the men of Apollo gave reality to the names by being there and showing us the places. They explored 60 miles of its surface, and their travels took them to craters, foothills, to explore, to observe, and to sample. The hard rock proof of Apollo, enshrined in the Smithsonian Institution in Washington, D.C., 478.8 grams of microbreccia under glass for mere earthlings to see and whisper about. Other rocks from the moon, 840 pounds, are being studied and talked about by scientists in laboratories around the world. Not only rocks, tens of thousands of photographs of those strange, exotic features of the moon. And telemetry, data on tape, facts, figures. The studies will go on for years, and the answers will come slowly, answers to questions about the moon and the solar system. The science of Apollo is not merely concerned with samples from past milestones, yesterday's missions. In a special room in Houston, men sit at consoles and command instruments on the moon to send them today's data. And they receive it today within 8 seconds of the command. Science, that's the key. And technology. And something else. In the drama of the moment, few stop to think of the essential element, the one thing that made it happen. People came to this program, government people, university people, contractor people. They brought to Apollo skills and knowledge and determination. This source of human intellectual energy was marshaled, focused, challenged. What came out of the effort was not just a very successful program, but a rich national resource of vast proportions. Crystals from the moon, the symbols of the science of Apollo. Behind it, causing it, was the spirit of Apollo.
I was strolling on the moon one day in a merry, merry month of December. Now, May's the month. May, that's right. May is the year of the month. When, much to my surprise, a pair of bunny eyes. That's the truth. You do that in West Texas and you get a...
We saw something of this spirit. We shared in the adventure, the excitement, the euphoria of being there. We shared it with the men who bounced across the surface of the moon.
Look at the size of that biggie. It is a biggie, isn't it?
And the surprise of discovery. We were there too, all of us, watching, vicarious explorers.
For the big boulder. Okay, we're headed that way. You get the tongs, John? Yep, I'll carry the rake. Look at the size of that rock. Can't believe it. Got it. I can't either. Okay, let's go on back. I am.
And the meaning, the significance of an occasion. That too came to us, flashed into our living rooms on our 19-inch window on the universe.
Countries throughout the world. We hope that this will be a symbol of what our feelings are, what the feelings of the Apollo program are, and a symbol of mankind that we can live in peace and harmony in the future.
There was also pride. They put up the flag and then posed for pictures as any visitor to a foreign place might do. The flag of each mission stood there as a reminder that we had been there, but there was the realization that in truth, it belonged to all the people. There are no boundaries on the moon. The focus was the moon. That's what it was all about. But by reaching up there, we, in a sense, came back here.
As one stands and scans a 360-degree panorama of his own, one of the first objects in the dark lunar sky that you see is a bright and beautiful bluish globe that we call Earth. This globe represented to all of us, I think, not only home, but a very fragile place that we have come back and felt that needed not only protection, but understanding.
They first went there in 1969. They last left there in late 1972. Between the beginning and the conclusion, they came to feel, to dimly perceive what it was all about, to come to a perspective on the meaning of it all. Poet Archibald MacLeish has said it better than most. To see the earth as it truly is, small and blue and beautiful, in that eternal silence where it floats, is to see ourselves as riders on the earth together, brothers who know now they are truly brothers. The excitement of the mission, the tension and drama of the splashdown, they remain only in our memories. And in time, they'll be replaced in the future by other missions, other memories. The moments of Apollo may be over, but the understanding and the discovery, they go on. And the full meaning, the real meaning, may yet be in the future too. But for now, for the present, the images and the sounds provide meaning enough to each in his own way and to each in his own time.
I call it the 10% rule. You got to be 10% smarter than the thing you're trying to operate. My name is Greg Cormouche, and I'm here to test rockets. We supply helium, air, nitrogen, and hydrogen so that they can use them while they're testing the rocket engines on the big stands. We have 4 compressors. Each compressor puts out 400 standard cubic feet per minute, and we send that to the test site. I'm a mechanical engineer. I did a lot of mechanical things besides go to college. I mean, I worked on my own cars, heating and air conditioning work. I was familiar with electricity. The first time I walked out on the engine deck and looked at a space shuttle main engine, I said, man, it was overwhelming, you know. Eventually, you know, you stick to it, and I was able to pick it up. The folks that work here are awesome. There's a wonderful group of men and women who keep this place up and running. When you're here as much time as we are, this place is like family. Being a part of the SLS program it's a life event, you know. This is going to be the culmination of all that hard work that everybody put in years ago.
Space Launch System is the next newest, biggest rocket that we're going to build, and it's not just a replacement for the Space Shuttle. This rocket is going to carry us much further than the shuttle would go. It's NASA's next big rocket for deep space exploration.
The SLS is a national capability that provides a unique access to space that America has not had in 40 years.
A large launch vehicle like this really opens the door to destinations beyond. It's not limited by destination. It's only limited really by imagination.
What we're focused on here at this center is the propulsion system. And that consists of 2 solid rocket boosters and a core with some tanks that feed some liquid rocket engines in the middle. And then the astronauts sit on the top in the Orion spacecraft.
One of the things we recognized for SLS is we had to be affordable. So we had to do things differently, more efficiently, and smarter.
We're all conscious about saving money, doing it more affordable than we have in the past. But at the same time, we can't sacrifice reliability or safety.
The system uses a significant amount of heritage hardware, which is things that we've evolved from the Space Shuttle program.
The Space Shuttle had two kind of candle-looking things, which are the solid rockets. Those are kept, and those are used on SLS.
We've added a segment to the 4-segment solid rocket boosters that we had on shuttle. That gives it more power, more thrust, and it helps this larger rocket get off the ground. What those boosters are for is just to get you going. They burn for a couple of minutes and then they fall to the ground. Then your liquid engines, you're up high enough, your liquid engines can carry your vehicle to as high as you want to go, and if you have additional stages, like we're going to have one, then you can go further out into space.
Right now, the inventory that we've got consists of 14 engines that have flown on shuttle. We've got one engine that was assembled and still needs green run testing or certification testing. We looked at all the spares. As we collected the spares, we determined that we could assemble a 16th engine. So we'll have 16 engines that we'll be able to use for flight.
We are making tremendous progress. We've got all of our prime contractors on board. We're testing engines, we're testing solid rocket boosters, our avionics systems.
J2X has recently set a record at Stennis. When we were testing, it was the first liquid oxygen engine to get to a full duration test in 4 tests.
We were developing this booster under the Ares program, and we're moving that into the SLS vehicle. The motor itself has been through 3 development firings, which are full-scale motors tested out in Utah, and we've gotten a lot of good data, engineering data from those tests.
This is an adapter that goes between the bottom of the Orion capsule and the top of the Space Launch System rocket that we're developing here at Marshall. It's been specifically designed to give strength to the adapter so that it can take the loads in flight and still be lightweight. This shape started out as a series of flat panels. The isogrid pattern was machined into the surfaces. Then they were formed, it was called in a process called bump forming, to make them into the shape that we need here. And we weld 3 of these segments together to form the cone that you see behind me.
We just delivered the first crew module to the ONC building at KSC. We've started a lot of the parts onto the outside of the CM, and we've actually put it in what we call the bird cage, so we can locate all those parts, within, thousandths of an inch to make sure that everything is going together okay.
Putting, wiring inside of it, putting tubes for the, for the propulsion system, putting valves and pumps, and so all of that happens in stages right there in the ONC building.
We have on contract with USA, United Space Alliance, to build our harnesses. They're set up shop in the ONC, and so their little shop delivers to the big shop.
Thermal protection is very difficult in re-entry vehicles to test and to model. I mean, really, you have to fly it to really understand what's going to happen. We're building ceramic thermal insulation tiles for the back shell of the capsule. We're building thermal barriers for the capsule, and we're building multi-layer insulation for that capsule.
I'm the heat shield design lead. So we're designing and building the heat shield for the future Orion missions.
The heat shield right now is in our big 20x20 router. It's a 5-axis router, and right now it's machining the interior bowl, if you will, of the heat shield.
To cut out that heat shield on the router, it could take weeks of machine time running multiple shifts.
It's the biggest heat shield ever constructed.
The other component is the heat shield skeleton, so that's the piece of the titanium substructure, the backbone that makes up the carrier structure itself.
Another unique thing is all the hand drilling that we're doing. So it's not automated by a router in this case, and it all has to be hand drilled by technicians on the inside.
200 plus titanium parts, all match drilled together.
So we have a tool that puts all the pieces in the right spot, and then we drill and high lock them all together.
MCC is transforming from supporting Space Shuttle and Space Station to a platform that will support Space Station and MPCB or Orion.
In order to adapt for the future, we need to go to a more modern system.
KSC will operate the vehicle all the way up until launch. We'll operate the vehicle till splashdown and the recovery forces come in and take over after that.
Fire Room 1 is the launch control room we're going to use for Orion SLS for EM1 missions. We've been working with the Orion program to get the spacecraft data so we can process it with our software in the firing room, and we will be flight following that mission out of Fire Room 1. We refitted the room, we redid it, putting the sound suppression carpeting on the walls, making it kind of a more comfortable place to work. So we're aiming for about 50 people in Fire Room 1 for an EM1 mission. We are actually using Fire Room 1 right now to test Pad B subsystems.
This pad is going to be almost like a complete new pad because we will have refurbished each and every system that it's inside the pad. We're going to have the vehicle launch from the mobile launcher, and not only launch from the mobile launcher, but have a tower that will have all the services attached to the vehicle. The tower is going to be on the mobile launcher. The vehicle will be assembled at the VAB.
It's a return to a concept that we knew that worked very well during the Apollo years when the mobile launch platform had a tower on it. We knew that the VAB was designed to accommodate a launch tower on a mobile launch platform. We have to make sure that the VAB can remain adaptable and accommodate different vehicle architectures. And now we have a clean VAB shell, per se, the infrastructure, so that we can accommodate the new hardware, the new vehicle access with new platforms. And that is the first phase of what we're doing now.
And once the vehicle is ready with all the connections, the only thing we got to do is move the vehicle to the pad, do the connections to the mobile launcher. And once we do those connections, we're ready to launch.
There was a time where I had to explain what a crawler was. If you didn't work out here at the Space Center, or if you weren't in the Central Florida area, a lot of people just, somehow the vehicle got out to the pad. We knew what to expect from a load perspective with the new vehicle, the larger rocket, and things along those lines. And that goes from the crawler lifted load, the hydraulics, also to the crawler way. We're going to have to increase the load lifting capability for the crawler way itself with the rock. What we've essentially done is keep all the same hydraulic components, but just increase the size, the diameter of the hydraulic cylinders. Last November, we actually took a ride out with the completed Crawler 2 out to the pad and tested out the systems and a couple punchless items, but everything worked great. The control system had been upgraded. The driver's cabs consoles had all been replaced. The brakes had all been replaced. Nearly every subsystem had some kind of work done to it. The traction support elements, each of the four corners has 22 rollers that are about the size of a car, to be honest with you, and we're changing out all of those, enlarging those as well.
What I love doing is reminding the outside world, whether it's within our government or especially the media, that has a perception that we're in a lull, there's nothing going on, that the space program's shutting down, to kind of dispel that rumor and say, no, this is the far opposite for us. We are utilizing this inter-program time frame to make all the modifications and all the infrastructure changes that it will help bring that agency vision into reality.
Many of us feel the country wants to go forward, and NASA has a big following, and every time I talk to people, they're excited about NASA.
enabling people to go beyond where they have ever gone before and look and discover things that they didn't even know existed it's just a real honor.
It's been a pleasure to be involved with this project, and I can't say enough for the team that's put this together.
I'm privileged to work this program. I think most people who are working it today feel the same way.
I can't believe they pay me for this job. It's just wonderful. It's great.
Very rarely do you get the opportunity to kind of literally from the ground up put together a factory whose sole purpose is to go make history and do exciting things for not just NASA but for America and for the whole world.
We're in the process of getting the factory ready for SLS production. And in that process there's a series of new tools that we've been installing in the factory.
Now we have not just put in new tooling, there's some legacy tooling that we're using. Most of the external tank buildings are being reused. We have a lot of construction going on for those, getting ready for a rocket that's same diameter but a little bit longer.
Not only are we using the legacy knowledge, the lessons learned, we're also incorporating new technologies.
The tool today is in the vertical friction stir welding center, and its job is to produce the cylinders that make up the parts of the tank that will be stacked.
And that is going to be the tool that joins every panel on every barrel for the rocket.
This device will actually do the weld in a single pass and then also do inspection. So these are the large barrel sections of the core stage that will be the foundation or the beginning rocket that will actually take our crews beyond the moon and really propel us into space.
Here at Marshall, we've designed the interface hardware in between the Orion capsule and that upper stage.
The MSA, I think, is a great example of a couple things. One, it's actually a piece of hardware that we're flying on an early test, but we're also going to fly for the long term. And so this is the same design that we'll use when Orion's on the SLS and we're actually flying people.
Today we've been taking the two unique pieces of hardware that are supposed to have a common interface, basically lowering them together, bolting and making sure that they fit.
Well, we're going to test a lot of the key systems on Orion and also for SLS with the upper stage of the MSA that are going to be used when we fly people into deep space.
Most recently, we've been involved with NASA with the SLS development using our unique forming technology along with our other core processes in terms of machining, welding, heat treating, and inspection technologies. Really is a one-stop shop is what the way you would describe it.
Right behind me you have the first weld development cap, or I think you call it the weld confidence cap. The production order will start deliveries in 2014. Spincraft also builds the domes for the upper stage Delta IV vehicle, which will be used for the EFT-1 flight, as well as the first two production flights of the SLS program.
For the SLS PDR, our primary role was the overall communication and outreach support that we provide back to Todd May's office for SLS. We provide all of the communication support for that particular team, that program and project.
Well, it's a preliminary design review, and primarily it's a technical review to make sure that the design is acceptable and at the appropriate level of maturity.
There's a lot of discussions, there's a lot of meetings across the board from technical, cost, schedule, performance data, safety, human factors.
It's like a health check on the program. Those of us that are working on the program, we've got our head down, we're doing our pieces, and sometimes when you're working real close to things, you don't necessarily see everything.
So there's so many moving parts and so many things going on at the agency, as well as the center, that to show people that we are moving in the right direction, to pull together a complete story of where we are as a program.
Watching at it from a higher level headquarters viewpoint, it's just gratifying to see the accomplishments that the teams have made and continue to make every day.
For CT2, we're doing modifications not only to make it last another 20 years, but also to uprate the load capacity. The main project we're working on right now is the roller replacement project, which is the roller assembly. It's actually the rollers, the shafts, the bearings that support the crawler. Actually, if you go there, you'll see trucks A and C jacked up and on cribbing. And that's the first time in the career of the crawler it's ever actually been jacked off the ground. So the guys have easy access to the roller assemblies. And they're in the process now of removing the old rollers, old shafts and old parts. Once they've done the line boring, that's when they'll start assembling the new rollers and the new shafts and the new bearings and the new sleeves and new adapters and new plates. So there's quite a bit of work, and that work will go, well, from August through October. So there's going to be a lot of trucks delivering a lot of steel here at Kennedy.
We started actually the new design for flame deflector as well as refurbishment of the flame trench, and that's because of the new requirements for SLS and commercial vehicles. We've started the demolition of the flame deflector. We've got concerns of, due to age and the debonding of the flame trench structure, this would possibly be a safety hazard for, our new program. And that's why we had to go in and do a new design and refurbish this flame deflector and flame trench.
These pieces here, they're not just one program, it's not just one mission, it's part of a capability that will enable this country to be a leader in space, to continue to take people from the Earth well beyond low Earth orbit out into deep space. And this is the hardware that will do that over multiple decades in the future.
So the work that's been accomplished so far is primarily structural type work, right? It's a lot of drilling, a lot of secondary structure installation, mechanical structures, the support structures. The next step is starting to install the subsystems. When we actually perform the welding on tubes for propulsion and the environmental controls and life support systems, those have to be at a higher level of cleanliness. When you look at the facility, there are these very large walls that are on the perimeter of the structure itself, and those are called HEPA filter walls. We can perform clean room work for the tubing concurrently while on the outside doing more standard clean rooms. So our goal is next summer sometime to turn the vehicle over, early summer, over to the ground operations organization so they can start their processing.
Well, the service module is attached below the crew module, and it has the prop tanks and the engine, radiators, solar panels. The service module all came in pieces. There's 49 composite panels on the SM. The actual structure itself is aluminum. That's the core skeleton where these composite panels were attached to. After the CM releases and the CM returns to Earth, the SM will just burn up with the upper stage of the Delta IV.
We performed two primary tests so far. The proof pressure test, which is just the pressure vessel, and that is put into the proof pressure cell. It's pressurized and a relatively high pressure. We're testing how well the vehicle was built. And then the follow-on test is the static loads test, where the vehicle goes through 8 different loads test cases. And so the vehicle is put under pressure, it's put under tension, it's put under compression. The whole intent is to simulate similar conditions that the vehicle would experience, say in flight, in launch, and also in landing and recovery.
We usually get the abort motor first, and for this mission the abort motor is inert, being a nominal flight.
We're going to have instrumentation on it to again understand more about the loads and environments that we expect to see in flight, but it will be an inert propellant that's cast into the motor.
This time we got the jettison motor next, and that's the only live component of this vehicle. We do a nominal jettison, the jettison motor fires, the last separates from the CM, and the CM continues on its mission.
One of the challenges of any new system is understanding the loads as you ascend up through the atmosphere and the dynamics, the acoustics, and we'll be able to gather a lot of that information.
The back shell
It looks, though it looks the same as what we flew on shuttle, it is different. We kind of took the best aspects and put them together to meet Lockheed Martin's requirements for the Orion capsule. Two major things we're trying to accomplish here. One of them is to prevent micrometeorite damage when we're on orbit for long duration. The other, of course, is the re-entry aspect. The skin that you see on the capsule, what you would see on orbit, sits on top of a composite substrate, what we call the back shell panel, that when combined together gives you the complete back shell. There's some sections that have some very complex geometry. So what we're going to do for the first time is take a substrate that's built by Lockheed Martin and put it together with the tiles that are manufactured by Jacobs and validate the fit up. Like any test vehicle, you're heavily instrumented. We're going to come back with a tremendous amount of data on how the system performed.
This first flight test of Orion is really to understand how the heat shield performs, and that heat shield's going final manufacturing at Textron.
Textron's had a long association with NASA and working in the space area for space protection.
The technology today has advanced tremendously. Our manufacturing technology has advanced, but ironically, we're still using a material that has proven itself for the last 40 years.
Avcoat is a very efficient ablator, and as an ablator, what it does, it allows us to protect the capsule from the high heating that occurs during re-entry.
There is no material, non-ablator material, that can handle that kind of heat. You have to shed away the heat. Basically what you're doing is you peel off the layers of the heat shield, you're taking heat with it.
When we apply Avcoat to the heat shield, we bond the honeycomb onto the carrier structure, and then we inject the Avcoat ablative material into the cells. The honeycomb acts as a crack arrestor and gives it rigidity and strength as a whole.
We know we're on the critical path for the Orion program, and so our employees are literally working all hours, all days of the week to make sure that we hit our schedule. We know there'll be more heat shields coming, and we're very excited about that. Our job is to make sure they're perfect.
The development programs I find just awesome, because this is where you're coming up with the new ideas, you're creating the new vehicles, you're pushing the boundaries in essence.
You can feel that we're going to go do this. The hardware is starting to come. The Orion hardware is getting ready for its first flight test down at the Kennedy Space Center.
The excitement is here. We are really ready to get going. So we are far from being out of space. We are really getting ready to go into space.
That's so rewarding to see our focus into what's next, because this really is our future.
I know the day that we fly this thing, there are going to be thousands of people that are going to be excited that are working on this, and the NASA workforce and the contractor workforce. We're going to be proud of the work that this team has done, and I think we're going to be proud of our country too. It's going to be a pretty exciting time.
I'm ready to build a rocket, and we are ready, and we want to build it on time.
Hi, I'm Lori. I study the planets, our solar system, and I especially love volcanoes. And this is Ask NASA. The thing I love the most about our solar system is that it's an incredible natural laboratory. We have so many different types of objects in the solar system, from planets and moons and asteroids and comets. We can study each one of those, and they all have something they can tell us about how the solar system formed or how Earth ended up in its special place. And understanding why the other planets are different from Earth actually helps us better understand how we ended up the way we are today. So this is a globe of Mars right here, and many of the reasons why we're so interested in Mars, there's a lot of different processes going on Mars that help us better understand Earth. A lot of the surface of Mars has been preserved for almost 4 billion years, and so we can study a lot of things on Mars that you can't even find on Earth.
Touchdown confirmed. Perseverance safely on the surface of Mars, ready to begin seeking the signs of past life.
So Perseverance rover is going to drive around and find some of the best rocks it can, drill down into the rock and soil and collect those samples so that on our next mission, Mars Sample Return, we'll be able to bring those back and study them in our laboratories here on Earth. There is volcano on Mars. In fact, there's lots of volcanoes on Mars. The largest volcano we know of in our whole solar system is on Mars. It's called Olympus Mons, and it is so giant that the entire chain of Hawaiian Islands could fit inside the crater at the top of that volcano. We see volcanoes really across the solar system on all of our rocky bodies. So on Mercury, we see evidence of lava flows on the surface of Mercury. Even on the moon, we have lava flows that we can see. On Venus, we see the entire surface of Venus is covered with lots of volcanoes and volcanic deposits. So this is a globe of the moon Io. Io is the moon of Jupiter. That's the most volcanically active body in our solar system. And that's because the pull of Jupiter's gravity on Io as it goes around Jupiter tugs and pulls at Io, and that heats up the inside, and that drives volcanoes. The heat needs to be released. This is the volcano Pele. And there's lava flows down here in the middle, but then there's also this big red-orange deposit, which is actually from explosive eruption of the gases that are falling down onto the surface of Io around the volcano. And it has no atmosphere, so if you were to turn it like this and look at this volcano from the side, you see a big umbrella of gas. The particles just come out and then they drop back down. And I started studying volcanoes on Earth about 35 years ago, and then started studying volcanoes on other planets, and that grew into my love of our solar system. So the asteroid belt really contains a lot of leftover material from solar system formation. You can imagine that when the solar system first formed, the particles kind of came together and made bigger particles. Some of those came together and created the planets. We actually find asteroids in lots of different parts of our solar system. We have asteroids that are near Jupiter, the Lucy mission, which is going to launch this year in 2021, and it's going to go study those special asteroids that are trapped in Jupiter's orbit. And then next year we have another mission called Psyche that's going to a particular asteroid called Psyche that looks to be made mostly of metal, of iron. It may actually be the exposed core of a small planet that may have had its crust blown off by an impact and left that metal core that we can see. There is definitely water on the moon. We know this because we've observed with some of our orbiters being able to identify that there's water molecules on the moon. And in fact, some of these we believe are preserved as water ice, perhaps in these permanently shadowed regions that are very, very cold near the poles. And what we need to do next is to actually go down to the surface of the moon and actually look at that ice up close. And so that's what we're doing with the Artemis mission. We'll be focused on looking for some of that water in the soil of the moon. We have explored really the far reaches of our solar system. We have sent missions to Mercury near the sun and visited all of the planets in our solar system, all the way out even to Pluto. And then one of our missions called Voyager actually has 2 spacecraft that have now even gone beyond the edges of our solar system. So we have really explored the whole expanse of our solar system.
Cool. Io and Mars are great.
Let's try it again. Oh, that's too hot.
That was a fastball. She had a fastball.
Do you have a question for NASA? Send your questions to our experts using hashtag AskNASA.
Welcome to NASA Edge, an inside and outside look at all things NASA. We're joined by Michelle Monk and Steve Gaddis. How you guys doing?
Great.
And we have a very important topic today, and that's going to be EDL, or Entry, Descent, and Landing. Now, Michelle, you're the principal technologist for EDL.
Yes.
What is Entry, Descent, and Landing?
Entry, descent, and landing is how we get a spacecraft from the top of an atmosphere to a planetary surface. So the entry part refers to, the atmospheric flight, most of it, and then we have descent and landing, which is usually propulsive and get us down on the surface safely. We do D and L at places that don't have atmospheres like the moon or, asteroids, but usually we talk about EDL when we talk about atmospheres.
So Michelle, what is your role as principal technologist for EDL?
I look across all the missions that NASA has coming up that will use entry, descent, and landing on any planet. And I look at the technologies we're going to need for those missions, and I bring them forward to the mission directorate for starting funding.
So you have a need in the EDL world, in the community. You're coming up with the technologies that are needed for future missions.
Right.
And so you take some of those technologies that maybe are less mature, hand them off to you.
Right.
And then you mature those technologies.
Design, develop, test, and evaluate.
Is that a pretty easy task, trying to figure out
Not at all.
what technology you're going to need?
Not at all. I have to look at both the human missions that are coming up, so, sending humans to Mars.
Right.
I have to look at the scientific missions that are coming up and all the destinations the scientists want to go to. And I have to kind of rank those and prioritize them and figure out, where they are in terms of maturity and what the best infusion point will be. When is the first mission that can use that technology? And then I have to figure out what is the best program within STMD for the investment. Is it better to have a university work on it, or a small business, or is it better for a game-changing program element?
And your job's really hard, because we're going to be talking about a suite of EDL projects over the next two shows, because there's so much content in EDL.
There's a lot of
We can't
content.
do this in one show.
Absolutely.
So this will be part one of two parts. So how do you manage all that?
Well, one is it's hard, but it's also fun. And we've got excellent technologists leading every one of these activities. So we all work together, and we all know that we need these technologies, so we're motivated to see them be successful.
We're a very passionate community.
Yes.
I've seen that in all the interviews that we've done. You guys are definitely passionate. Now, the first one that we're going to be talking about is ESM, or Entry Systems Modeling. What is that about?
So that's the first part of it, where they develop these models and simulations to understand how the technology works and how it will be beneficial at a system level. It's very cross-cutting against all the projects, and the plan is to take that data and then infuse it into the projects.
Blair had a chance to go out to NASA Ames Research Center to talk to Mike Barnhart, who is the Integrated EDL Systems Lead. Let's check it out.
Mike, tell me a little bit about Entry Systems Modeling Project. What is it?
So the Entry Systems Modeling Project is tasked with developing a lot of these technologies that are coming from lower technology readiness level, things like academia, and trying to bring them up to a level so that we're ready to help them.
So in this particular situation, we're talking about EDL projects, and so you're actually helping them raise their technology readiness level?
That's right. So any of these things, Orion, Mars 2020, Mars Insight, anybody that's flying anywhere in the solar system and they need to enter an atmosphere, you have to go through an entry, descent, and landing phase. And we don't have all those problems solved. We don't have all those technologies built. And so we're continually trying to improve on our existing technologies and also renew with new ideas. And that's the real purpose of the Entry Systems Modeling Project.
How do we get the data we need to improve the EDL process across these missions?
Right, so there's a lot of different things that we can do. We have ground facilities, which we rely on a lot. So we have arc jets that we do for material characterization and developing models for material response. We have our shock tubes, which we use to develop radiation models. We have wind tunnels that we use to build aerodynamic models, the dynamic motion of a body as it's flying, that sort of thing. We need to know all that in order to have a successful entry into a planetary atmosphere. So that's the simplest thing that we have access to every day. And then we also have, some amount of flight data. So there was the Orion EFT-1 flight last year, which was very successful, and we can use that to take our models and look at our predictions and then try and back out, exactly how well are we doing, quantify, how well are we predicting that.
You used a lot of data from the Apollo era. Are you able to use data from things like MSL and more recent missions to help? Because I know we have limited data on entry.
Yeah, so MSL is a really great example because we flew Medley on MSL, and that allowed us to get some of the only data that we've had on entry at Mars. So heating data, pressure data, which we use to reconstruct the aerodynamics, is a fantastic tool for us, but there's a lot of challenges there as well. So it's really, it takes a village. You need to have your computational models because they're the only thing that's going to access the true flight space that we have here on the ground. We have ground facilities that simulate parts of the flight space. And then ultimately you have a little bit of flight data. And your goal is ground to flight traceability. Let's predict what we do on the ground. Let's predict what we do in the air. And let's see, how far apart are we so that we can quantify when we're designing the next mission exactly where we think we'll be.
Are you sharing that data with all the different EDL potential systems that are being developed?
Absolutely. Absolutely. Everything that we do in the Intersystems Modeling Project is, for the greater good. We work very closely with academia. So we've got university partners that we are sharing this data with to help improve our models. We share it with other projects. So with radiation modeling, we were working very closely with the InSight project and OSIRIS-REx projects because they had issues with radiative heating on their back shell. So they call us because we're the radiation modeling experts and they say, here's our problem, tell us, how worried do we need to be?
Be worried, be very worried.
Yeah, we're always looking to help everyone else around the agency. And that's really what Space Technology Mission Director is all about, right? Is trying to help the other directorates with the technology that they're going to need.
Tell you what, great interview with Mike Barnhart. I mean, it really kind of gives you the flavor of how difficult EDL really is.
Right.
I mean, if you can't characterize it and model it here on the ground,
Yeah.
I mean, you'll never be able to land.
That's right.
And you can't test an entry system on the ground and get the flight-like data that you need to design.
And that's the challenge but with Medley on MSL, that was a game changer, wasn't it?
Absolutely.
I mean, you actually, for the first time, were able to actually see the health of the spacecraft as it was entering the atmosphere.
Yeah.
Right. As engineers, it's great that we succeeded, but I want to know if I got an A+ or a C- on the design. So the Medley data allowed us to actually know how we designed the vehicle.
And based on that Medley data, what were the results? They were pretty good, weren't they?
They were fantastic. But we found some things that we didn't know. Radiative heating is important at Mars and at the scale of MSL. We didn't recognize that before.
And now, since it was such an important mission for you guys, now you're going to take it to the next level for Medley 2 for Mars 2020.
For Mars 2020, yeah, we've got that going, and they're right in the middle of their preliminary design phase. Right. They're all excited. They're going to put some new measurements on the back shell.
Yeah, they were actually at Aberdeen Proving Ground last week doing some testing to see where to put the pressure measurement on the back of the vehicle.
Right.
So yeah, it's really exciting to get this new data in the back shell and using new sensors.
We know Blair had a chance to sit down with Mark Schonenberger, who's the reconstruction lead, which I got to ask you about that when we come back because I never heard of a reconstruction lead, but we're going to learn more about Medley 2. Let's check it out.
So Mark, when we think about the differences between Medley 1 and Medley 2, it's interesting because Medley 1, the M stood for MSL, Mars Science Laboratory. Now it's Mars 2020. You guys caught a break. You get to use the same letter.
We still get to use the same letter. I think it'll just be shortened to Mars, EDL instrumentation, and it'll hopefully continue for a bunch more Medleys, Medley 3, 4. We can always call it Mars.
Perfect. This nice little series you got going.
We're getting great data. So.
Now I'm wondering though, in terms of technology and in terms of how you're growing Medley, I mean Medley 1 was a very successful mission as far as the data we got back. What are we expecting for Medley 2?
For Medley 2, it's really to dig in and look at the pieces that we couldn't quite get for Medley 1. The instrumentation there was it was the first time we'd flown instrumentation since Viking to get pressure and heating data. So we really tried to capture the whole event. And to do that, especially for pressures. We had these transducers that could see the peak high pressure as you went through the hypersonic phase, and you're really slowing down around Mach 18. And then as you slow down, you really start getting in the noise there with the kind of information you can get. The signal is just really weak. It's sort of like using your bathroom scale to measure the ingredients for a cake. It's just, there's not a lot of resolution there. So it's tough. You don't really trust those measurements.
That's about how my cakes turn out, as
right.
if I measured ingredients with it.
So what we did here now is to use more of a postal scale for pressure. So we're measuring down at the low range when we're flying supersonically. Right as we get near parachute deploy, we're spending a lot of time just kind of slowing down, flying at the same altitude, but you're really at terminal velocity. You're not slowing down real well.
Now, is that pretty much in the part of the descent, if you will, that where you've burned away most of the heat shield that you're going to in the process?
Yeah, all the heating's over. It's still a little warm and things are kind of winding down, but yeah, all the exciting heating stuff is over, and you're really just trying to bleed off energy until you get down to a condition that's safe for the parachute. And so any error in your prediction of how that vehicle slows down, or your prediction of what the atmosphere is going to end up being on the day at Mars, can lead to being far uprange or far downrange. Your landing ellipse and how you target it, you need to account for that. So if we can get better data to characterize the aerodynamics, we can tighten that up and land in even smaller spaces.
Which is always the goal, right?
Yep.
You're trying to find out exactly where you need to land.
Yep.
So Mark, how is the instrumentation different on Medley 2 from Medley 1?
So, at least from where my experiences with the pressure side, Medley 1 was really designed to capture the pressure all the way through entry. So it had this nice high maximum pressure it could measure. What we really wanted to do for Medley 2 was to look for the low pressures right before chute deploy. We're going to be coasting there, slowing down from, say, Mach 4 down to Mach 2 for a minute, 100 seconds, something like that. And that adds to the landing ellipse, any error in the aerodynamics. So the transducers, we put more of them on the heat shield, and they're at a lower range, so they'll have much better resolution at those low speeds. So we can pull out things like winds, and we can get a better estimate of the drag. And we also have a pressure transducer on the backside. As you slow down, get down to supersonic speeds, the pressures on the back shell become a big contributor to the total forces acting on the capsule. And it's really hard to predict, actually, what those pressures are. So with some truth on the backside, that can really help us nail down the total behavior of the capsule as it's flying at those low speeds.
It seems like we're getting an awful lot of good data on the things that are happening during EDL and Mars, especially for Medley and Medley 2. Are we able to, in the future, maybe translate what you're doing here to potential different atmospheres or different EDL circumstances?
Absolutely. So Medley 1 definitely demonstrated, and it was the reason I think we have Medley 2, was it became the model of how you put an instrument package on a heat shield, how to work with the project to do it, so that they're not scared about putting holes in their pristine heat shield that's designed to keep their rover on the ground. We have a process now to do that. So you'll see missions going to Venus or Jupiter, Titan, those kinds of things. They'll all have instrumentation during entry, and NASA has the confidence to require that because we did so well with Medley 1 and hopefully again with Medley 2.
Mark did a really nice job discussing Medley 2, but I have to ask the question, in all my years at NASA, talking to subject matter experts from all 10 centers, what is a reconstruction lead?
Reconstruction is really important after a flight to understand exactly how and where the vehicle flew.
Oh, okay.
And without the proper data, it's really hard. You have to make some assumptions.
Okay.
So for instance, before Medley, when we didn't have an independent pressure measurement, we had to assume something about the aerodynamics of the vehicle in order to figure out how it flew.
Okay.
Now with that independent pressure measurement, we can nail it and we don't have to make any assumptions. So reconstruction lead is really key to understanding how we did.
See, you learn something new every day. I had no clue.
Yeah, he comes back up with that flight plan that
Right.
they had and where the data is along those flight plans. It's very important.
Now, speaking of that flight plan, with Medley 2, can you take the data from Medley 1 and kind of show what the flight plan is going to be for Mars 2020, or is that a completely different flight plan?
It's a lot the same because it's the same shape, size, vehicle. The mass will probably be a little different. They're using the same entry, descent, and landing system, but the atmosphere obviously will be a little bit different. The entry velocity will be a little bit different because of the different year.
Right.
But largely, you know, we're going to use all of our MSL simulations as the basis for where we start on 2020.
Now, I know, Steve, with game changing, you take technologies and you take them from a technology readiness level. We always talked about that 1 through that 9 scale.
Yeah.
And you're in that middle range.
Middle range, about 3 to 5 or 6.
Right. So, but with Medley, since you have proven you have a fight underneath you, and then you're working on Medley 2, is that still considered,
Yes.
technology at that level?
Yeah,
It's still not space ready.
Yeah, and it was like what Michelle was telling you was we learned so much through Medley 1 that we want to put different kinds of transducers to get the lower pressure range. We want to understand the back shell pressures and radiation rates. So we learned so much, so it's not really just a repeat of Medley 1.
Yeah, we have totally new sensors. Knowing what we know from Medley 1, we've moved a lot of our sensors, so we have kind of the same number of channels of data, but we've distributed them differently on the forebody and then moved some to the back of the vehicle.
Well, speaking of a new mission, we also have now, instead of Medley 2, we also have HIAD 2.
Yep.
Absolutely.
Which is a hypersonic aerodynamic inflatable decelerator.
Inflatable aerodynamic, yes.
We did it again. It's a hypersonic inflatable aerodynamic decelerator.
Yes.
Bravo.
Very cool.
Bravo.
All right, so that's a completely different type of EDL system from Medley 2.
It is.
And Franklin had a chance to sit down with the project manager, Joe Del Corso.
Yes.
And we're going to learn more about HIAD 2, so let's check that out.
So Joe, we're talking about HIAD 2. Tell me what has changed since HIAD 1.
So we've had a number of changes. The first one was we upgraded our thermal protection system. In HIAD 1, we used a Generation 1 thermal protection system, which was somewhat capable. It's low temperature capable, basically something on the order of 1,000 to 1,100 degrees Celsius on the surface. For HIAD 2, what we've looked at is much higher temperature capable materials, much more flexible and lighter weight. So now we're using custom built silicon carbide materials as an outer fabric. We're using COTS materials and some custom materials for our insulator systems. And then on the backside for the gas barrier, you have woven fabric systems with PTFE film wrapped around it. Our inflatable structure is also being upgraded. And then the other thing that we're doing is we are working on scalability. We're focusing on trying to get to a 12-meter scale. In order to do that, we've got to upgrade a lot of our equipment. We've got to work on something as simple as just picking up one of the gore seams. It takes a lot of development, a lot of careful coordination. So what we're focused on is not just upgrading our materials, but also upgrading our handling techniques, our manufacturing techniques.
Tell me about the HIAD timeline from the time it was conceived to where we are right now with HIAD 2.
So HIAD has been in development, previously it wasn't known as HIAD, but it's been in development now for almost a decade, and we still have probably another 4 years worth of work to do to get us to human access to Mars. We started out in 2006 doing material testing, and really all we were doing is we were doing low-level, trying to learn how to test fabric systems so that we could simulate an atmospheric entry condition. We were learning how to learn in the early phases. We had IRVI-1 happen. Unfortunately, there was a launch vehicle anomaly, so we lost that. But what it did do is enabled us to put in place IRVI-2 flight tests. People had enough confidence in what we were doing that they allowed us to build a build-to-print. That went up on a sounding rocket, launched out of Wallops, and it was an incredibly successful proof of concept. We had an inflatable structure, but no real TPS at the time, thermal protection system. Following the success of IRVI-2, we started up what we currently know as HIAD, which is the Hypersonic Inflatable Aerodynamic Decelerator project. During that project, we were doing all the lab scale development, small scale, little samples. We had learned how to do the initial testing. Now we were taking it through a maturation process, getting it ready for flight again. The third flight that we flew out of Wallops again is called IRVI-3. That was a much higher heating condition, and it was the first chance for us to actually test a thermal protection system with our inflatable structure.
After the success of Irby-3 and the closure of the initial HIAD, we attempted to fly an orbital entry flight test called Thor, the Terrestrial HIAD Orbital Reentry Flight Test. Unfortunately, due to the ORB-3 failure, we had to cancel Thor and we went back to a ground development effort. But unlike the first two ground development efforts, the third one wasn't focused on learning how to test or testing materials or developing materials. It's focused on scaling. So we did small scale in the early development phases, and now we're scaling to something more applicable for human access to Mars.
Now, the cool thing I understand about HIAD 2, that you guys have a partnership with ULA.
Yeah.
Let's talk about that.
So about a year ago, ULA announced that they wanted to use HIAD technology to recover their boosters as part of their new business model, affordability. And so we've been working on a flight demonstration with them over the last year and a half.
Yeah, and that would be at the 6-meter scale, which is about halfway to what ULA would need for their full booster recovery, 12 meters that Joe talked about on the video. And it's also the right scale for us to do maybe a technology demonstration mission leading up to putting humans on Mars.
So the idea is that you're using this HIAD technology to recover the first stage of a ULA rocket. And so is that going to be recoverable, and is that going to sort of land in the ocean? Is it going to land on dry land? How is that going to work?
They actually want to snatch it out of midair with a helicopter and to minimize any refurbishment costs.
Wait a minute, so you're going to have this booster coming down with the HIAD deployable shell.
Yes.
And then a helicopter's going to come and just kind of grab it
mid-air retrieval. Yeah, it'll come in. It'll have a catch hook, and the helicopter will come. It's a modified helicopter, obviously, but that's the plan.
Yeah, we've not air snatched anything of that mass yet, so that's a little bit of technology development as well.
Wow, I seriously hope that you go back to your ESM folks and do some modeling of that snatching, because I
reconstruction of the booster trajectory.
Reconstruction. So the reconstruction will be a part of that too.
Absolutely.
That's perfect. Well, we're looking forward to seeing that in action, because that will be something to see when that actually happens.
That would be awesome.
And also with HIAD, which is a win-win not only for ULA but for NASA. NASA gets a demonstration out of it, but then it kind of matures that technology to move on to an eventual test on Mars.
Yes.
Awesome. I tell you what, we've come to the close of just part one of EDL. I mean, we've covered a lot of technology today, and on the next show, we're going to be covering even more technologies.
Yeah, we should be talking about Adept and 3D Mat and heat.
And now, with regards to 3D mat and heat, that's more of the material side as opposed to the big system side, isn't it?
Right.
I'm looking forward to that, and so stay tuned. We're going to be talking more about EDL. You're watching NASA Edge.
Wherever, however, whenever. We're here, there. We're everywhere. NASA Space Communications and Navigation. Exploration enabled.
The reason that you would do any kind of experiment in space is if there's something particular about the space environment, and most often that is microgravity. So mostly the ISS gives us the ability to either do something that we can't do in a facility on Earth, or investigate some phenomenon, some property in a way that we can't on Earth. So for example, some of the tissue architecture, these really delicate tissues, as you start to build them up, they would collapse because you have gravity, or the cells would naturally settle to the bottom of the plate. And so you just can't study the answer to the question that you're looking for. So the space station lets us have that ability to either test what the effect of gravity is, or remove that problem entirely from our experimental setup. Yeah, the space station's an incredible place to conduct research. It was sort of like being in the world's most amazing lab when I was up there in 2016. So when you're a scientist, you're used to working on one thing over and over and maybe really refining the details on that over the course of a PhD thesis or a lab project. On space station, you get somebody's incredibly refined project times 200 different fields. So for me, it was a chance to learn about all of these different areas of science, and they each have a team behind them. So I was usually pretty excited to open the container and do whatever experiment that day brought. I also really got a chance to talk to those PIs, the principal investigators, and those scientific teams, and understand everything that was going on behind their experiments and read their papers. So by the time I got to doing the experiment, I was pretty excited to take it out and to see what was going to change in microgravity. Yeah, science in space, it's an amazing lab and it's incredibly fun. So we are smiling all the time. I'm Kate Rubens. I'm a scientist and an astronaut.
It's a new era of pioneers, star sailors, thinkers, and adventurers.
3, 2, 1, 0. All engine running.
Let's go.
We have been given the scientific knowledge, the technical ability, and the material to pursue the exploration of the universe.
And as we leave the moon, we leave as we came, and God willing, as we shall return.
You probably dreamed of this.
Liftoff on Apollo 11.
You probably replayed this moment 1,000 times. You probably imagined the awe-inspiring, indescribable rush of the ride. You probably celebrated the miraculous, cheered the momentous, and mourned the shocking. You probably still dream of what could be. We did. We do. And while many thought we were through, no. We've been learning, we've been building, we've been training. And now, it's time. Because the next frontier is not just for the next generation. It's for this generation. It's for me, and it's for you. For everything we still dream about. We go as Artemis.
The complexity, the systems that we've brought together in this one place to do something that very few places in the world do, launch humans to low Earth orbit, and hopefully with the new program into farther reaches of space. So when you go to a system or a place like that, you can't help but be overwhelmed.
Every space shuttle mission began with a fiery liftoff from Launch Complex 39 at NASA's Kennedy Space Center. The launch complex for the space shuttle had two pads, Pad A and Pad B. If the launch pads demonstrated anything, it's that complex is the right word for the two pad areas that handled the shuttles for about a month before they made their trips into space. Outfitted with everything a spacecraft and its crew would need to take the final leap into space, the pads handled fueling duties and crew support and held precision machinery for a range of payloads. Its graded floors and gray paint, along with armored boxes for instruments, telephones, and elevators, revealed a style more Spartan than space age.
You always find something that you didn't know. You've got so many systems. You've got system level experts and technicians that have been out there for so many years, dedicated, essentially, many of them, their entire careers out there. Even though, yeah, it's a lot of steel, a lot of wires and lights and tubing and that kind of stuff, it does it interfaces to a flight vehicle, so you have those complex interfaces, and there's always something to learn. It may look kind of Spartan, but yeah, it's got its hidden treasures.
The launch pad and all its fittings were built to withstand the brute force of a launch, which would rattle the pad with intense fire, corrosive exhaust, and thunderous sound waves.
Tested, let's put it that way. There's a tremendous amount of force that gets placed, and liftoff on the structure, on the mobile launch platform, the MLP, heat, acoustics.
Each pad featured a shallow slope concrete pyramid about 40 feet high with a flame trench carved through the middle to channel exhaust away during launch. The launch pads were first built for the Saturn V rockets of the Apollo program. Back then, the launch complex did not have any permanent service towers because the support structure was on a mobile launch platform and traveled with the rocket to the pad.
It's an element of the history, to think back and to stand in places where people were launched to the moon. That has a real place for me.
For a shuttle, a pair of support structures called a fixed service structure, or FSS, and a rotating service structure, or RSS, were built at the pad and would remain there for all 30 years of flights. Both structures carried wiring and other infrastructure needed to support and protect the space shuttle for weeks at a time. A shuttle stack, meaning an orbiter attached to an external fuel tank and a pair of solid rocket boosters, would move to the launch pad about a month before liftoff. The shuttle was connected to networks of data cables, water lines, and the fueling system.
Unless you were out there when the workers and technicians and engineers were out there, it's hard to capture the elements of these people working together as a team, doing complex tasks, complex jobs, with a vehicle there that's just loaded with solid propellant. It could be dangerous as heck, it really is. And they did it routinely and made it safe.
There's also a bathroom, complete with stainless steel fixtures instead of brittle porcelain.
And when we do give give some tours up there, or groups come up there, I always point out that that's the last toilet on Earth.
Before launch day, the RSS covered most of the shuttle and provided a clean room that safely moved space probes, space station modules, and even NASA's Hubble Space Telescope into the shuttle's cargo bay without contaminating them. Other parts of the launch pad gave workers access to most areas of the shuttle stack, which stood up to 184 feet above the surface of the mobile launcher platform. The launch pad was woven throughout with propellant lines, wiring, and machinery.
There's so many complex things out there that could literally kill you, if you did something wrong, or not just yourself, it could be, devastating. And we do it safely, routinely, day in and day out. That's testament to the workforce and to what this nation built from the Apollo era, learning through hard lessons.
Launch day was also when most of the structures at the pad came to life, mostly by remote control, to keep people a safe distance away. The huge white spheres on either side of the shuttle would pump supercold liquid hydrogen and liquid oxygen into the shuttle's external tank. Each propellant had to flow through long lines from the spheres about a half-mile from the shuttle.
As you get closer to launch, things just kind of step up, and you can feel it. Just pure excitement, really, as you're getting closer.
The last people at the pad on launch day were the astronauts. They headed into the White Room, a kind of cramped locker room, before boarding the shuttle. With 2.5 minutes to go, the gaseous oxygen vent arm and its white beanie cap retracted from the top of the external tank, clearing the way for the launch. About 16 seconds before launch, some 300,000 gallons of water poured onto the launch pad. Though it might seem to be done to protect against the blazing fire, the water was actually for sound suppression to dampen the vibrations produced by 7 million pounds of thrust. The fire and thunder would produce a show unlike any other.
Go for main engine start. We have main engine start. 2, 1. Booster ignition and the final liftoff of Discovery. A tribute to the dedication, hard work, and pride of America's space shuttle team. The shuttle has cleared the tower.
Some of our team would work late shifts, so you kind of had to go home and sometimes, watch it from the river, just like the other folks would, or something like that, which I actually kind of enjoy. If I couldn't make it into center in time, just kind of being out there with the general public and everything like that. Just sit back and watch the kids and people enjoy a beautiful launch. It's part of my joy, I guess.
Now that the space shuttle is retired, the pads are being prepared for another transition. The structures that marked the space shuttle era have been removed from Launch Pad 39B, so it can handle several different types of launchers that are expected to make up the next generation of space exploration. Pad 39A, the starting point for some of NASA's most famous flights, including Apollo 11 and the first and last shuttle flights, will look as it did during the shuttle years for the near term, echoing the thundering success of the space shuttle program.
Go for main engine start. We have main engine start. 2, 1. Booster ignition and the final liftoff of Discovery.
2 solid rocket motors. That's a pretty rough ride, but you can feel the thrust tail off right before they separate. And you get an indication PC less than 50, and then you're going to be there 2 minutes 5 seconds or so. They separate away. There's a huge flash in the front window, a big bang. You can hear the set motors push those away, and then it's just as smooth as can be on those main engines. They're phenomenal pieces of machinery.
The Space Shuttle main engines have been one of the brightest success stories of the Space Shuttle's 30-year career. Powered by a combination of fuel and oxygen, a single SSME, as the engines are called, produces about 500,000 pounds of thrust. Working with the 2 solid rocket boosters for the first 2 minutes of launch, 3 main engines push a shuttle up to Mach 25 and into orbit in 8.5 minutes.
We call the SSME an extreme machine, and it's extreme because on the inlets you got liquid oxygen and liquid hydrogen, and liquid hydrogen's minus 420 degrees Fahrenheit, so it's extremely cold propellant that we're putting through the turbo machinery, and then we're burning it in the main combustion chamber at 6,000 degrees Fahrenheit, so that's hot enough to melt iron.
It can do that without melting because the engine pumps the cryogenic hydrogen through a series of 1,040 tubes lining the nozzle. The supercold fuel keeps the flames from touching the sides of the nozzle. There also are a pair of turbopumps that move the propellants through the machinery and into the combustion chamber quickly. The turbopumps alone produce more power than a locomotive, even though they would fit on a desk. Providing that amount of power safely calls for extensive testing and inspections of each engine and their turbopumps. A main engine gets examined from the time the shuttle lands until liftoff. Highly trained technicians use long, flexible lenses called borescopes to look at each engine's insides for cracks and other defects.
A skilled technician engineer can perform a real good borescope inspection of bearings, seals, and actually the turbine blades, nozzle vanes, pump blades, and diffusers.
The engine's success did not come easy. Engineers began testing engine designs in 1975 at NASA's Stennis Space Center in Mississippi. Just getting the startup sequence right took months and months of complex work.
Well, of course, the first test of the Space Shuttle main engine on A1 test stand was like 20 milliseconds. I mean, it took a long time to develop the start sequence of the engine, and it was 20 milliseconds at the time, finally 40. They worked their way up to 1.5 seconds, which is a critical time period in the thrust buildup of the start sequence, and then it just went on from there, and it took a long time to actually finally get to main stage.
The shuttle's main engines made their first flight test on April 12, 1981, along with the rest of the Space Shuttle system. Although the engines had been fired on test stands, no crew flew with them until Commander John Young and pilot Bob Crippen rode them into orbit on STS-1.
And when that whole vehicle got together, we put the crew in and we counted down, and we saw engine ignition and all 3 engines come up. It was just an extremely rewarding experience to see that and see the SRBs fire and that whole orbiter take off and fly. It was hard to describe because of all of the activities that I know led up to that and all the people involved in it to see that as a successful mission, because we didn't have an opportunity to fly it unmanned before we flew it manned. So that's the first time this country really did an experiment with people on board, and it all worked.
Though the shuttle engines are smaller than the mammoth F-1s that powered the Saturn V's first stage, they had to be far more efficient.
And then this is the first time we had to design an engine that would operate for 8.5 minutes. In the Apollo program, the first stage engines operate for about 200 seconds, and it basically gets you up to about 50,000 feet or higher through the heavy atmosphere, and then the first stage is spent and then the second stage takes over. In this case, the SSME was designed to start on the ground, have the ability to health check it before the solid rocket motors ignited, and then commit the launch, and then stay running all the way through orbital injection velocity. So that made it run for 8.5 minutes. So that was different than engines we had built previously.
Along with the brawn of hundreds of thousands of pounds of thrust, the engines carry very delicate brains that take constant measurements of the systems dozens of times every second.
This is the first engine we built that had an active onboard digital computer. And the computer has a program in it that runs through its full cycle in 20 milliseconds. So 50 times a second, it's out reading valve positions, sensor data, and we have algorithms in there that allow that engine to have what we'll call health monitoring. So we have active flight red lines that in the event that temperature should exceed the limit, that engine will automatically shut itself down to prevent a catastrophic failure.
No mission ever failed because of a Space Shuttle main engine, but a couple saw close calls during launch. In 1985, one of the engines on Space Shuttle Challenger picked up a problem.
So they actually shut that engine down at about 18,000 feet per second, let the other 2 engines run the vehicle until it reached the actual velocity required to make orbit. So it was a successful mission, and it just showed that the redundancy built into the engines really paid off.
The Space Shuttle's main engines also had a requirement no other engine faced before. They had to be reusable.
Reusability created issues with hardware embrittlement. It was hydrogen molecules embedding themselves in the material, causing embrittlement later on. So that created life cycle issues, and we were always talking about what's the remaining life in the hardware.
The SSMEs produce nothing but steam when they fire, another departure from previous rocket engines.
Oxygen, hydrogen, when it combines and creates water, it's very clean. A lot different from the Apollo days when you had liquid oxygen and kerosene. Well, this engine's extremely clean. And people are amazed when they look at the engines in the shop that have flown 10 times or more. They look brand new.
The shuttle main engines have proven to be extremely reliable machines with a record of reusability and success without parallel in rocketry.
But SSME is in a class all by itself. And of course, the reliability that we get out of the SSME is the reliability and the performance that allows the shuttle to fly.
As far as the extreme temperatures, the pressures they operate, the fact that they have been reusable and so reliable from STS-1 to STS-135, I still rate the main engines at the top.
For two of NASA's Story space shuttle orbiters, the lights have gone out for the last time. Discovery and Atlantis were permanently powered down in December 2011 as teams at NASA's Kennedy Space Center in Florida prepare the vehicles for public display. It was an emotional milestone for the technicians, test conductors, and system engineers who have spent years, even decades, preparing each spacecraft for its next flight. The final assignment for Discovery's processing team on December 16, 2011 was to close the 60-foot-long payload bay doors. Many gathered for one last look inside the shuttle's payload bay.
Even at the Smithsonian, there's no plans to open those payload bay doors on Discovery, so as far as we know right now, those doors will never open again.
Then it was time for the spacecraft operators on Discovery's flight deck to shut down the power.
Okay, PRT 1 off now, PRT 2 off now, PRT 3 off now.
Actually, our center director, Bob Cabana, was there, so he actually pulled the plug on that power-up sign, and that was it for Discovery.
December 22nd was the last day that work on Atlantis would require power. Its starboard robotic arm and Ku-band antenna were stowed inside the payload bay for the vehicle's upcoming move into temporary storage.
So we were anxious to get as much work done on Atlantis and get to a point where we could then continue to do work on Atlantis in the vehicle assembly building while she was staged there in a waiting mode.
Then the focus turned to the flight deck as Atlantis, known by the shuttle team as OV-104, was powered down for the last time.
AC bus sensor 1 off now. AC bus sensor 2 off now. OV-104 final power down is complete.
Discovery and Atlantis have gone dark, but the team has one more power down to get through. Shuttle Endeavour will be next.
It's sad, but you know, progress, you have to move on. So something has to be done, and I'm extremely proud to be a part of it till the end. Extremely.
Throughout the Space Shuttle program, a familiar launch day sight was the shiny silver vehicle known as the Astrovan. Before each launch, astronauts smiled and waved as they left the crew quarters and boarded the van that would carry them to meet their fully fueled ride to space. The vehicle would wind its way across NASA's Kennedy Space Center in Florida as it carried the crew to the launch pad. It was an exciting ride for the crew members, but especially for the rookies ready for their first trip to space.
The first time, it's just everything about it. It's just, you know, the anticipation, excitement, you know, you're a little bit nervous, but it's, I mean, it's just neat to know that, you know, you're one in the series of a very long line of astronauts that rode in this vehicle going to the pad, you know, for a flight to space, so it's pretty cool.
Early shuttle crews had fewer astronauts, so they rode to the launch pad in an Apollo-era transport van. But since 1984, each shuttle crew traveled those 9 miles aboard the current vehicle. The modified Airstream motorhome only racked up about 27,000 miles in its 27 years of service. That's because it's used solely to transport the astronauts for each mission.
But I always associate this vehicle with flying, because you only get in here twice. You get in here for TCDT, which of course is the launch rehearsal, and then launch day.
The only other time the Astrovan was used was to take the astronaut back to crew quarters after landing. The vehicle's appeal is rooted in its tradition rather than its decor.
It's not really extravagant, kind of like bench seating, and it's pretty crowded on launch day, especially with a crew of 7. You know, I think everyone's trying to cut the tension with a joke or two from time to time.
The interior's narrow center aisle is paralleled by long benches. Lift-out sections accommodate the ventilator units used to circulate cool air through the astronauts' bulky orange launch and entry suits.
This is the only place they have liquid air, and liquid air is really good. You know, we have this this cooling garment that circulates water cooling, and in the hot Florida sun, it's nice to have it. They plug that liquid air into you, and it just blows this cool air throughout your suit, which is really nice because it actually dries your suit. And the only place we get to have it is in here. And I don't know why. It was like a special treat on launch day.
Now, while each crew no doubt had their own unique take on their ride to the launch pad, Shuttle Atlantis STS-135 mission crew took in the significance of the final ride for the Space Shuttle program.
It was really special this time because there were so many people here. And I think even though it's kind of an anxious time as you head out to the launch pad because you know this might actually be the day, on this particular day, you know, the last flight, I think we were all really amazed at how many people showed up. I mean, even on the road, you hang the right turn to go to the pad, and the road was lined with people waving American flags. It made me feel good, you know, to know that the shuttle program meant this much to so many people, and not just national, but international. I mean, a lot of people turned out to watch the grand finale, if you would.
While the vehicle won't be taking any more shuttle crews to the launch pad, NASA plans to keep it ready to ferry future astronaut crews to the pad.
I would like to keep this tradition. You know, I don't know if any of us will get to fly on the next vehicle, whatever that vehicle may be, a U.S. vehicle, but it would be kind of neat to have some of it be the same.
You know, and actually traditions are important in a business like this. It keeps everybody connected.
Everybody ready?
Let it happen, Captain.
Hold on, everybody.
So after riding the Astrovan to the launch pad a number of times, what would it be like if a Space Shuttle commander got the keys to take it for a spin? STS-135 Commander Chris Ferguson found out.
There's 0 to 35 in a minute and a half. That was the most white-knuckled event I've had. I pronounce this vehicle fit for another space program.
Orion is getting ready to launch. My name is Kelly Smith, and I work on navigation and guidance for Orion. Orion is NASA's next-generation spacecraft. Built with versatility in mind, it can take astronauts deeper into space than we've ever gone before, to an asteroid or even onto Mars. For these missions, Orion has to be one tough spacecraft, withstanding high speeds, searing temperatures, and extreme radiation. Before we can send astronauts into space on Orion, we have to test all of its systems. And there's only one way to know if we got it right: fly it in space. For Orion's first flight, no astronauts will be aboard. The spacecraft is loaded with sensors to record and measure all aspects of the flight in every detail. It all begins with launch aboard a Delta IV Heavy rocket. As it punches into Earth orbit, Orion will jettison its launch abort system. The abort system is a safety feature designed to pull Orion and its crew out of danger if there were a problem with the rocket during ascent. Orion's journey is just beginning. As the spacecraft and the upper stage begin their first lap around Earth, Mission Control in Houston is monitoring the progress of the flight. Orion's over 100 miles up and going about 17,000 miles per hour. Just as it passes over the Indian Ocean, we lose communication. This is expected. The communications link we have through satellites to Orion is momentarily lost, but Orion continues to receive and process data. Its computers can handle 480 million instructions per second. Imagine you are traveling with Orion as the flight test continues. One orbit completed. Time to go. The upper stage of the rocket fires again. Like the setup for a roller coaster ride, this is the big climb we've been waiting for. We are headed 3,600 miles above Earth, 15 times higher from the planet than the International Space Station. As we get further away from Earth, we'll pass through the Van Allen belts, an area of dangerous radiation. Radiation like this could harm the guidance systems, onboard computers, or other electronics on Orion. Naturally, we have to pass through this danger zone twice, once up and once back. But Orion has protection. Shielding will be put to the test as the vehicle cuts through the waves of radiation. Sensors aboard will record radiation levels for scientists to study. We must solve these challenges before we send people through this region of space. For this flight, it's time to head home. The upper stage of the rocket triggers separation. Orion's jets fire to turn it into the proper position to re-enter Earth's atmosphere. No matter what happens now, we're coming in. 75 miles above Earth, the spacecraft enters the atmosphere. Things happen quickly. We're now traveling more than 20,000 miles per hour. Air particles pushed out of the way heat up. An envelope of hot plasma surrounds the vehicle as it plummets towards Earth. The plasma reaches temperatures of 4,000 degrees Fahrenheit, almost twice as hot as molten lava. This may be the most dangerous part of the flight. Mission Control is monitoring all the data from the spacecraft, and then we lose communication again. No data can penetrate the plasma. Orion is on its own. Orion is inside a fireball. Onboard systems ignite jets to keep the ship pointed correctly, so the specially constructed heat shield takes the full brunt of the inferno. This is the largest heat shield of its kind ever made. Orion's computers command the spacecraft to bank like an airplane, keeping a precise path to the landing site. Even though we've slowed from 20,000 miles per hour to about 300 miles per hour, we're still traveling amazingly fast. We must slow down to safely land in the ocean. Luckily, we have parachutes. Specially designed for Orion, the parachutes help us hit the brakes, but not too quickly. One day people will be aboard, so deceleration must happen in stages to keep things comfortable for the crew. The forward bay cover jettisons. Two drogue chutes deploy and slow the returning spacecraft down to 175 miles per hour. Then, the three main parachutes open. Once fully engaged, this canopy would cover an American football field. It takes parachutes this size and strength to slow our descent to 20 miles per hour, and then splashdown. For this first flight, we won't have astronauts inside, but we still have some very precious cargo. The flight data from this mission is stored inside the Orion spacecraft. While our flight might be over, there is still a lot of work to do. Onboard sensors recorded every detail, from launch to flying in space, to re-entry to landing. Flight tests are difficult and complex, but they give us confidence that the systems we have designed work under real flight conditions. It's great to be a part of this first space flight for Orion, and we're looking forward to beginning a new chapter in human space exploration.
We're excited to feature the Honey, I Shrunk the Payload Challenge on our show. The challenge was made possible by the NASA Tournament Lab, which facilitates the use of crowdsourcing to tackle NASA challenges. The challenge is funded by the Game Changing Development Program in support of NASA's Lunar Surface Innovation Initiative, which champions technologies needed to live and work on the moon. Judging for this competition included representatives from the Space Technology and Science Mission Directorates, as well as engineers from NASA's Jet Propulsion Laboratory. The instrument payloads developed under this challenge could enhance future science missions on small platforms like rovers, helicopters, and CubeSats. Data from these types of crowdsourced miniaturized sensors could enable future robotic missions to protect and improve life on Earth and in space, and to discover the secrets of the universe. Finally, the Center of Excellence for Collaborative Innovation managed the contract with HeroX for the competition and awards under the Prizes, Challenges, and Crowdsourcing program at NASA. Clearly, a lot of effort went into this incredible challenge. And now, on with the show.
Welcome to NASA Edge, an inside and outside look at all things NASA.
Hey guys, today we're going to do things a little bit differently on set.
I know, the set looks great. I look great. This is great.
Today we're talking about miniaturized payloads, about HeroX's Honey, I Shrunk the Payload Challenge, where teams are shrinking down flight hardware to fit on small robots that NASA is sending back to the moon.
You know, Blair, I really love this idea, and I'm guessing you're going to tell us about a mission to do just that? Yeah, and I'm guessing it's going to be a super cool idea, Chris, just like all of Blair's ideas.
That's right, Franklin, but to help our audience understand exactly what I'm talking about, I had a chance to sit down with NASA Langley's Mark Thornblum to tell us all about the Honey, I Shrunk the Payload Challenge.
Sweet. Hey, let's check it out.
Mark, you work with Game Changing, and not only is that a really cool name, tell us what it is and how you develop these cool technologies for NASA.
Sure. Well, Game Changing is the Game Changing Development Program Office based out of NASA's Space Technology Mission Directorate. And we have about over 100 projects that are at what we would call the mid-technology readiness level. So they're great ideas and great new concepts for how we would have either a new technology or advance a current state-of-the-art that has a future in making and enabling our future missions for NASA, either for NASA science or for NASA exploration. And a lot of our projects right now have a future on lunar exploration and a sustainable presence of humans on the lunar surface.
And that's with Artemis, right?
Right. Most of our projects right now, or at least a good bit of them, are working on what we'd call a technology demonstration in order to prove themselves to be ready to be infused into an Artemis-like mission. So what we do is we start where the projects are now. They're better than just a good idea at this point. They've been shown that they're feasible and that they've shown that they really have a promise to work. So we work with these projects around the country to get them ready, get them packaged, form, function, and then demonstrated either on the lunar surface or on a ground demonstration or maybe a suborbital flight. If they're successful, then our goal is to put them onto a mission and to infuse them, or to infuse them into the commercial market and let these technologies become commercial products that the whole space economy can utilize.
You now have competitions where you're inviting people to participate in this process. Tell me about these competitions that Game Changing's working
Right.
with.
Well, let me specifically talk about Honey, I Shrunk the Payload, because that's where we want to kind of talk about today. With Honey, I Shrunk the Payload, we are engaging the public. So in this particular competition, we were interested in small instruments. Our platforms for space flight have gotten smaller. The rovers are getting smaller. Even the lunar landers that are developing now for the commercial lunar payload services, those are a little bit smaller in scale than what you might be kind of used to for, like, I'd say, a human landing system or something like that. So with these smaller platforms, you need smaller instruments to put on them just because of their capabilities. And so with Honey, I Shrunk the Payload, we have asked the public to generate ideas, submit their ideas, and really see what they've got and see what's out there. So we get a lot of benefit out of that. We get to see what small instruments are out there, which ones would be useful to advance science and exploration on the lunar surface. And then hopefully we get to actually fly them.
Was there any specific guidance that you gave the participants as they worked at this competition?
Absolutely. So we knew that we wanted to engage the public with this, and we knew that we were going to have to help them. So we worked with our partners at JPL, and we came up with what we would call an interface document. We gave all the participants constraints and parameters for how they needed to design their payload. So first, it has to be a certain size.
Small.
So think bar of soap. So 100 millimeters by 100 millimeters by 50 millimeters. That's the package that you have to fit inside. You have to weigh less than 400 grams. And then on average, you can only consume about 4 watts of power on average. And that's kind of the parameters that we gave them. And then the last thing was your instrument has to do something useful and interesting on the lunar surface. And it has to also be applicable to the types of challenges that NASA is facing for Artemis and for sustained presence on the lunar surface.
And it makes perfect sense, because if you are sending smaller spacecraft, then you will need these smaller instruments.
Right.
And so how do you know when you've been successful at game changing? When do you know that you've actually achieved your goal in delivering this technology?
So in the world of technology development, we have a numerical scale, which we call appropriately the technology readiness level. And it's a scale from 1 to 9, 1 being basically a really good idea on the back of a napkin. Okay, that's, hey, here's a great idea.
Where all minds stop.
Yeah, right. And a lot of good ideas end. But then all the way to TRL 9, or technology readiness level 9, which means used regularly for a particular mission, available to purchase on the commercial market, and is readily accepted as this is a space flight, instrument, if we're talking TRLs for space flight. And so all of our projects are in that kind of 4 to 6 range, and it can go a little below, it can go a little above, just depending. Typically, our projects end with some type of demonstration, and that can be on the ground, in a lab, that can be on a suborbital rocket flight, it could be on a sounding rocket, it could be on a full LEO mission, it could be on the space station, and in this case, for unanswered payload, we're hoping that this will be on the lunar surface demonstrated. So when those demonstrations are done, that typically gives us confidence that from a technology standpoint, that particular technology has the fit, form, and function to be useful and survive in that environment that we're going to put it in. So at that point, we would then look for infusion opportunities. We look for a mission to adopt that technology to use, or we look for a commercial partner to go and develop it further and then commercialize it.
Man, that was probably the best interview we have ever done, Blair. Spot on.
Yeah, very informative. But now I want to know more about Honey, I Shrunk.
Uh-oh.
What is it? What are you doing?
I just finished shooting the first segment of our show with these way cool miniaturized versions of ourselves. I mean, look at the accuracy. I mean, I'm depicted perfectly. And you can see the detail. It's so profound.
Now, how did you do all this without using our voices?
Oh, trust me, I got that all worked out.
I don't like the way that you're handling me, Blair.
It's fine.
I don't think you should be doing this with toys.
Oh, no, it's acceptable.
Hey, I look pretty good.
Well, I guess I look pretty good as well. Where are we at, Chris?
You're watching NASA Edge.
And inside and outside?
Man, we don't need to do that. I've already done that. I did the first segment. It's already done.
You already interviewed Mark?
Oh, yeah, it was great. He's great.
So what action figure did you use for him?
Actually didn't use action figures, did the actual Mark.
Oh, he was 1-to-1?
Yeah, 1-to-1. Yeah, scale lingo. Yeah, absolutely.
Now, what kind of scale are we talking about? Are we talking about CubeSat small, or are we talking about Saturday morning cartoon shrink ray small?
It's a good point, Franklin, because I love the shrink ray idea, and that's what I thought it would be. But it turns out that they're looking about wallet size, which is kind of CubeSat size, but they're using real science and engineering to bring that technology into this new form factor for the challenge itself.
Chris Small.
Yeah, there you go, right? So I had a chance to talk to the teams about their particular payloads and how they actually managed to get it down to size. Let's check it out. Joining us now are 3 representatives for the finalists competing in the Honey, I Shrunk the Payload Challenge. Those teams are Sun Slicer, Water Snooper, and URAD. Let's talk about URAD first. Christian, can you tell us about your payload, URAD?
Sure. So URAD, or microrad, is intended to be a more compact, lower-cost radiation sensor that will enable future missions to deploy radiation monitoring equipment much more broadly than has been done in the past. So the name was inspired by the radiation assessment detector that was carried on the Curiosity rover, which was used to survey the Martian radiation environment both once the rover got to the planet, but also to assess what the radiation dose would be on the journey to Mars. So sort of following on from that basic concept of being a very generic, broadly applicable radiation sensor that can tell you a lot about different types of particles and measure the energies of those particles, we decided to name our payload MicroRad, reflecting that it has, as much as possible, similar capabilities, but in a much smaller package.
What were the challenges of taking that standard radiation detector and sort of getting it down to that very wallet-esque size payload which you accomplished?
So there were definitely a lot of challenges, both implementation difficulties. For example, the chip shortage really caused us a few issues, but also technically as far as getting the capabilities we wanted in such a small package. But thankfully, we were able to leverage some novel technologies that really only became available in the last couple of years to do that. So that was definitely a challenge. Basically, how many new technologies we were trying to leverage and cram into such a small payload, and also do it with such a small team and on such a short schedule.
Christian, what are some of the broader uses for the technology you've developed for URAD?
So URAD is very unique as far as being very low cost and small size. And it's also not specifically focused to any one type of measurement. So it's very good at characterizing sort of a general radiation environment. And that sort of lends itself to a lot of other applications beyond the immediate needs of NASA or the immediate needs of the Artemis program. Potentially, I could see applications related to national security, for example, assessing whether someone's trying to smuggle radioactive material into a port, for example. But there's also other applications in space. For example, it's small and cheap enough that you could put one on a large number of spacecraft, and then that would give you spatial diversity as far as the radiation measurement, which could be useful for understanding the structure of CMEs, perhaps, or perhaps it could be used for being able to discriminate between hostile anti-satellite action versus natural effects, as far as when radiation effects show up on a spacecraft, being able to tell, is someone pointing a particle accelerator up at the satellite, or is that the radiation that's just coming naturally from the sun, for example.
Christian, thanks so much for taking the time to explain URAD. Next, let's talk with Phil, who has SunSlicer. Phil, can you tell us about SunSlicer?
Hello, Blair. Yes, SunSlicer is a miniaturized X-ray spectrometer that's been adapted for the harsh lunar environment, as well as to ride around on a miniaturized lunar rover.
What would you use a spectrometer, X-ray spectrometer for on the lunar surface?
We've tried to keep the instrument as versatile as possible. So there's many different science experiments you can do. The big one is prospecting for the purpose of in situ resource utilization. And we can leverage the sun somewhat as a X-ray or alpha or radioactive source to illuminate the regolith, and then leveraging X-ray spectroscopy, we can see what the rock-forming elements and hopefully their relative abundances in the regolith.
I like that, a lunar prospector of sorts.
Correct. There are also a couple of other applications. For the initial phase of the competition, we came up with a cool science idea that allowed measuring active regions of the sun to very high angular accuracy compared to what you could do with orbital assets. And that experiment was all about lunar rover mounted SunSlicer pointed at craters on the moon that could shutter or block the sun's X-rays as it rose or fall behind that crater, and then get enough imaging information to map the size of those active regions. And then lastly, for free, you get radiation monitoring ability up into the high X-ray range, which is interested in to keep our astronauts safe when they return to the moon on the Artemis program.
Awesome, thanks so much, Phil, appreciate it. Let's go now to Tibor Pasher, who is actually in Budapest, and he's going to tell us about Water Snooper. Tibor, what is Water Snooper?
Hi, Blair. Greetings from Budapest. The water snooper is a very small, actually a neutron detector, which is able to look for volatiles, hydrogen and water ice on the moon surface.
How did you accomplish this task in such a small form factor for Honey, I Shrunk the Payload?
The idea is actually from our colleague David. He was thinking of how can we use industrial CMOS sensors to detect neutrons. This looks crazy, but we managed to put just really good quality industrial CMOS sensors in this very small 10 x 10 x 3.4 centimeter box actually, and it looks fine. That works everything. The challenge was actually to put also the electronics into the box, but we managed that as well.
Now, the idea would be that you would put this payload on a rover, correct?
Yeah, that's correct. Actually, so if we manage to put the snooper on a rover, then we can just go around and look specifically water if we know that the area is a potential area for water ice or hydrogen. On the other side, we can make a kind of prospecting map, looking at what is there actually, where it would be useful to dig for water ice. So the snooper is able to look about 1 meter into the regolith, and this is the upper region of the regolith where we expect to have water ice. And if we know how much is there, how much water equivalent hydrogen is there, then it might be a good chance for somebody to follow up, dig it up and make water and then hydrogen and oxygen from the water ice.
That's awesome. Tibor, thanks so much to you and your team. And I want to thank everybody who joined us today, all the participants for Honey, I Shrunk the Payload. We wish you all the best of luck and hope to see you all fly these payloads to the moon. Thanks, guys.
Thank you so much.
What really impressed me about these teams, guys, is the fact that they've taken technology and miniaturized it, basically shrunk it down for the challenge, but all the things they're looking at are all things that NASA needs to accomplish for us to develop a sustainable presence on the moon in Artemis.
That's a great point. NASA's not going to be able to do it alone. We're going to need, commercial industry, academia, other government institutions, the international community, and the general public. And this is a great way to get the general public involved and excited about the Artemis mission.
Yeah, and crowdsourcing the development of flight hardware is just brilliant. And this will be the first time that it will be done.
Not only that, but this technique will be used in other challenges to come down the road.
Yeah, and the payload interface requirements were developed by JPL, and all the teams had to submit their payloads to them for testing. My next interview had a lot to do with that. Let's check it out. I'm here with Josh Ravage, who is a mechanical engineer at the Jet Propulsion Laboratory, and he was part of a team who received the Honey, I Shrunk the payloads to test their flight worthiness. Joshua, can you tell us a little bit about the testing process?
So it's actually an interesting problem figuring out how to test these payloads, which came from very diverse places with very diverse functions, and that were going to be potentially accommodated on a mission to the moon, on a lander that wasn't yet selected, and on a host spacecraft mission that also wasn't selected. So to do this, we took kind of a twofold approach. The first, we looked at just characterizing whether they would survive during launch events. So we did random vibration testing using standard NASA specification for this. We took all 3 payloads, put them on a vibration table, shook them, see if they turned on afterwards. Everything so far so good. The other aspect was thermal vacuum testing, and that's did we think that we could survive in the lunar environment. This, we took a more custom approach. The standard NASA spec wasn't quite designed for this mission where it could be a single cycle on the lunar surface. So we took a pretty simplistic test approach of 1 cycle from minimum temperature to maximum non-operational temperature, and then 1 cycle from minimum temperature up to operational temperature, turning on every 15 or 20 degrees Celsius or so, see if these payloads are able to turn on, how they function, and inform the future if they move to a lunar mission and were accommodated. Did we think that they'd be able to survive and operate?
Now, these payloads were smaller than most payloads that would fly. Did that impact the testing at all?
These payloads were small. We actually originally set them at about half U, which is a standard CubeSat size, about half of that. So it's about 10 centimeters, 10 centimeters, 5 centimeters. That they were so small, actually, the truth be told, made testing a little bit easier. We didn't need particularly large, complex tooling to be able to accommodate them. So it actually made the testing go fairly smoothly, and it was pretty convenient.
What is the next step for these 3 payloads?
Yeah, so testing through vibration testing appears to be successful. Thermal vacuum is actually, as we speak, almost completed, and so far so good. If any of these are selected to actually fly to the moon, we'll begin the official accommodation process with our host missions. There'll be some interface. I'm sure interface hardware will be designed to manage them. They'll get delivered to those missions, and they'll get tested and certified along with those missions. And hopefully they'll get a ride in the next couple of years.
Sounds great. Josh Ravage, thanks for joining us on NASA Edge today.
Thank you so much.
It's interesting that these payloads from these teams were tested at JPL just like any other flight hardware or satellite would be for a mission. The vibration testing, the thermal vacuum, all of that. So these are legitimate flight hardware that can fly on any mission.
Yeah, that's what I love about what HeroX has done here. And in addition to a catchy title that led to a cool part of our show, as you said, Franklin, winners or just any of the teams that participated and got their hardware flight ready, they have a chance to fly to the moon. This is an incredible thing, and to have your hardware there is great. Now, I have some good news.
Okay.
There has been an announcement for a winner
for
the challenge. So all the teams did a great job. The 3 finalists were spectacular, but we do have a winner. It is Phil Jobson of Sunslicer.
The miniature X-ray spectrometer.
Yeah, with that cool dust mitigation gear mechanism.
Oh, very
really cool stuff. Yeah, they won. I sent him a message, and he sent us his thoughts on winning this challenge. Let's check it out.
Thanks for the kind words, Blair. Team Sunslicer is thrilled to rank first place in the inaugural NASA Lunar Payload Challenge, especially in the company of 2 other exceptional teams in Pooley Space and Microrad. We're excited, over the moon you might say, in the possibility that Sunslicer, created in a Santa Rosa garage, may fly and validate 18 months of extreme commitment and sacrifice. I cannot thank enough my teammates Garrett Jernigan, John Doty, Brian Silverman, Vadim Gerasimov, and the countless volunteers, partner and sponsor companies for their tireless efforts. Please check out sunslicer.com for full credits and updates. And in the words of Ralph Cramden, to the moon, Alice.
I tell you what, Phil and his team did a really good job with Sunslicer. I mean, I'm looking forward to seeing that on the lunar surface one day.
Man, I can't imagine entering a contest like this and actually winning, knowing that, as you said, your technology, your creation might one day fly to the moon.
Yeah, we talked about this before with CubeSats. Can you imagine your resume at that point? You go like, I've done X, Y, and Z, but I also have a payload that's working on the moon. That's really cool.
And in addition to Sunslicer, we can't forget about the other teams that were in the competition.
Absolutely. And so when we were talking to the teams, we were talking to Tibor in Hungary, his whole team, which wasn't just there. They had team members in CERN, they had team members all over the place. The effort that went into this, and Christian, who was up at MIT, and his team, lots of hours, lots of creativity and innovation came together. And the good news, guys, and this is really important, that whether you win the competition or not, because of that testing that they've all gone through, each one of these payloads is flight ready and has the potential to fly to the moon. Good job, HeroX. Good job, game changing in NASA. It looks like we got a winning plan for the return to the moon with Artemis.
You're watching NASA Edge.
An inside and outside look at all things NASA.
With show-ready technology.
I found a flaw in your system.
Uh-oh.
It's not the scale, Franklin.
Yeah.
You notice that?
You're like taller than everybody.
Hold on a second.
Oh,
what do you think? Something like that? Yeah, that's more like it. Yeah,
it's more like it.
Yeah.
astronaut Randy Bresnik, living and working aboard the International Space Station. Now, on the space station, we live in a microgravity environment. Do you think the laws of physics will hold up? Come on, let's go find out.
The acceleration of an object depends on the net force acting on the object and the mass of the object, or F equals ma.
Surely good show, Sir Isaac.
Here we see that once the force of the thrust is greater than the weight of the vehicle, the rocket begins to accelerate.
All right, we're going to start with something small, something you might have at home, a little stick of chapstick. We'll go ahead and use our force being our bungee cord here. We'll put it on our bungee, and we'll pull it back. And let it go. And you can see how fast it accelerates because there's very little mass. Next, we'll try a little spaceship. A little more massive, and you can feel that because as you move it, you can feel that the kind of the force, the extra force you have to push with your hand. So we'll put our spaceship on our launcher here, same spot. Notice it's flying a lot slower than that chapstick did. What we've seen is the same amount of force on a smaller, less massive object means the acceleration is faster. Well, this is the biggest and most massive thing we have, so let's see how the acceleration is affected. Pull back the same amount on the force, and here we go. And there you have it, Newton's second law of motion in action. Thanks everybody for exploring a little physics with me today. Now I'm going to send it back to Earth so you can start your experiments. See you again real soon.
It is great to be back at America's Space Coast, at this historic place with the men and women of the John F. Kennedy Space Center. And it's here today in the 21st century that the modern marvels that launched from these grounds prove that the public and private sectors are achieving far more together than we ever have apart. American businesses are developing new rockets, spaceships, satellites that are taking us further into space than ever before, and renewing our confidence that we can and will achieve the impossible once again. This truth echoes through the history of the Kennedy Space Center. Named for a president who challenged the American people to marshal the best of our, in his words, energies and skills, become the world's leading spacefaring nation. I know America will once again astonish the world with the heights we reach and the wonders we achieve. And as these feats of American enterprise and ingenuity attest, much more than the bridge to space, Kennedy Space Center is the bridge to the future.
It's a new era of pioneers, star sailors, thinkers, and adventurers.
3, 2, 1, 0. All engine running.
Let's go.
We have been given the scientific knowledge, the technical ability, and the materials to pursue the exploration of the universe.
Imagine living in a modern metropolis full of opportunities, endless sunshine, Hollywood celebrities, and fancy cars. That was the American dream. That was Los Angeles in the early 1940s. But in the morning of July 26, 1943, in the middle of World War II, the sun didn't rise over the city. A throat-burning noxious gas covered the sky. Entire city blocks faded away. A thick fog that made people's eyes sting and their noses run had taken hold of the city. They were under attack. Or so they thought at the time. But the attack didn't come from the outside. Massive wartime production facilities, a high increase in population, and the exhaust fumes of cars, combined with the geography of the valley, made the city a trap for air pollution. The day after the first event, city officials tried to control the damage by restricting emissions from power plants and industry. But while these efforts helped reduce air pollution, smog episodes continued to occur. Scientists discovered that volatile compounds, like the gases produced due to evaporation of gasoline during the refining process, and nitrogen oxides generated during the combustion inside car engines, both reacted with sunlight, creating a highly toxic gas, ozone. And sunlight isn't precisely something Southern California lacks. But this wasn't a localized phenomenon. Other U.S. cities also experienced high ozone concentration levels. These cases made society aware of the importance of keeping track of emissions and lead politicians to implement policies to improve the quality of the air we all breathe.
Air quality is a serious global problem. More than 7 million people die per year due to the effects of air quality.
There's many economies around the world that are growing, and what the United States has seen is that your economy can still grow while your air pollution levels are decreasing, but it takes some effort to do that. The good news is that air pollution levels around the world are gradually decreasing.
In fact, air quality trends have improved in the last decade as a result of policies developed to reduce air pollution.
Back in the 1950s, Los Angeles had a really awful air quality problem.
So when the Clean Air Act began, it was a commitment to cleaning up the air. But the actual legislation and the differences took a long time to put into place. And so here in Asia, we're at the beginning of that process.
These nations that are still increasing in their standard of living and increasing in their pollution levels can learn from what's happened in the industrialized nations. We can have a more rapid decrease in pollution levels.
Now we know how to put together effective policies to control air quality.
Understanding that economic growth and industrial development bring air quality problems and knowing how to deal with it in the future is vital for us to keep progressing as a society. Now we have better tools, better technology, and more knowledge. We can act faster and more efficiently to address pollution issues.
Chorus AQ is an international cooperative field campaign between NASA and the Korean National Institute for Environmental Research.
The Ministry of Environment of Korea has put in a great deal of effort into improving air quality.
By working with our Korean colleagues, we've been able to design a campaign that is very specific to their knowledge of the air quality problem from the past decades.
Joint venture with NASA has provided us with many research opportunities.
The air in our planet does not know of national borders or countries. A worldwide effort is needed so that what we do in the name of progress does not have a negative impact on our health and helps preserve the only home we know, Earth.
Chorus AQ combines satellite-type observations with ground observations and airborne observations to create the most complete picture of air quality we've ever created.
Explore with us. Take a deep breath and join us on an expedition that will investigate a major public health problem, air pollution.
One of the difficulties in understanding air quality is that the pollution that affects your health the most is not the initial component put into the atmosphere.
Under certain atmospheric conditions, some of these pollutants react with each other and produce new harmful agents like ozone.
There's three key ingredients to make ozone: NOx, hydrocarbons, and sunlight.
So think of ozone as an important cleansing agent from the atmosphere. When you have a big stain to clean, you use a lot of cleanser. And when you create a lot of pollution, a lot of ozone becomes evident in the atmosphere. That's helping to clean the atmosphere, but it's also impacting our health. We have primary pollutants. Nitrogen oxides and reactive hydrocarbons are most important in the formation of ozone.
Your car emits both NOx and hydrocarbons, sort of unburned fuel.
But the ozone itself comes from the chemistry, so we call it a secondary pollutant because it results from the chemistry that occurs after the emission of the nitrogen oxides and the reactive hydrocarbons.
When nitrogen oxides and hydrocarbons react with sunlight, they produce a harmful secondary pollutant, ozone. But wait, isn't ozone good for us? Well, it depends.
The role of ozone in the atmosphere is quite complex. In the stratosphere, ozone is a great benefit because it protects us from UV radiation. In the lower atmosphere, ozone is also a benefit because it's responsible for initiating the chemistry that cleanses the pollution out. But when pollution levels are very high, the chemistry runs amok and you create very high levels of ozone. And those ozone levels can become so high that they become reactive with our own body tissues and become a problem in terms of health.
Photochemical smog is considered to be a problem of modern industrialization. It is present in all modern cities, but it is more common in cities with sunny, warm, dry climates and a large number of motor vehicles. It can also affect rural areas, where agriculture, trees, and forest fires can release a considerable amount of volatile organic compounds, or VOCs.
What are the sources of VOCs? Well, we have just the evaporation of gasoline when you're filling your tank, petrochemical plants, the refineries that are making gasoline for us from oil, and also the plastic companies that are making plastics, polyethylene, polypropylene.
In terms of reactive nitrogen, man's activity far outpaces the natural sources, and so we can say that when nitrogen oxides are present, that's man. When you talk about reactive hydrocarbons, actually vegetation plays a major global role in creating them.
Trees can emit that pine tree smell you smell, but also a lot of the deciduous trees are emitting isoprene. Isoprene is very reactive and very good at making both particles and ozone.
But fortunately, they create very specific molecules, and when man creates pollution, it creates a different chemical mix. And so we can look at the constituents of the reactive hydrocarbons to determine whether it's nature or whether it's man.
But because these compounds travel with the wind, they can affect different parts of the world. Recently, scientists from other airborne campaigns were able to trace the origin of unusual high levels of ozone in the air above the western Pacific Ocean. They found that they were linked to the organic compounds released by forest fires in Southeast Asia and Africa, half a world away.
The atmosphere is a shared resource, and we're seeing more and more that the entire northern hemisphere is suffering from pollution background levels that are due to all of us, not just one.
Everyone living in a big city around the world is breathing polluted air, and it is having an impact.
It's part of the tug of war between progress and the price that we pay for that progress. And so that balance needs to be maintained into the future as we continue to develop economically, develop technologically. We have to pay attention to how that's impacting the air quality.
Our world is an interconnected system, and the impact of air pollution goes beyond the air we breathe.
All of the processes that are emitting and causing air pollution are also putting CO2 into the atmosphere, causing climate change, global warming.
It also affects our soils, our glaciers, our oceans, our climate.
And this is a problem that's going to affect our children and our grandchildren. So it's very selfish of us to ignore this long-term problem that is created by us.
In a laboratory setting, you can artificially control different parts of the problem, so each effect can be isolated. That's hard to find in nature.
Seoul, South Korea. A megacity with over 25 million people and a population density which is almost twice that of New York and 8 times greater than Rome. Despite being a modern and massive megacity, South Korea still counts with many forests and rural farming communities throughout the country. But why is South Korea an ideal natural laboratory to carry out air quality studies?
We have a bunch of factors. We have a very large city, a mega city, the 4th largest city on the planet, with lots of cars, lots of power plants. And then downwind from that, we have a forest. So we have the urban plume reacting with the natural emissions from the forest.
This is a perfect place on the globe to try to understand how the mixture between man's emissions and nature's emissions can create poor air quality.
Air pollution is an important environmental problem in modern societies. The rapid growth of new economies and industries in developing countries makes it very difficult to address environmental issues.
Korea has been developed very quickly after Korean War. Actually, economic success gave us lots of benefits to the people. However, this also brought many environmental issues, including air quality.
So general public has been known about the yellow dust issue before, and in recent they start to learn about the fine particle issues and ozone issues. They're starting to pay their attention to those newer issues emerging to our society.
Korean government has been making persistent effort to improving air quality. We participate in this project as though understanding of current situation with aerial, ground, ship, on the top of current simple ground observation, crucial in future improving air quality.
We are definitely pay attention to solve this issue, and general public wants to know how we can actually achieve that goal.
Developing effective strategies to balance the economic growth and the good health of the population is key to continue growing and prospering as a society.
Unfortunately, policy always lags emissions, and so it usually takes time to understand what's causing the poor air quality, and then regulations can take effect.
It's a tough problem. We haven't solved it completely in the U.S. But here, I think you're right. We're learning a lot more about the specific sources in this area so that here locally the government can decide what's the most effective strategies to use, because we don't want to hinder economic development. We just want to know what are the smartest choices you can make so you get the best bang for the buck.
In the United States and in Europe, this has taken place over a long period of time. Things in Asia are growing very rapidly, and so we're in the middle of that process.
But the difference is that now, with our knowledge and technology, we are better prepared to address these complex environmental issues.
In these days, many countries in East Asia have been developing very quickly as well. Pulse AQ mission makes people aware of the seriousness of current air pollution.
So we are thinking, based on this mission, more general understanding, getting better and better, and eventually we can find something to actually reflect to the strategy.
Chorus AQ mission results will help develop improved ways to assess this challenging task.
Current investigation will definitely help us gain deep understanding of air pollution phenomenon in global scale.
This is a lab, but maybe not the lab you would expect. Meet the NASA DC-8 Airborne Laboratory.
The airplane is designed for different instrumentation suites depending on the missions that we fly. So we have multiple zenith ports that look up, we have multiple nadir ports that look down, and of course many of the window blanks there.
There are 25 instruments on board the aircraft, not only from NASA but from many universities and other government labs and organizations. And together they paint a picture of the atmosphere that can allow us to completely evaluate what emission sources in the peninsula are contributing to poor air quality and how the chemistry actually works in terms of the outcome at the end of the day when ozone and particles are such a concern.
Yeah, this integration is about as big as we do, and if you've seen on board the airplane, you can see it's very full with all the racks and most of the windows, covered with the in situ probes that are there.
The Chorus AQ campaign will gather air quality data in and around the Korean Peninsula from multiple sources, such as ground stations and maritime sensors. However, the Chorus AQ aircraft will be the ones to provide the most detailed information over a larger geographical area and at different altitudes.
So in order to understand how it all works, we have several aircraft that we have to fly. One is the one I'm standing on right now, the NASA DC-8. The DC-8's role is to measure the atmosphere directly. From this aircraft, we can measure literally over 100 different compounds in the atmosphere.
The airplane flies as easily at 500 feet as it does at higher altitudes. That enables us to do both remote sensing, which is using radars or LiDARs, as well as we can fly lower, we can do vertical profiles with our in situ sensors, which is currently what we got mostly on this airplane.
In order to understand the atmosphere, there are many different molecules that we have to measure. The satellite will not see all of them. And so by being able to measure what the satellite will see and at the same time see all of the details, we can begin to understand what sources and what meteorologies and what combinations of conditions will affect what we see from space.
By combining detailed measurements from aircraft with those made by satellites, we can get a better picture of pollutants in our atmosphere.
So this aircraft carries instruments that work just like the satellite instruments. The higher we fly, the wider the patch of Earth we can see.
During the campaign, NASA King Air aircraft will mimic the measurements future satellites will make.
We fly at about 28,000 feet, and at that altitude we see about a 5-mile wide patch of ground. Like mowing the grass, we're just trying to cover a patch on the ground continuously and make a map of what the pollutant distribution looks like.
So we have a small King Air aircraft flying above all throughout the day, measuring the way the future satellite will measure air quality. Meanwhile, the DC-8 flies underneath, showing what the distribution of pollution is above the ground. That allows us to understand how to connect what the satellite sees with what's at ground level.
Chorus AQ has in its team 2 smaller aircraft equipped with atmospheric chemistry measuring instrumentation. A King Air from NASA Langley Research Center, and a King Air provided to the Korean National Institute for Environmental Research by Hanseo University.
The Hanseo King Air aircraft is relatively smaller than DC-8 in NASA. It can freely access source of pollution and measure air quality capital territory that cannot approach using DC-8.
Working all together, scientists from the Chorus AQ campaign will provide valuable data and test the technologies needed to better understand air quality and the flow of pollutants within our atmosphere.
We can only fly the planes for a very short period, but the details that you get from the aircraft help inform the observations from space and from the ground, and how models can interpret those observations.
From this mission, we'll have better models and better mission data for Asia, and so we'll be able to extend the usefulness of this well beyond South Korea to other developing cities around the world.
We have the tools to study our atmosphere. Now, let's go exploring.
There's one thing that stands between us and the harsh environment of space, our atmosphere, the part of Earth that sustains all life. But here, in the closest town to the North Pole, it's slowly leaking away. A team headed there to launch rockets into the leak, but it's not the lack of atmosphere that they're concerned about. The leak is a natural process that will take billions of years, so we're not going to run out anytime soon. It's part of the larger story of how a planet's atmosphere changes over time, a key factor in the search for life on other planets.
We have 35 residents and 60 of our team together in a town that is completely isolated. There's a plane twice a week, and there's 1,000 polar bears nearby.
This is Doug Rowland, a NASA scientist who's taken his team to Ny-Ålesund on the island of Svalbard. The island lies beneath one of two regions near Earth's poles called the cusps. It's where we can access space directly, and where 100 tons of atmosphere escapes into space each day. This escape gives clues to how long an atmosphere will last, and ultimately, whether it stays around long enough to sustain life.
What we're trying to understand is, how did Earth's atmosphere evolve over time? And how do other planets that might be like Earth or more dissimilar to Earth, how did their atmospheres evolve?
So Doug joined forces with Göran Moen, a professor at the University of Oslo, who started the Grand Challenge Initiative, CUSP. It's an international mission to launch 12 rockets into the Earth's northern cusp. And Doug, he's the mission leader for the first 2 rockets of the campaign.
We don't want to waste our rocket. It'll take us 3 years to make the rocket, only 15 minutes to use it, and I don't want to waste my shot here.
He's using a sounding rocket, which is different from the bigger rockets that carry satellites and humans into space. It's a small suborbital rocket that flies briefly into space, collects real-time data for around 15 minutes, then falls back to Earth. It's affordable, quick to build, and can launch towards a precise point.
The major advantage is that you can launch into a target on the sky.
But there's a limited launch window and only one chance to get the launch right.
We have these unguided rockets. They go where you point them, unless the wind is blowing, because the wind literally just blows them over. We don't launch when there's high wind.
So to measure the winds, they launch balloons with GPS trackers. They're released every 15 to 30 minutes, and then they're monitored to see how fast the winds are carrying them.
The ground winds were 12, 13 meters per second, gusting 17, which is way off.
You're filled with trepidation. Oh my gosh, this thing that I built, is it going to work after all this? So I think we're going to scrub for today. I'd like to thank everyone. I think it was a great performance. Thanks a lot.
This means that we are scrubbing this operation for today and we'll try again tomorrow.
The mission is named Visualizing Ion Outflow via Neutral Atom Sensing 2, or VISIONS 2. In short, they're looking at how oxygen is getting enough energy to escape.
It's a good test of how atmospheric escape works. Earth's gravity should hold onto the oxygen, and yet we see this gas shooting off into space. We're trying to figure out how that works.
That is a science question that has been hanging around for 4 decades.
Fortunately, anyone can see atmospheric escape at the right place and time.
In Svalbard, we have the so-called polar night. It's dark all 24 hours.
This continual darkness is key for witnessing this. This is the cusp aurora. It's a type of northern lights that appears between 8 a.m. and noon, and you can only see it when it's dark during the day. It looks similar to the aurora that occurs at night, but when these iridescent colors dance at this hour each day, 100 tons of oxygen escapes from Earth's atmosphere into space.
This is our sport now to chase the aurora.
Working with them is the iSCAT radar and Kjell Henriksen Observatory. They have additional instruments to find the aurora.
Sometimes it's cloudy, so we use radars to track the cusp. We can give advice that this is the right type of aurora.
This is the Wall of Science, a collection of data from satellites and ground instruments that helps them predict where the cusp aurora will be.
So the cusp actually isn't a fixed point in space, it kind of moves around.
What's controlling the cusp's movement is the sun interacting with Earth. Our planet is surrounded by a magnetic field that helps us hold on to our atmosphere. But at the North and South poles, the magnetic field bends inwards, creating a corridor between Earth and space.
When energy is released from the sun via a solar flare or coronal mass ejection, all of that energy in the form of radiation rides down the magnetic field lines of the Earth and is transferred and dumped into the Earth's atmosphere.
Electrons cascade into Earth's atmosphere. They accelerate and collide with oxygen particles, giving them energy to release light and sometimes enough energy to escape. Collectively, this forms the cusp aurora and streams of escaping oxygen.
This cusp is in constant motion.
And we've got a fixed trajectory. We really can't aim at where the cusp is. We have to wait for the cusp to come across our line of sight. Can you guys hear Chelmar? We'd like you, as soon as you see an indication the cusp is moving close, to move it, the radar dish if we can.
This is iSCAT. It's been very quiet, very difficult to launch.
Do you think we're gonna launch today?
No. Probably about a 60% chance of launching.
When we started seeing this really good data, this clock started counting down, and that's when everyone realized this is gonna happen. We're going to launch.
We're doing everything we can to get that launch off before the aurora goes away. It is really, really challenging and nerve-wracking at that point. You can see the tension just rise in everybody when that happens.
And so everyone's watching their instruments, getting really excited, and then at T-minus 1 minute, all of us ran out to go see the launch happen. And then we immediately turned around and ran right back in to look at all the data that was coming back from the instruments. You know how much time and effort went into it because we all worked on it, and there's just nothing that compares to that feeling.
Everybody in every one of those little places, really just so happy to contribute to getting this science. It's really an incredible experience.
This is a story about what it takes to launch science instruments into space, but the real adventure will be in the data they sent back. Hidden within the numbers will be answers that reach far beyond Earth, shedding light on how atmospheres throughout the universe change, evolve, and perhaps support life.
Flashing across California desert skies, the airplanes you see here are writing new chapters in the story of man-made flight. There she goes.
This is my first opportunity to greet you as Deputy Administrator of the National Aeronautics and Space Administration.
Together, you and I must make our new agency
the most unusual place.
An organization that can challenge conventional wisdom.
We can engineer anything we can write the requirements for.
We're going to make your idea work. This particular idea is quite disruptive.
A typical flight, of course, starts under the wing of the B-52 mothership.
This sleek, high-speed machine would have made Rube Goldberg proud.
The manner in which we fly re-entry from space on the space shuttle was pioneered on the X-15.
The X-31 pretty much wrote the book on thrust vectoring, along with its sister program, the F-18 HAR.
And the observation of an occultation is one of the more challenging missions that Sophia can do.
Right now, we are looking at the dawn of a new era of aviation.
Something has now emerged that might make even our most elegant theories workable.
Scientists developed equipment which would be able to think.
Machines that do things and make choices without human beings. That uncanny spectacle is automation.
Capable of storing, processing.
Calculations that would ordinarily take hundreds of man-hours. Unique ability to check itself on possible errors.
Cheaper and quicker and better.
Electric eyes, limit switches, servo mechanisms.
Secretary, librarian, banker, teacher, medical technician, bridge partner.
Volumes of changing data into a continuous flow of interpretations. Aladdin's lamp couldn't do more.
Jaws, loading machines, electric drills, it's all automation.
Computers have taken wing.
By the late 1960s, digital computers had become more available.
Using data about the aircraft's performance, the computers vote on the correct amount of control deflection to make in response to the pilot's stick and rudder movements.
This system could make air travel of the future smoother and safer by reducing aircraft vibration through automatic response from the computer to the aircraft controls.
We did the digital engine control. We had an early large digital computer that ran the engine and the inlet and exhaust system.
We did an integrated control study to provide digital control of the inlets, autopilot, throttle, air data, and navigation system. A digital computer here, major improvement in the capability of the airplane.
Test pilots are flying a plane without having to leave the ground. It's a new way of flight testing advanced aircraft that's both more economical and less hazardous. A research pilot in a realistically recreated cockpit on the ground, complete with flight controls, flies the remotely piloted craft using computers and television.
The airplane includes computers. Those computers take stick command and
continuously monitor what the airplane is doing and compares it to what the pilot wants the airplane to do.
The computer signals the control surfaces to not only execute the pilot's maneuver, but also to counter any attempt by the X-29 to veer out of control.
Fly up.
Yikes! No doubt about it. We didn't get a roll through on that one.
New initiative in the artificial intelligence area, and it's called aircraft automation. The technologies that end up coming out of this would be autonomous flight vehicle technology.
ERAS stands for Environmental Research Aircraft and Sensor Technology. Platforms that could fly higher and longer than the current piloted airplanes, do science missions and other commercial applications.
Primarily the dull, dirty, and dangerous.
We can go all the way up to where the airplane can fly itself completely autonomously with no input from anyone on the ground.
Fly up to 50, 60,000 feet, fly a circle loop perhaps over a city,
providing the capability that a satellite now does.
Now that we can fly for on the order of 8 to 10 to 12 hours, we can look at long duration processes, biogeochemical cycling, looking at carbon and nitrogen moving through an ecosystem.
To sort of kickstart a commercial UAV industry.
The technology that we've seen here in this test is what would be the foundation for a follow-on program to really address the issue of how can UAVs routinely operate in the National Airspace System.
The primary benefit of this technology is the ability of it to adapt to the unknown, whether it be a system failure, battle damage, icing on the wing, or flying in an unknown atmospheric environment.
The aircraft may be able to be flown, but the pilot may or may not be able to find a solution to how to fly that aircraft.
Neural net control systems where the controls are going to teach themselves and keep being smarter from flight to flight.
It can reconfigure the airplane in an optimal way in order to give you the best flying qualities.
Okay.
There is no operator of the vehicle itself on the ground. Basically, the role that the human plays is more in managing the mission, an orchestra director, not the instrument player.
The vehicle will complete all the autonomous actions necessary to release the weapon optimally positioned to hit the target.
One of the next things that we'll be demonstrating in UCAV is the collaboration amongst aircraft. How do sets of aircraft interact together in almost a social form?
We're going to examine the feasibility and technical utility of actually being able to fly two airplanes or multiple aircraft in formation with each other.
Now the trick to this is to make sure that they fly in formation close enough that they can extract the advantage without obviously running into each other.
The station keeping would be fairly close proximity for hours. The workload on the flight crew would be quite high, so we started to develop autonomous algorithms to do the station keeping. So you basically would have an autopilot that you could engage.
The computers are flying the airplane without your stick input, even in the system, to allow a piloted airplane to take 2, 3, or 4 unpiloted vehicles on a long distance trip.
We're just getting started on this technology. We'll use this technology to refuel unoccupied combat air vehicles.
The basket's slightly moving. Looks like it's going high. Okay, it detected a miss and came back on its own. So I did not do anything. She's got it. She's got it. Congratulations, guys. That was fantastic.
The Autonomous Soaring Project has one simple goal, is to program a small UAV to soar in thermals similar to the way a glider pilot or birds do. It has been reprogrammed to automatically detect that it's in an updraft and then use that updraft by circling. There's a wide variety of applications for this technology to help UAVs do things like forest fire detection, police surveillance, border patrol, and weather monitoring.
If the aircraft was damaged, you don't have to necessarily just rely on the pilot to compensate and fly the airplane. Adaptive flight controls, autonomous flight controls, different things where we're using the airplane to assist the pilot.
It will take over basically the controls of the airplane as far as flight stability.
The Platform Precision Autopilot is capable of staying on a given path within about 15 feet. It allows the synthetic aperture radar system to fly over essentially the same path more than once. This obviously has some potential applicability when you're looking at Earth's surface movements, such as after an earthquake, or if you're looking at an ice pack melting.
For the F-16, we went out and tested the system and based them on actual mishap cases. It prevented every single mishap. What we're developing here is merely an aid should the pilot get distracted or disoriented. By automating it, we can take out the pilot reaction time entirely.
The computer takes full control away from the pilot for a very brief period of time, and it redirects the trajectory of the aircraft to save the human.
ADS-B is automatic dependent surveillance broadcast. It's equipment on board an airplane that transmits its position and velocity information twice per second.
We are really trying to prove that we could use ADS-B as a way to do coordinated flight between multiple vehicles.
This system is present on a lot of manned aircraft, but we were one of the first UAS to perform testing of it in the national airspace. NASA has a project for integrating UAS.
So one day, UAS could hopefully fly with other commercial airlines and everybody will fly together safely.
There's various benefits to integrating unmanned aircraft, being able to monitor specific weather systems, monitor firefighters, delivering packages to your doorstep.
Operations to deliver medical emergency supplies, infrastructure, surveillance, and monitoring.
The technical side is a big challenge, but being able to integrate them safely is maybe even a bigger challenge.
To have thousands of these vehicles flying at the same time, you're going to have a lot more automation on the vehicle and in the airspace system.
Regulations for operations of the vehicle, regulations for airspace, regulations for infrastructure.
These aircraft are going to be highly autonomous, piloted, optionally piloted, unpiloted vehicle.
It's not just looking at the UAM, it's actually integrating the small UAS, the package delivery, or even the larger cargo delivery.
Subscale aircraft, we use those for a variety of reasons, to test things like new technology, which could be hardware or software, or even a completely new vehicle. You can do almost anything you want without much risk, and you can realize those gains very quickly. We're researching some level of autonomy. The aircraft, in most cases, are capable of taking off, flying around and landing without any human intervention. Things like ardupilots and multi-rotors and flying computers are allowing kids to play with research type tools that they never had access to before. So it's sort of driving in this new robotic learning type environment that never did exist.
Hey everybody, this is Beck, and I'm a maker of music. And like the great Sun Ra said, space is the place.
And I'm Farah, I work at NASA, and I use AI to explore Mars.
And I brought a few friends along who know something about artificial intelligence.
Hi, I'm John.
Hi, I'm Isabel. We are both artists working with NASA using artificial intelligence.
This is Ask NASA.
Yeah, so Beck, you just released a set of new music videos using a lot of NASA imagery, and I grew up loving space, and obviously those images are used by scientists. What inspires you about space, and how you came up with this idea?
Well, the title of the record came from a video game, a really primitive video game from the 80s called Asteroids. When the asteroids were going to kill you, and they were just about to collide with your spaceship, that you would hit this button and it would make you disappear and reappear somewhere else in the galaxy. And I always wondered what that button was called, and I looked it up one day, and it was called hyperspace. So I sort of, it got my mind thinking into music and song ideas. Because I think in some way, I think of music as sort of a hyperspace button. You know, it's something that we press play on a piece of music and it takes us somewhere out of our lives, out of our circumstances. But I did like the feeling of the music, that there was this sort of thread of outer space, kind of wide vista of space and time, existing in the songs.
Artificial intelligence is the ability for machines or computers to make autonomous and intelligent decisions. That can look like recognizing patterns or analyzing images or learning certain behaviors and then mimicking them.
I mean, right away when we heard hyperspace, we thought we have to use AI for this. Beck was already creating a sonic environment that went to like the edges of our understanding and the way that we see. And that's something that we're most excited about working with AI with, that it expands our modes of thinking. And then just the title, hyperspace, literally means to go beyond 3 dimensions. The one that we use for this particular project, it literally works in a 512 dimensional space. The process begins with the AI training on the images. So if we showed it just a few hundred, it wouldn't know that much. But what was so great about working with NASA's decades deep, archive of knowledge is that it could really learn. So for weeks and weeks, the AI trained on as many images as we could show it. I think in the end, it looked at over 25 million images. Sometimes that was multiple times looking at the same images to try and understand these images.
Yeah, basically imagery of anything in our solar system is how we get started in the process of exploration, right? And so when we first went to Mars, or when we sent Cassini to Saturn, we had some thoughts about what we might find based on that imagery, and that's what allows us to really focus down on the type of science we're going to do.
I worked a lot on the database creation, and I feel almost like I could draw a picture of the galaxy now just from going, like anyone can do, just by working with the NASA websites and going through the archives. Like the AI was then able to take that and recognize colors that were happening a lot, recognize shapes that were happening a lot. I remember when it first showed us what it thought Saturn looked like, I was blown away.
Yeah, and even then, seeing these images and getting all the info, it is overwhelming, isn't it? I mean, we're talking about other worlds, we're talking about other realities we probably won't ever get to experience in our lifetimes. This is the closest we'll come to touching the unknown. This project is so interesting because it really came out of the theme of the record. I would have loved the idea of taking sounds from these missions in space and putting them into the music itself.
The coolest thing that we have coming up, which we can point you to when it comes out, is that Perseverance actually has 2 microphones on board, and it's the first time we'll have real audio from Mars. So we'll have audio as we're landing on the planet, so that during entry, descent, and landing, and then we'll have audio when we're driving, or the rover has a laser, and so you'll be able to actually hear that laser zap on another planet, which is kind of something that's kind of hard to even wrap your mind around.
And that hasn't been recorded before?
No, not with a microphone, not this way. We've never had a microphone on the rover like that.
Okay, well, send those audio files my way when you get them.
Absolutely. So on Perseverance, we actually have an extra computer, and so that extra computer allows us to make the rover smarter. And we actually self-drive on Mars, so the rover has to take imagery of the area in front of it, literally build its own map. It can then identify different types of obstacles and slopes, and based on that and its knowledge of where it's able to drive, it decides on the path.
The Mars database was in one of the easiest ones because it's where we have the most high resolution imagery. It's been so well captured from so many different points of view.
We've seen the soil on a terrestrial level, and then we also have imaging of Mars from above, and looking through this data set of massive data set of incredible images. Once we trained the AI on that, it was able to kind of produce such vivid, strange imagery, because Mars itself, I think, is so much more complex and so much more deep and varied than we imagine it is.
Okay, so one more cool feature about the Perseverance rover is that it can also act as a scientist. The rover can look at the environment around it, look at all the rocks, and say, hey, this rock over there looks really cool. Let me image it, use my laser to zap it and figure out what's under that surface, send all of that data back to the scientists. So it allows us to essentially have scientists on Mars making decisions without having humans in the loop here on the ground.
I think, to me, the idea of space is a bit overwhelming and awe-inspiring. Just the idea of listening to a piece of music and we go somewhere else, our lives change. You know, it's a mirror to this other idea of space and space exploration, and letting the imagery of these other worlds, these unknown places with this music, I think has been really satisfying to me. It's you know, I feel really fortunate to have you all open your doors to me and my music, and for us to go somewhere with it that was unexpected, even for me.
Let's just make it space or something.
Here, let me get my video up.
Sorry, guys.
We'll get it. We'll get there.
We'll get there.
NASA. This is Ask NASA. I mean, that would be the show tune way. There's all kinds of guitars. This guitar is actually from 1901, and it has these ivory pegs. All right, so these are some vintage keyboards, and this is the 808, which is responsible for the sound of all trap music. This is the Moog, and this is responsible for most of the music of the 80s. There's a couple of pedals that I use, little bits and bobs.
The reason that you would do any kind of experiment in space is if there's something particular about the space environment, and most often that is microgravity. So mostly the ISS gives us the ability to either do something that we can't do in a facility on Earth or investigate some phenomenon, some property in a way that we can't on Earth. So for example, some of the tissue architecture, these really delicate tissues, as you start to build them up, they would collapse because you have gravity, or the cells would naturally settle to the bottom of the plate. And so you just can't study the answer to the question that you're looking for. So the space station lets us have that ability to either test what the effect of gravity is or remove that problem entirely from our experimental setup. Yeah, the space station's an incredible place to conduct research. It was sort of like being in the world's most amazing lab when I was up there in 2016. So when you're a scientist, you're used to working on one thing over and over and maybe really refining the details on that over the course of a PhD thesis or a lab project. On space station, you get somebody's incredibly refined project times 200 different fields. So for me, it was a chance to learn about all of these different areas of science, and they each have a team behind them. So I was usually pretty excited to open the container and do whatever experiment that day brought. I also really got a chance to talk to those PIs, the principal investigators, and those scientific teams, and understand everything that was going on behind their experiments and read their papers. So by the time I got to doing the experiment, I was pretty excited to take it out and to see what was going to change in microgravity. Yeah, science in space, it's an amazing lab and it's incredibly fun. So we are smiling all the time. I'm Kate Rubens. I'm a scientist and an astronaut.
The urban air mobility market is a rising market in the United States and around the world where highly efficient transportation aircraft seek to make commute times much shorter and very efficient compared to ground transportation, for example. So rather than having to force everyone to transport on the ground, if we can do short distance transportation in the air, we've taken some of that traffic congestion and spread it upward. NASA is trying to respond to that by providing the safety standards and the performance metrics by which all these aircraft can be judged and qualified for flight so that it's safer for the public and gets better performance. The X-57 Maxwell is NASA's first manned X-plane in over 20 years. This version happens to be the first fully electric X-plane that we've ever done. So what makes the X-57 unique is that for a similarly sized aircraft, the wing is actually 58% smaller than the baseline. What that means is it's very efficient in cruise. That, combined with the propulsion integration effects of the tip propellers and the fact that it's a fully electric system, have a combined design goal of a 500% improvement in efficiency over the baseline aircraft. So there are a few different ways that we try and test out various models to get an estimate of the performance or the behavior of the aircraft. And one of my favorites is using 3D printers to make prototypes of individual components or assemblies so that we can learn things like how the assembly might go together or how the dynamics of the system might behave. Another thing that we've done is to build wind tunnel models of the nacelles, propellers, and even a full vehicle test. And what we learned from that is to get detailed aerodynamic data on real-world parts. We also run extensive computational fluid dynamic analysis, and what that does is help us reduce some of the uncertainty in the regions of flight where this aircraft may operate. So now that we have the Mod 2 aircraft at Armstrong, we're ready to actually start the operations side of things, where we're going to be integrating, we're going to be flying. And what that means is we've gained enough momentum now to where the ball's rolling, and the pace is picked up in such a way that all of the things that we learn are feeding directly into the nascent urban air mobility market. So this isn't pie-in-the-sky dreamers reality of 10 or 20 years in the future. This is a right here, right now technology that's benefiting the taxpayer as we speak.
And as we leave the moon, we leave as we came, and God willing, as we shall return.
You probably dreamed of this.
Liftoff on Apollo 11.
You probably replayed this moment 1,000 times. You probably imagined the awe-inspiring, indescribable rush of the ride. You probably celebrated the miraculous, cheered the momentous, and mourned the shocking. You probably still dream of what could be. We did. We do. And while many thought we were through, no. We've been learning, we've been building, we've been training. And now, it's time. Because the next frontier is not just for the next generation. It's for this generation. It's for me, and it's for you. For everything we still dream about. We go as Artemis.
Advanced Air Mobility, or AAM, is NASA's vision to map out a safe, accessible, and affordable new air transportation system, enabled by transformational technology such as electric and automation, leading to both local and intra-regional applications. One area of innovation that Advanced Air Mobility will impact is in healthcare. Healthcare is an exciting AAM mission that is entirely focused on helping people by keeping them safe through contactless delivery and allowing for better access to healthcare through transportation services. NASA's Advanced Air Mobility mission is doing critical research and development on areas that will make the Advanced Air Mobility system safe and sustainable. Healthcare use cases are in their infancy within the Advanced Air Mobility ecosystem. Advances in both technology and regulatory environments will enable aviation healthcare use cases that better serve the general public. There are many things already happening in the healthcare industry with AAM, including lungs being delivered using drones, moving supplies to remote areas globally, performing medical deliveries such as prescription refills, and hospital systems using drones to deliver blood, creating efficiencies in their supply chain and getting results back to patients sooner. Another exciting area of AAM is urban air mobility, with multiple companies domestically and internationally focusing entirely on developing new types of innovative vehicles for use in the medical arena.
It's a new era of pioneers, star sailors, thinkers, and adventurers.
3, 2, 1, 0. All engine running.
Let's go.
We have been given the scientific knowledge, the technical ability, and the material to pursue the exploration of the universe.
NASA. The agency that landed on the moon, launched the Hubble Space Telescope, and took the first rover selfie? Yeah, that NASA. We also chase fires. This team is in the middle of a recovery operation. The California Department of Forestry and Fire Protection is using NASA satellite data to map the path of destruction after the 2018 Camp Fire.
NASA has the tallest fire towers, with our satellites looking down from space, catching images every day and every night. We're often the first to detect and then share information about fires, especially fires that are burning in remote locations.
That's where we can come in and provide a much better picture. And so I have NASA MODIS and VIIRS stuff, which we always use on Google Earth. You can kind of see the streets here. This is the neighborhood totally burned down.
A NASA Rapid Response grant allowed the team to study the impact of the Camp Fire just 4 months after it was contained. NASA provides crucial tools for both first responders and fire recovery managers. But there are even bigger implications for understanding the future of fire.
The information we collect from satellites helps us understand not just where and when fires are burning, but what kind of changes they're making to the ecosystems on the ground and our atmosphere up above. I'm Doug Morton, and I'm an Earth System Scientist here at NASA's Goddard Space Flight Center.
Doug is one of NASA's go-to scientists when it comes to making sense of how fires affect people and ecosystems.
You need 3 things to make a fire. You need something to burn. You need climate conditions that allow that fire to start and grow large. And you need a source of ignition. Today, the source of ignition is almost always humans. We can use information about rainfall and climate to anticipate landscapes that might become flammable in the future. That kind of predictive power, how we harness our understanding of the Earth system, has really helped us move forward in terms of anticipating and minimizing the risk to landscapes that might be flammable next week or even next season.
But the real work of science may be something that many people don't have a lot of visibility into. When we talk about taking a team of scientists and putting them into the field, that could mean weeks, months, or even years of collecting data.
The first time I spent in the Amazon was in the early parts of the 2000s, just at the peak of deforestation rates in Brazil. And I don't think anyone could make it to the end of that frontier landscape, standing at the edge of a road and looking in all directions and seeing towering columns of black smoke and not feel like there was an opportunity to be careful with our planet. Fires have been burning across the southern Amazon, an area where I've been working for the last 20 years. And so people have looked to me to explain, is this normal? One of the things I can do as a NASA scientist is I can go back in time. Our data record allows us to literally compare activities that are happening every day with these same days and the same kinds of conditions in previous years. From space, we're mapping fires across the entire planet, and that often takes us to remote locations. And the best way to partner and understand those remote locations is with people who live and work in those communities.
So that's what we did. This year, NASA is sending a blitz of missions into the field, and you're coming with us. Climate change is shepherding in a new era of fires that burn hotter and longer. And our pilots, our partners, our scientists and engineers, they've come prepared to meet that challenge.